Hi there, fantastic viewers. Welcome to an exciting journey into the world of compiler design. I'm thrilled to take you from the beginner's playground to the advanced realms of fascinating field. Throughout this course, we will unravel the intricacies of compiler design, starting with the fundamental concepts and progressing seamlessly to the advanced territories. Here is a sneak peek at what we'll be diving into. We kick things off with comprehensive introduction to compilers, laying the ground for our exploration. From there, we will delve into the various phases in a compilation, understanding how code undergoes a transformation. Next up, we will break down the key players in the compilation process: the lexical analyzer, syntax analyzer, and semantic analyzer. These concepts or these components work together harmoniously to ensure code correctness and efficiency. But wait, there is more. We'll venture into the intermediate compiler concepts, exploring the nuanced aspects that bridge the gap between the basic and the advanced compiler design. Brace yourself for a deep dive into advanced compiler topics where we tackle complex subjects such as code generation, memory management, and more. Our journey doesn't stop there. We'll shine a spotlight on special areas in a compiler design, including domain-specific languages or DSLs, parallel and GPU compilation, and compiler tools and frameworks. These are the cutting-edge topics that push the boundaries of what compilers can achieve. And to wrap it up all, we'll delve into a compiler construction projects, where theory meets practices. Get ready to apply your newfound knowledge to hands-on project that solidifies your understanding and skill set. So, if you are ready for an adventure into the heart of compiler design, buckle up. This video series is not just an education. It's a thrilling exploration into the future programming. Let's dive in and unlock the secrets of compiler design together. Computers work by using machine language or binary digits, zeros and ones, zero representing off and one representing on. In the early days, people interact with computers or machines by writing all these binary digits. They use the punched cards and the paper tapes to write these codes. Imagine a time when humans communicated with these colossal machines by inscribing these binary secrets onto punched cards, each whole and absence thereof representing a command or a data point. Yet, this method wasn't without its challenges. Picture this: a room filled with stack of punched cards, a single error potentially unraveling hours of meticulous coding. The complexity of managing these physical cards, debugging errors, and the sheer inefficiency of the process left for programmers to work on. In the mid-20th century, a game-changing innovation emerged: a language translator. These transformative tools liberated programmers from the laborious tasks of handcrafting binary instructions. Instead, they could write a code in a higher-level language, a language closer to human understanding. The first of these translators was the assembler, utilizing assembly language as an intermediary step between high-level language and the binary machine code. In the left side, you can see these binary digits. If you want to write compiler design, you have to write these binary digits or machine language code in the early days. But by using assembly or assembly language, using some commands, you can write it easily. However, even this leap forward wasn't without its quirks. Assembly language, while more readable than raw binary, still required a deep understanding of the computer architecture. programmers have to grapple with the intricacies of specific hardware, making portability a significant challenge. As technology evolved, so did the need of more sophisticated and user-friendly solutions. Interpreters and compilers, two revolutionary concepts that changed the landscape of programming. Interpreters functioned on the fly translators, executing code line by line. While they provide flexibility and ease of debugging, the trade-off was performance. The translation process happened in real time, introducing overhead. On the other hand, compilers emerged as the powerhouse of language translation. They took an entire program written in high-level language and translated into the machine code in one go. The result? Well, faster execution but a less forgiving debugging process. The program had to be error-free before compilation, or the process would halt. Compiler is a program that can read program written in one language or the source language and translate it into the equivalent program in another language or the target language. As you see here in the diagram, we could have the language that we want and it would be translated to the machine language or binary digits. One advantage of compilers is that they have two aspects. The first one is source to source compilers. The next one is source to machine compilers. Source to source compilers means that you can change one language to another language which is not machine language. This is very one advantage of compilers. The next one is the default one, or you can change the language that you want to the machine language to interact with the machine or the computer. In a sense, from the cumbersome days of punching cards to the advent of interpreters and compilers, the evolution of language translation had marked a pivotal chapter in the history of computing. These innovations not only bridged the gap between human and machine language, but also paved the way for the sophisticated software we interact with today. As we marvel at the ease of which we write code in modern times, let's tip our hats to the pioneers who transformed the early days of computing into the dynamic landscape we know today. Next, let's see the importance of compiler design. The first one is transformative role. Compiler design plays a transformative role in a software development process. It acts as the bridge between high-level programming language and machine executable code. The next one is programming efficiency. Compilers enable programmers to express complex ideas in high-level language without worrying about the intricacies of machine code. This separation allows for more efficient and expressive coding. The next one is creativity unleashed. With the burden of low-level details lifted, programmers can focus on creative aspects of software development. Writing a code becomes an art, and compilers are the facilitators of this creative process. Next, we have programming paradigm diversity. Compilers have enabled the development of diverse programming paradigms, from procedural to object-oriented functional programming. Compilers have adapted to different styles. Now we have many languages that use compilers like C++, C#, Java, and so on. Next, we have the software innovation. The efficiency brought by the compilers have fueled software innovation. From operating system to applications, compilers have played a crucial role in development of digital ecosystem. Now, check how many of these softwares in your computer and mobile applications use compilers. Now, let's see the prerequisites for this course or compiler design course. The first one is programming language. For this course, we are going to use C++ as the main programming language, but you can choose any programming language that you are comfortable with, like Java, C Sharp, or any other. But remember to pick a language that uses compiler rather than interpreters, like Python and JavaScript, which uses interpreters. The next one is data structures and algorithms. A little bit of knowledge on data structures and algorithms would help you to understand some of the algorithms that we are going to write. The next one is discrete mathematics. A little bit of knowledge on mathematics would help you, especially in the front-end part, like lexical analyzer, semantic analyzer, and parsers, because we are going to write some mathematics there. Next, knowing a software engineering principles would help you understand some of the theories that we are going to talk about. Next to that, a usage or understanding of text editor or IDE usage is very essential. For this course, we are going to use VS Code, but you can choose any other also. After this, let's look at the setting up development environment. The first thing that we need for this project is pen and paper. Especially in the front-end part, there is going to be some mathematical works that we are going to write. So I suggest you have pen and paper ready when we are working on that. Next to that, we are going to use text editors to write some code. For this project, I'm going to use Visual Studio, but you can choose any other text editor. After that, we need a compiler and build tools for C++, because I'm going to use C++ for this course. And we are going to install MinGW and or CMake. After this, the reference material that you can read about for further is Compiler Principles, Techniques, and Tools, second edition by Addison Wesley and its colleagues. It's a very great book, so I suggest reading that book would help you understand more on compiler designs. Now, let's see how to install our text editor or Visual Studio and MinGW. So let's type Visual Studio on Google and we can find the Visual Studio here, the right one. You can also type this code.visualstudio.com directly and you find here download for Windows. I'm currently using Windows, so it's going to show me window. If you are using Mac or any other, it will show you the right one. So click this button and you download the software application, then you install that one. I have already done that one, so I don't have to download the VS Code. Next, after this, let's go to the docs here in the Visual Studio. And in here, we find some documentation and we also find some documentation how to integrate for some language. So we are going to use C++. So let's go to the C++ here. And I'm using Windows, so I'm going to choose this GCC on Windows. You can choose on Linux or Mac. And in the documentation, the prerequisites are first installing Visual Studio, then installing extensions of C++ extension. But I'm going to leave that one. I will go back to this later. First, let's install the MinGW. So we can get the link for the MinGW here. So let's click this link, direct link to the installer. It's going to redirect us. And let's save it. After the download is complete, we are going to install this min.jw file. Let's click on run. Next. After the installation is complete, we are going to follow some instructions to integrate this min.jw. After it finishes, let's run the MSYS2 application now, and let's click on finish. Let's paste this code to our command. Right click there, paste, then hit enter. Then we click enter again, and we type Y to accept the installation. It may take a few minutes to finish this installation. After the installation completes, let's add the environmental variable of min.jw to our PC. So let's go here and select this line and copy it. Then let's go to our settings. In the settings, let's search for environmental variables for your account, and this pop-up is going to appear. And if you have the path here, click on it and then new, then paste the one that you copied here and click on OK. If you don't have path here, for some cases, you can create it here and give it the name path and give the value of the copied value here, paste it, and then click on OK. But since I have the path here, I am going to drop the copied value here in the path. Then click on OK. Now let's open our VS Code. In the VS Code, let's search on the extensions here in the left bar, C++, C++, and we are going to get this C++ package, but we are going to install this C++ extension pack. I think it contains more than 3 packages inside it, so let's install it. I currently installed this, so I don't have to install it again, but you can click here and it's going to appear an install button there, not disable. Then after that, everything is ready. But one thing that left is, let's go to the command prompt or cmd and check if our C++ values are installed correctly. How we do that is by typing this one, G++ version, GCC version, and all the 3 of them. Then we paste it here, and yeah, as you see, the version is visible here. Let's check the next one, G++. And it is installed correctly. And for the last one, it's GDB version. So everything is working fine and it is installed correctly. So we are ready to go. And currently now, you can create your VS Code here in the documents by creating on by going directly here and new file, and you can create your C++ file, and the extension for C++ is .cpp. Thank you. Guys, in this section, we are going to see compiler design. We are going to see the introduction part of the compiler design, what compiler means. Also, we are going to see the language processing system, how it works and what does it mean. Also, we are going to see the difference between compilers and interpreters. Plus, at the end, we are going to see the phases in compiler design. So, let's jump into it. First, what's compiler? Compiler, at its sense, is a sophisticated program tasked with the crucial role of translating a program written in one language, known as the source language, into an equivalent program in another language, termed the target language. This is the general and the specific meaning of what compiler means. This translation is essential because the computers understand and execute instructions in machine language, which is binary code comprising ones and zeros only. The source language is typically a high-level programming language, such as C++, Java, or any other language, whereas the target language is a low-level machine code specific to computers' architecture. Now, let's see types of compilers. The first one is source-to-source compilers. This is also known as the transpilers, performs a translation from one high-level programming language to another high-level language. The purpose of these compilers are employed when there is a need to migrate code from one programming language to another, while maintaining the structure and the functionality of the program. It facilitates code portability and can be useful when transitioning to a more modern or efficient programming language. For example, a source-to-source compiler might convert a code from Java to C++, enabling the execution of the Java code within a C++. The next one is source-to-machine compilers. These are more traditional type of compilers that translate high-level source code directly into machine code executable by computer CPU. The purpose or the primary objective is to generate efficient and optimized machine code that can be executed directly by the hardware. This type of compiler is a crucial component in the software development process, enabling the creation of standalone, platform-specific executable program. For example, when you compile a C++ program using a source-to-machine compiler, it translates the C++ code into a machine code, producing an executable file that can run on a specific computer architecture without any further translation. In summary, compilers serve as a linguistic bridge, allowing programmers to express their ideas in high-level language while enabling computers to execute these instructions in low-level machine code. The categorization into source-to-source and source-to-machine compilers reflect the diverse need of programming landscape, accommodating scenarios ranging from language migration to efficient code execution on a specific hardware platform. Now, let's see the language processing system. Let's elaborate on each step in the diagram, breaking down the stages of the language processing system in the context of a compiler. First, we have the source program. The source program is the original code written by the programmer in a high-level programming language, like C++, Java, or some other computer language. The purpose of this is the human-readable representation of the intended program logic and functionality. This is high-level language. Next, this source program enters the preprocessor. The preprocessor is initial phase of the compiler. It processes the source program before the actual compilation. The preprocessor handles tasks such as file inclusion, macro expansion, and conditional compilation. It transforms the source program into a modified source program, resolving any preprocessor directives. It changes to pure high-level language. For example, in C++, we add some libraries or modules at the top, like hash include and hash define at the top. And in the preprocessor, we are going to include these libraries or modules to our own code, making it like the pure high-level language. Next, this modified source program enters the compiler. The compiler is the central component that translates the modified source program into an intermediate form, often in the form of target assembly language or intermediate code. It performs a lexical syntax and semantic analysis, generating an intermediary representation that captures the structure and the logic of original source program. This compiler can change the language to the binary or machine language, but for the productive purpose and the time purpose, changing it to directly to the assembly language is more preferable. That's why we are changing it to the assembly language or target assembly program. Then we have next assembler. The assembler is responsible for translating the intermediate code or target assembly language into the relocatable machine code. This step involves mapping the symbolic instruction of the assembly language into the specific binary instructions understood by the computer's architecture. The output is a relocatable machine code. Next, we have linker and loader. The linker and the loader are often combined into this step. The linker resolves references between different programs, modules, and combines them with external libraries. The loader loads the executable program into memory for execution. The purpose, when you see the purpose, the linker creates a cohesive program by combining the relocatable machine code with external modules, uses other programs or libraries of programs, while the loader then prepares the program for execution by loading into the computer's memory. Combined program must be moved into the memory. In essence or in summary, this language processing system embodies a sequence of transformations that convert a human-readable source program into executable target machine code. Each phase in this process plays a distinct role, from pre-processing to compilation, assembly, and finally linking and loading. The system ensures that a high-level logic and structure of original program are faithfully translated into a form that the computer can understand and execute. Let's see the difference between compilers and interpreters. Let's start from the processing approach. For compilers, compilers scan the entire program before translating it into the machine code. This global analysis allows for extensive optimization and can result in more efficient executable code, while interpreters translate the program one statement at a time. This incremental approach allows for quick analysis, making it suitable for scenarios where rapid feedback is necessary. This is especially for testing modes, error finding or debugging. It is very good, the rapid feedback system. Now, let's compare them in execution time. Although compilers take a significant amount of time to analyze the entire source code, the overall execution time is usually faster compared to interpreters. The upfront investment in analysis pays off during execution, as the compiled code tends to run more efficiently. While interpreters take less time to analyze the source code, the overall execution time tends to be slower. The lack of compiled form may result in repeated analysis of same code during execution, impacting performance. Now, let's compare them on error handling. Compilers generate error message only after scanning the entire program, making the debugging comparatively challenging. Debugging may involve identifying errors from potentially distant points in the code, and the feedback loop is less immediate. Interpreters continue translating one program until the first error is encountered, at which point they stop. Debugging is facilitated as the interpreter provides immediate feedback when it encounters the first error, allowing for quick identification of issues. Additionally, we can also compare them on portability and other things like memory usage. In the portability, compilers generate machine code specific to target architecture, potentially resulting in more efficient and platform-dependent executables. Interpreters tend to be more portable as they analyze executable code dynamically, adapting to the host environment during runtime. Now, let's compare them on memory usage. Compilers can generate a standalone executable, leading to potentially lower memory usage during execution. Interpreters may require more memory as the source code is analyzed and executed in real time. In conclusion, the choice between compilers and interpreters depend on specific requirement of a given scenario. Compilers offer optimized performance at the cost of a long upfront analysis, while interpreters provide a quick feedback and easier debugging but may sacrifice overall execution speed. Considerations such as staggered platform development workflow and debugging preferences play a crucial role in determining the most suitable approach. Most of the time, for web development, we use the interpreters like JavaScript, and for things like C++ codes, we use the compilers because they require more sophisticated work. Now, let's see the compilation phases or steps. Compilation contains 6 steps or phases that are very crucial while compilation or translating one language to the another one. The first one is lexical analyzer. The next one is syntax analyzer. The third one is semantic analyzer. The fourth one is intermediate code generation. The fifth one is code optimization, and the last one is code generation. These are the basic steps in compilation process. In the right side and in the left side, we have error handler and symbol table manager. We are going to see each of them one by one. By unraveling the intricate details of each phase, we gain a comprehensive understanding of the compiler's role in translating abstract program constructs into a form of executable by computers. First, let's look at the lexical analyzer, or the first phase. The lexical analyzer, often referred to as a Lexer, is an initial phase of compiler journey. Its fundamental role is to meticulously traverse the source code, breaking it down into elemental units known as tokens. These tokens encapsulate the essence of code, encompassing keywords, identifiers, literals, and operators. This lexical analyzer is sometimes called token analyzer. What it does is it reads streams of characters, and it groups the characters into meaningful sequence called lexemes. For each lexeme, it reproduces a token in the form of token name and attributes value. The token name is an absent name that will be used during syntax analysis, while the attribute is the value that points to an entry in symbol table for this token. We are going to cover it in details later, but let's see some things. When you see the functionality, by scrutinizing the source code character by character, the Lexer identifies and categorizes these tokens. For instance, consider the code snippet int x is equal to 10. The lexical analyzer would distinguish between the keyword int, the identifier x, the assignment operator equal sign, and the numeric literal 10. For example, we can also mention another example. Let's see this example. We have position equal to initial plus rate times 60. What the lexical analyzer would do is first, it takes position and it is a lexem that would be mapped into the token as you see it here with ID and 1. Next, we have equal sign and it is a lexem that's mapped to an equal sign. After that, we have the initial, which is a lexem that would be mapped into ID and 2. After that, we have the plus sign, which is the lexem also, and it is mapped to the token plus. After that, we have the rate, and it is also a lexem that would be mapped into a token ID and 3. Then we have the multiplies, and it was also mapped into a token multiply sign. At the end, we have the 16 digits, and it is a lexem that's mapped to 60. By doing this, the lexical analyzer changes the format of the code or the function that we gave him. And what it does is it will give it this kind of style. And this position is called to initial plus rate times 60 is going to look at like this. The key takes from this are the inputs in strings and outputs are the tokens or lexemes. And in lexical analyzer, it eliminates the comments and white spaces. Token is a sequence of characters. It can be an identifier, keyword, operator, special symbol, constant, and so on. As you see here, we have different kind of tokens, like here operators and also another symbols. Lexem is a sequence of characters that can be matched by a pattern for a token. Tokenization is the process of forming a token into input stream. Next, we have the syntax analyzer. When you see the purpose, following the lexical analysis, the syntax analyzer or the parser steps into the scene. Its pivotal role involves scrutinizing the sequence of tokens generated by the lexical analyzer to ensure they adhere to the grammatical structure specified by the programming language. When you see the functionality, imagine a simple assignment statement such as variable is equal to expression. The syntax analyzer ensures that the token form a valid structure resembles the expected syntax. It navigates through the token stream, verifying that identifiers align with the assignment and expression aligns with their respective operations. The parser uses the tokens produced by the Lexer analyzer to create a tree-like intermediate representation called a syntax tree that describes the grammatical structure of the token stream. When you see this lexeme, it is produced by the lexical analysis, and in the syntax analysis, it's going to be changed to a syntax tree. It's going to look like this. We have the ID1 equals with these values, and it would have its own hierarchical tree. Each interior node represents an operation. The nodes are the operations as you see. The children of the node represents the arguments of or the operations. Here we have the arguments in the each leaf. From the words, next step is to understand the sentence structure. Program that takes token and grammar as an input and validates the input tokens against the grammar. Generate a parser tree or a syntax error. There are two types of techniques, top-down approach and bottom-up approach in syntax analyzer. We're going to cover that later, but this is the main purpose of the syntax analyzer. It creates a syntax tree and it checks the grammatical structure specified by programming language. We have semantic analyzer. When you see the purpose, moving beyond syntax, the semantic analyzer ventures into the realm of meaning within the source code. It scrutinizes the program to identify and rectify semantic errors, ensuring adherence to the language rule and constraints. When we see some things on semantic analyzer, currently we have two things, type checking and type conversion. Let's see them one by one. Consider the statement int x is equal to hello. Here, the semantic analyzer plays a crucial role by recognizing the type mismatch between the expected integer type of variable x and its incompatible string value hello. It is responsible for ensuring that the program not only adheres to syntax rules but also aligns with the intended semantics. It uses the syntax tree and the information in the symbol to check the source program for semantic consistency with language definitions. It gathers the type information and performs type checking. It checks that each operator has a matching operand. And as you see now, this is an integer and it's given a string value, which is wrong. So it checks or it type checks in the semantic analyzer. The next one is type conversion. As you see here now, we have position equal to initial plus rate times 16. The semantic analyzer first converts integer 60 to a floating point number before applying the times. This is how it works, the semantic analyzer. Now, let's look at intermediate code generation, or the fourth phase in compilation. After syntax and semantic analysis, many compilers generate an explicit low-level or machine-like, which we can think of as a program for an abstract machine. When you see the purpose of the intermediate code generation, as the compiler proceeds, the source code undergoes transformation into an intermediate representation, a critical step for abstraction and portability. The intermediate code generation has two properties when it works. The first one is it should be easy to produce and it should be easy to translate into the target machine. When you see the functionalities in the context of expression a is equal to b plus c, the intermediate code may take the form of three-address code, such as t1 is equal to b plus c, a is equal to t1. This stage paves the way for the subsequent optimization process while providing an intermediary form that abstracts away machine-specific details. 3. Address code consists of an assembly-like instructions with a maximum of 3 operand per instruction. Each operand can act like a register. Let's see the output of the intermediate code generation. Currently, we have this generated from the lexical and semantic analysis. And let's see the intermediate code that is generated. It has 4 functions here, and as you see, it is very simple. But the thing is, currently we haven't described them each one by one, but to show you, the first one is the t1 or int to float 60. First, it has a function t1 which changes this 60 to float. Next, it gives t2. T2 means that id3 times t1. This is the t2 that we have function, and the next one is the t3 or this one. This T3 is ID2 plus T2, and the next one is ID1, and the ID1 is going to be equal with T3. And as I said earlier, each operand can act like a register. Here we have equal sign, plus sign, and multiply sign. They can act like a register. The compiler must also generate a temporary name to hold the value computed by the three address instructions. As you see now, T1, T2, T3, and ID1 are all the temporary names that are generated by intermediate code generation to hold the values computed by ICG or intermediate code generation. Next up, we have the code optimization phase, or the fifth phase in compilation process. This code optimization phase delves into refining the intermediate code to enhance the overall performance of the generated executable. Automatically, it modifies the program so that they can run faster, use less memory, and conserve some resources. The three things are it automatically modifies the code to run faster, use less memory, and conserve some resources. When we see the code optimization, it has two types. The first one is the machine-independent code optimization phase, which attempts to improve the intermediate code so that better target code will result. The next one is the machine-dependent code optimization phase. When we see the functionality, so through the myriads of techniques like constant folding, loop optimization, and dead code elimination, the optimizer works to streamline the intermediate representation. For instance, the expression a is equal to 2 times 3 might be optimized to a is equal to 6, eliminating the redundant multiplication operation. Here we have the previous code generator that from the list diagram that we're working on. And this code can be optimized. If you look close, it can be converted to this code, merging the inflow code to not that one, merging the other codes to this one would give the value to the correct code. Remember, in code optimization, there are three things that are modified. It makes the code run faster, use less memory, and conserve some resources. The last part of the compilation process is the code generation. In the final stage of the compilation journey, the code generator transforms the optimized intermediate code into the target machine code, tailored to the specific hardware architecture. The target code generation will generate an assembly code that is specific to the platform that is running on. The code generation takes an input intermediate representation of the source program and maps it into the target language. If the target language is a machine language, registers or memory locations are selected for each of the variables used by the program. A crucial aspect of the code generation is the judicious assignment of registers to hold variables. When you see the functionality in the code generation, taking the optimized intermediate code a is equal to 6 as an example, the code generator produces a machine code instruction such as move 6 space a, ensuring compatibility with interfaces of the target machine. For example, using the register R1 and R2, the previous intermediate code might get translated into the machine code. This is the code that we used earlier, and we have the position is equal to initial plus rate times 60, and in the lexical analyzer we convert to this Lexer, and after that we worked on the semantic analyzers, syntax analyzer, the code generation optimization process, and we get this code. T1 is equal to ID3 times 16, which is the float here, and ID1 is equal to ID2 plus T1. And this code can be generated to the machine code or assembly code like this. This is the generated code that we have after the code generation process. We have the assembly language written from this function to now we have this code generated or assembly language generated. At last, all these phases of the compilation process are interconnected phases. They are interconnected through the symbol table manager. Throughout this multi-phase journey, the phases of the compiler operate cohesively, with each other phase built upon the result of the preceding one. This interconnectedness ensures the systematic and through transformation of human-readable source code into efficient and executable machine code. But let's see the symbol table management. The symbol table is a data structure containing a record for each variable name, with fields for attributes of the name. An essential function of a compiler is to record the variable names used in source program and to collect information about various attributes of each name. These attributes may provide information about the storage allocated for the name, its type, its scope, where in a program its value can be used, and in the case of procedure names, as the number and types of its arguments, the method of passing each argument by value or by reference, and by type returned. In the right side, we have the error handler. This error handling and feedback in the intricate process, error handling is a paramount, meaningful error message provides it for developers, with the feedback needed for effective debugging. When you see as a general for symbol table manager and error handling, these are components of a compiler that every step of the process has to include. They handle the definition of grammar and what is correct in a given compiler. They also describe measure the compiler has to make when there is an error detected. This is the steps and the phase in compilation process. Now that you have seen the compilation process and its phases, mention and show the compiler phase of this kinematic equation. We have here distance is equal to vt plus half at square, where v is velocity, t is time, and a is acceleration. Try to name all the steps and mention what they do, all the steps. Plus, if you can, try to come up with their response or their output of each compiler phase. There are 6 phases in compiler to transform this string to the given instruction. And when you come to the solution for this equation that we have, the first phase is going to be the lexical analyzer. This eliminates the comments and white space, and it takes an input of string and gives an output of tokens or lexemes. So when we take this equation, then it's going to transform it to the given token or lexeme. So it's going to identify the given identifiers, white spaces, it removes white space and comments also. So it's going to transform this distance to identifier 1, and it's going to identify this equal equation also, and this v, t, a, and t are all identifiers, so it will give them an identifier and assign them some number. And also it's going to add a times button. If you see it in the lexical analyzer here in the answer, we can find that it's added the times between these identifiers. Generally we don't write the times when we write it like this, but we assume that there is a multiplication between these two tokens. So it's going to add it and it's going to pass it to the syntax analyzer or the parser. So the parser is going to generate a tree based on this lexeme. So this is how it looks when we see the parser, how it parses, and it's going to make a tree. And this program takes tokens and grammars as an input and validates the input tokens against the grammar. Next to this, we have the semantic analyzer. And the semantic analyzer, once the tense structure is understood, we can try to understand the meaning using the semantic analysis. The syntax analysis is going to check the grammar structure, but not the meaning. But in the semantic analyzer, it's going to check if it is right or wrong, or the meaning of this equation that we have. Next to that, we have the intermediate code generation. And as the name indicates, it generates an intermediate code for the given tree. And usually it generates a three address code, and it's going to be an intermediate code that is closer to the machine code. After that, we have the code optimization, which automatically modifies the program so that it can run faster, use less memory, and conserve some resources. And the end is going to be target code generation, which will generate an assembly code that's specific to the platform that is running on. So these are the steps in the compiling of this given equation. Hello everyone. In this section, we are going to see the lexical analysis. We will see how to construct a lexical analyzer. We will implement a lexical analyzer by hand, which helps to start with the diagram or other description for the lexemes of each token. We then write a code to identify each occurrence of each lexeme on the input and to return information about the token identified. We begin the study of lexical analyzer generator by introducing regular expressions, a convenient notation for specifying lexeme patterns. We see how the notation can be transformed first into non-deterministic automata, then into deterministic automata. So, without further ado, let's jump into it. As the first phase of the compiler, the main task of the lexical analyzer is to read the input characters of the source program, group them into lexemes, and produce as the output a sequence of tokens of each lexeme in the source program. The stream of tokens is sent to the parser for syntax analysis. It is common for the lexical analyzer to interact with the symbol table as well. When the lexical analyzer discovers a lexeme constituting an identifier, it needs to enter the lexeme into the symbol table. In some cases, information regarding the kind of identifier may be read from the symbol table by the lexical analyzer to assist in determining the proper token it must pass to the parser. We can see it from the graph now. In here, we have the source code. The source code enters the lexical analyzer, and there is a send of token from the lexical analyzer to the parser, and also the parser asks the lexical analyzer to get the next token, and in the middle between them there is a symbol table which they interact both with it. And as I said now, the symbol table is very essential because it helps to store the identifiers of the lexical analyzer, and the lexical analyzer refers to the symbol table most often. We can see from the graph that the interaction is implemented by having the parser called the lexical analyzer. The call suggested by the getNextToken command codes the lexical analyzer to read characters from its inputs until it can identify the next lexeme and produce for the next token, which is returns to the parser. Since lexical analyzer is part of the compiler that reads the source text, it may perform certain other tasks beside identification of lexemes. The tasks that the lexical analyzer do beside the identification of lexeme are: the first one is stripping out comments and white spaces. These white spaces are blanks, new lines, tab, and perhaps other characters that are used to separate tokens in the input. The another task is correlating each message generated by the compiler with the source program. Here we have a code that's written and it is the source code. In the lexical analyzer, it is going to be transformed into this code, which is striped out comments and white spaces. As you see now, the comments are out and also the white spaces and the new lines are represented by here, backslash and new line, and for the tab, backslash and T represents the tab. And this is how it's represented. And the next one that I mentioned is correlating error message generated by the compiler with the source program. For instance, the lexical analyzer may keep track of the number of new line characters seen, so it can associate the line number with each error message. In some compilers, the lexical analyzer make a copy of the source program with the error message inserted at the appropriate positions. If the source program uses a macro preprocessor, the expansion of macros may also be performed by the lexical analyzer. Sometimes, lexical analyzers are divided into cascade of two processes. These are scanning and lexical analysis. The scanning consists of simple processes that don't require tokenization of the inputs, such as deletion of comments and compaction of consecutive white space characters into one. The next one is the lexical analysis, which is the more complex portion, where the scanner produces a sequence of tokens at the output. As you see now, the scanner part is only removing the comments and removing the white space, the new line, the tab, and all. But the next one is the lexical analysis, which is more complex and which is most of the part of the lexical analyzer are done here. So the goal of the lexical analyzer is to partition input strings into substrings, where the substrings are tokens. So what's token? Let's see it next. There are three concepts: tokens, patterns, and lexemes. When discussing lexical analysis, we use these three related but distinct terms: a token, a pattern, and a lexeme. What is token? Token is a pair of consisting of token name and an optional attribute value. The token name is an abstract symbol representing kind of lexical unit. For example, a particular keyword or sequence of input characters denoting an identifier. The token names are the input symbols that the parser processes. In what follows, we shall generally write the name of the token in boldface. We will often refer a token by its token name. In simple terms, a token is a categorized meaningful unit resulting from the lexical analysis of the source code. The next one is the pattern. A pattern is a description of form of that the lexemes or the token may take. In the case of keyword as a token, the pattern is just a sequence of characters that form the keyboard. For identifiers and some other tokens, the pattern is a more complex structure that is matched by many strings. And the next one is a lexeme. A lexeme is a sequence of characters in the source program that match the pattern for a token and is identified by lexical analyzer as an instance of that token. Tokens and lexemes are closely related concepts in compiler design, but they represent different aspects of lexical analysis phase. To see the difference, let's use this example. Int x is equal to 10. First, as I said, a token is a categorized meaningful unit resulting from lexical analysis of the source code. It represents a group of characters that together form a single entity, such as keyword, identifier, literal, or operator. In the statement int x is equal to 10, the tokens include the keyword int, the identifier x, the assignment operator equal sign, and the numeric literal 10. What about the lexeme? A lexeme is a sequence of characters in the source code that match the pattern for a particular token. It is the raw unparsed substring that corresponds to a token. In the example, int x is equal to 10. The lexemes include the entire word int or the entire word int that we have here, int. The next one is the identifier x, the symbol equal sign, and the numeric literals 1 and 0, which is 10. And when you see the difference, the key difference lies in their abstraction level and their perspective form, which they are viewed. Tokens are high-level abstract entities that represent the categorized units derived from lexemes during the lexical analysis. Tokens are the result of categorization and classification process, while lexemes are low-level concrete substrings of the source code that match the pattern defined by the regular expression for the specific tokens. Lexemes are raw input elements that are subsequently recognized as tokens. So let's look at it more. Here we have a chart or a table that shows us the difference between tokens and lexemes. As I said, tokens are high-level and general word or general categorization, while lexemes are low-level and they are defined by regular expressions for a specific token. In here, we have the if here, and this if is made of characters I and f, and for the sample lexeme, it's going to be an if. Okay, let's look at the simpler one first. In here we have number. The token name is number, and what is number? Any numeric constant, right? So this is the description of the token, and the sample lexeme can be any number, any expression that makes true for this statement any numeric constant. We can choose this 3.14, 0, 6, or any other number, but it must include numbers only, and it doesn't have a non-numeric word. So this lexeme is a token, which is a number token. And also for the comparisons, we have this equal sign, less than, greater than or equal to, and many more. For the sample, we can take this less than or equal to or not equal signs, and these are sample lexemes and they are comparison tokens. And for the else, also for the if, and also for the literals. And for the literal, anything that is surrounded by quotation can be a literal token. And for the sample, we can take apple, which is enclosed by quotation, and more. And for the ID, which is letter followed by letter or any digit, and we can have a lexeme sample lexeme of core, high, d2, or many more. So this is how the difference between the lexeme and the token. It's essential to recognize the difference between them. And as I said earlier, tokens are very high level and abstract entities that represent the categorized units derived from lexemes. And lexemes are low-level concrete substrings of the source code that match the pattern defined by the regular expression for a specific token. In summary, while tokens represent abstract categorized units resulting from lexical analysis, lexemes are raw concrete substrings from which tokens are derived. Lexemes are input elements that match the pattern specified for the token in the lexical analysis phase of the compiler design. For the last time, let's look at the number because it is easy to understand. In the lexical analysis, first we propose that number tokens are numbers or number tokens are tokens that have numeric constants, and the lexeme would only have to be a token would have only numeric constants in it. It doesn't have any non-numeric constants. If it has, it won't be this number token. So this is the difference between tokens and lexemes. Now, let's see regular expressions. Earlier, we were talking about some identifiers, such as keywords identifiers, literals, and operators. But the question arises, what makes a lexeme an identifier? What makes a lexeme a keyword? Or what makes a lexeme a comparison operator? What are the specifications for the token to be an identifier, keyword, or an operator, or another literal? Well, the answer is regular expressions. Regular expressions serve as a powerful tool for specifying patterns that lexical analyzers can recognize. They define the rules for identifying tokens such as keywords, identifiers, literals, and operators. Now, let's see what regular expressions means. But first, before jumping into regular expressions, let's see what regular language means. Regular language, for example, let sigma be a set of characters. A language over sigma is a set of strings or characters drawn from sigma. Meaning that if you have one regular language, a language over sigma, or that language must be from the characters drawn from that sigma or from that language. For example, if you take English, the alphabets are the characters and the language is the sentence, meaning that you have the language that are created from these alphabets from A to Z. You don't have any, you don't have any alphabet or characters that are not from the alphabet. That applies for the programming. For the alphabets are the ASCII codes, and the language is the program that we write. So these programs don't take any alphabet other than the ASCII. These regular languages are one of the several formalisms for specifying tokens. Regular languages are simple and useful theory, and they are easy to understand and efficient in implementation. Because one language must be efficient to be used as a language, it must have characters and all the things that a language should have. And the standard notation for regular language is regular expressions, because all the characters are nothing if we don't create we don't have a regular expression or something like a command that suggests this is a sentence, this is not a sentence. So when we go to the regular expression, a regular expression is a set of rules and techniques for constructing sequence of symbols or strings from an alphabet. Let sigma be an alphabet and R be a regular expression. Then L of R is a language that is characterized by the rules of R. Meaning that if you have an alphabet and if we say that R is a regular expression, then L of R is language that is characterized by the rules of R. Meaning that the regular expressions act as a rule that guides this is a language literal or this is an identifier or so on. While working on the regular expressions, there are some rules that we follow. Things that we should consider. The first one is when you have a single character, for example, let's take C, we are going to show that this single character as like this, with single double quotation in sets. And when you have an empty set or an epsilon, this is how we represent it, with double quotation and empty double quotation. When you are unioning two identifying tokens, for example, for keyword and for the identifier, if you are unioning them, this should be respected. A union B, where S is A union B and S must be an element of A or S is an element of B. And in concatenation, when you are concatenating two tokens, A concatenates B, where A must be an element of capital A and B must be an element of capital B. And during an iteration, A asterisk, where A is an element of U and A the power of I, where I is the times that the iteration is going to work on. We are going to see this in example to clarify it more. So let's go to our examples. In regular expression, let's see some of the tokens that we have. For example, for integer, for identifier, and for the white spaces. The first one is the integers. In the integers, we know that how many characters that we have in the integers or the digits. Let's say them the digits, because every integer is made up of all these digits from 0 to 9. There is no other digit that is used in the integer. So how do we express any integer in regular expression? The answer is like this. Integer is represented by digits concatenated with digits asterisk, meaning that it must be a digit, because by default if it is an integer, there must be a number, right? So by default there must be a number. But if it's included, for example, if you are saying 10, 20 or 300 or 1000, there are other digits that are becoming coming next to the first digit. So we have to add this asterisk next to the digit that we have here. And in the abbreviation, if you have a regular expression like this, where digit comes and then digit asterisk, we can represent it by this, like here, by changing the power using the plus instead of the asterisk and removing the first one. We can abbreviate it like this. The next one is the identifiers. Identifiers are characters or letters from A to Z in capital and from A to Z in small letters. And we know that these identifiers have things that they follow. And the thing is that in identifier, the first character should be a letter, and next to that it can be a digit or a letter as it wants. So at first it comes a letter comes, then next to that it can be either letter or a digit. We are unionizing these two. As you see here, we have the letter and the digit, and they are in the asterisk, meaning that they can be iterated as we want. And this is the rule. In identifier, the first character that comes must be a letter, and next to that it can be a digit or a letter. And this is how we represent it in regular expression. First we have the letter, then the letter or a digit, and we are unionizing it, letter and digits, then we are iterating it, because we don't know how much the iteration is going to be. And the next one is the white space. The white space includes the empty space, the new line, the tab, and so on. So this is how it is represented. we have the empty quotation here, union u plus, meaning that the union, and then the new line, then the tab, and all of these three are unionized. As you see here, they all three are unionized. And at the top you have this plus sign, meaning that they have the iteration that it's going on. And let's see it in other examples. For example, let's see it as in the set of regular expressions. First, let's say we have 0, 1, 2, 3, 4. And to represent it in regular expression, this one, the value is going to be R union. Okay, the regular expression is going to be 0 union 1 union 2 union 3 union 4. I mean, there is no other value that's going to come other than these values. And the next one is empty set and x and y, xy. And the value is going to be like this. If it is an empty set, we don't have to add a union because it can work like this also, the regular expression. And the third one we have here is xy, xx, yy, and xxy. The regular expression of this set is going to be like this: xy union xx union yy union xxy. Remember that the plus sign represents the union, not plus. And here at lat we have a value that's continuing and it is iterating. As you see, first we have 1, next we have 1 1, then 1 1 1, and it continues. And the value is going to be like this: r1 plus. This is how it's going to look like. And next, if we have another example, for example, let's say we have this phone number. What's going to be the regular expression for this? Because as we see here, we have integers here, and also we have the operators, the plus and the minus sign, and also white spaces here. So how do we represent this regular expression? The answer is like this: digits, or plus, we can change this one with the plus sign, digits union all these operators and empty space. This is how we express the regular this is how we show the regular expression of our phone number. Try this with other numbers, digits, or any token that you think of. Give the regular expression for the following. The first one is a sentence: I like dancing. The next one is a mathematical expression: int x is equal to 10. Based on the principles of regular expression, when we change these two given strings, we get, for the first one, we get character union white space. As you see here, we have characters, or a string that is including only characters. So we can represent it that it is a subset of the characters from A to Z, union with the white spaces. As you see, there is a white space between all the words. When you come to the second one, for the given equation that we have, the regular expression is going to be like this. First, we have the keyword. Int is a given keyword, so we are going to write it like this: union with an identifier. X here is not we are not going to say it's a character, rather it's an identifier. So we are going to write an identifier, union with the digits, because 10 here 1 0 is the digit, and union with the given equal sign. Hello everyone. Next, Let's see the finite automata or finite automation. What is finite automata? It is a simple idealized machine used to recognize patterns within the input taken from the same character set. The job of the finite automata is to accept or reject an input depending on whether the pattern defined by the FA occurs in the input. We can call it, as I told you, finite automation, or also we can call it finite state machine. It is a computational model that consists of finite states, a set of transitions between these states, and an initial state, also a set of accepting or final state. So the goal of this finite automata is it is a transition table which recognize or which acts as a recognizer, and it simply says yes or no about each possible input string. So if you say that it is like a transition table, it consists some things. The first one is an input alphabet or sigma, and this is a set of input symbols known as the alphabets determine the valid inputs that can trigger state transitions. The next one is a set of states. After that, it contains also a starter state. Next, a set of accepting states, and at the end, a set of transitions. Don't worry, we are going to look at each of them next. Here we have the diagrams for the finite automata. The first one is the states, and it is represented as a sheet at a circle, and these states are a finite set of distinct patterns represents a different configurations or conditions in which the automation can exist, and it is represented by a circle. And the next one is a starter state or initial state. The starting point of the automation, it is a starting point of the automation denoting the state from which the computation begins. And after that, and it is represented by a circle with the arrow pointing to it. Next, we have an accepting state. A state or subset of states designated as an accepting state indicate the successful completion of a computation or the recognition of a specific pattern. They are they indicate successful completion of computation or specific completion of specific pattern, and they are shown like these concentric circles, two circles like this. And at the end we have the transition, and the transition is defined the movement of one state to another in response to an input symbols. Each transition is associated with a specific input symbol or set of symbols. So this is how we are going to design the finite automata using all these diagrams. First we have the states, we have the starter state and accepting state also. And for the transition, we have these arrows that points from one state to another state. And because of this input that we have, or letter A for now, so this is how the finite automata is represented in transition diagrams. When we see the transitions, as I say it now, the transition from S1 to S2 appears because of an input A. So in state S1, when input A appears, then it transforms to S2. This is the transition. If the input is an accepting state, it accepts, or it is going to be represented by the concentric circle. Otherwise, it is rejected. Now, for example, let's look at simple input that contains some things. It says that a finite state automata accepting any numbers of ones followed by a single zero. So what could be this number? It could be 10, it could be 100, 1000, or 1010, something like that. But what say that a finite state automata accepting any number of ones followed by single zero. So it could be 110, 11110, and so on. All of this can be used for this question because they have number followed by a single zero, any number of ones. So how do we design the finite automata from this? So this is how it's going to look like. This is how the finite state automata for this question is going to be like. At first, we have the starting point, a circle that is with an arrow pointing to it, and next to that we have a any number of ones that are followed by a single zero. So whenever ones are included to the state, it's going to return back to it. As you see, any number of ones, whether we use multiple ones or single one, it's going to be stated in state 1. When at the end, when a single digit 0 appears, it's going to finish, or it's going to go to the accepting state. This is how it's represented in the finite automata. We are going to look this in many ways later, but now let's jump to the next topic. Next to that, we have an epsilon move. This epsilon move is any kind of transition with an e move, and this is represented by the graph as you see it. In finite automata theory, an epsilon move is a special type of transition that allows automation to move from one state to another without consuming any input symbol. So, in finite state automata, especially machines can move from state A to state B without reading an input. And they don't need input consumptions, just like the before one. They don't need an input or a letter or a digit to move from this state to the next state. In the previous example, we have seen that the transition occurs when a zero appears. But during the epsilon move, we don't require any input. We can just jump from one state to the another. And epsilon moves are particularly useful in non-deterministic finite automatas, or NFS, where a state may have multiple transitions from same input symbol or no transition at all. So epsilon moves transition help more additional possibilities. We are going to see about the non-deterministic finite automata later, but let's look at it, and it's represented by this epsilon icon. That's it. Finite automata come in two flavors. The first one is deterministic finite automata. The next one is non-deterministic finite automata. When you look at them, the first one, or deterministic finite automata, have for each state and for each symbol of its inputable alphabet exactly one edge with that symbol, leaving that state. And for non-deterministic, it has no restrictions on the labels of their edge. A symbol can label several edges out of the same state, and E, or an empty string or an epsilon. So the difference is listed here. The first one is for deterministic, it has for every state exactly one living edge with a given non-empty input. So one input can represent only one living edge. And it has one transition input per state and no epsilon move. And it is completely determined by the input. For non-deterministic, a finite automata, it has no restrictions on the label of their edges. A state can label several edges out of the same state, and epsilon move or e move is possible. And machine can choose whether to make an e move, which of multiple transitions of a single input take. So in non-deterministic finite automata, epsilon moves are often used to model non-deterministic behavior, allowing for multiple possible transitions or paths from one state to another without consuming an input. They provide a more flexible way to express certain language patterns. And it is important to note that the epsilon moves are not used in deterministic finite automata, or the first one, DFA, as DFAs have a unique transition for each input symbol. Epsilon transitions are more prevalent in the context of NFA, and certain algorithms for automata manipulation and conversion. So when you see it in the graph, this is how it looks for NFA and DFA. Non-deterministic finite automata, as you see it, the graph looks like this. And for an input 0, it could stay like right there, or it could transit from one state to the another one, as you see it here. But in deterministic finite automata, that's not appearing. For one input, there is only one transition in one state. So, in conclusion, in DFA, for each state and input symbol, there is exactly one transition to next state. The behavior is fully determined, providing a unique path for each input. While for non-deterministic finite automata, it allows multiple transitions from state with the same input symbol, providing a unique path. They offer more flexibility but may require additional mechanisms for handling ambiguity. Because as you see, if you are working on non-deterministic finite automata, the using one input, you can stay in the state also. You can jump to another transition, another state. You don't know the for sure what to do with non-deterministic finite automata. So it may lead to ambiguity. Now, next, let's see the regular expressions in diagram or in finite automata. So these are the basic principles while building finite automata. We have to change the regular expressions that we have done before to a finite automata or a diagram. So this is how it looks. For each kind of regular expression, we have to define the NFA notation. For epsilon move, we are going to show it like this. We are going to have a transition of epsilon transition, and for normal input, we are going to have a state, a starting state and an end state, and the input is going to appear like this. We are going to show the diagram like this. And for concatenation, we have talked about concatenation in regular expression before. This is how it's going to appear. We have A and B. A could be another expression like 1 plus 2, 1, 2, or any other thing, or single digit also, or alphabet also. We are going to jump using an epsilon move to B. This is how we represent the concatenation of regular expression in finite automata. Remember to look at all of them. And next, we have the union. A union B is represented like this in transition diagram. We are using this big symbol here because we don't know for sure that A could be like another function inside in the union. It could be a single digit letter number, or it could be another function. So that's why we are showing it like this. And using this epsilon move, we jump to each of them. Then using epsilon move, we go to the end state. And for the iteration, this is how it's going to appear. Here we are using letter A. If it is a single digit, we can probably show it like in a single digit, but we don't know the substantials. That's why we are showing it like here. So this is going to have an epsilon move to the starting or an epsilon move to the end also. And this is the basic principle. Remember to look at these principles because next we are going to work on some examples using this by changing regular expressions to finite automata. Now, based on the previous principles, let's work these examples. Perform the following for the regular expression to non-deterministic finite automata. So the first question is, we have the number 1. What do we do for a single digit while transitioning? Well, the first thing is to create the starting point from there, or from there we proceed to the transition. So we first do the initial state like this. We represent it, the state, for example, by randomly a. Then we proceed to the transition. The transition is the digit or the input. So this is how it looks. And this is the accepting instinct. This is how we represent the regular expression 1 to non-deterministic finite automata. Next we have the B3. This is 2 digits and it's an identifier because the a character is coming first and digit is coming second. That's how identifiers are written. So how do we represent this regular expression to non-deterministic finite automata? Okay, the first thing is we have to remember the principle that we used before, which is for the concatenation. In the concatenation, we have said that for regular expression to change it to non-deterministic, we use this principle. Well, this is one system A, and by epsilon move by epsilon transition, we move to system B. This could be another function, so let's hold on this principle. So for B3, what we are going to do is first create the starting point. Done. For the B, we use the transition B. Remember, this B is for the digits and these are for the states, and these are the inputs. So first we create the non-deterministic finite automata for the single digits. Then using the epsilon move, we create this non-deterministic finite automata. And remember also to add the accepting state. This is how we represent the concatenation for a B3. Next we have the union, which is 5 plus q. And for the new union, we have said that in the principle it's going to be like this. This is one system and the below is another system. And by using the epsilon move, we jump to these systems. Then this is how we represent it using finite automata. So what we are going to do is first, let's separate it for the 5 and for the q and create their system. So this is how we represent it. Meaning that if we remove the left ones, these epsilons, and the right ones, these epsilons, this one is one system or one finite automata. And also this one from D to E. This is one transition, and we are creating that transition for the Q only, then for the 5 also. And after that, we are going to union both of them using this transformation. Next to this, we have a little bit harder one, which is A5Q2. And we are using union, and also we are using concatenation if you look them. So how do we do that? The first thing is, first let's do the single digits finite automata. Then we go to the concatenation. And for the concatenation, this is how we represent them. Because we have said earlier, this is how we are going to represent them. For the A5, first we transition from B to C using digit A, then by epsilon move we concatenate it with 5, and 5 is the transition also from D to A, and we repeat that one for the Q2 also here. And after that we union it using the principle from the finite automata like this, and we have the starting point, and by epsilon move we jump to the two systems. Here we can say that this is one system and another is another system, the Q2 is another system, and we can represent it just like the previous one as a single circle here, and for also for the single circle for the Q2 also. This is how we represent it. And at last we have this example which includes the union, also iteration plus concatenation. So how do we do this? Try to work all the examples on the raw paper. So what we are going to do is first simplify it. First, let's do the union. After that, after we draw the union diagram, then we iterate it using the principle. And after that, after the iteration, we concatenate it with the number one using the epsilon move. So this is how it's going to look like. First, we have the starting point, and we first are going to create the union diagram. So for 1 plus 0, we have here one system, which is a union system of finite automata. Here, then we added the iteration for this union, and this is how we add from the ending point to the starting point by moving using the epsilon move, and also from the starting point to the end using epsilon move by transitioning them. And remember, we are working on non-deterministic finite automata because, as I told you, only in the epsilon is used only in the non-deterministic finite automata. So this is how it looks, and at the end, by using the epsilon move, we concatenate it with the number one that we have here. So try to practice all these examples by writing them on the paper, because it is essential to know that this diagram, this is the basic principle in finite automata. Now, let's see the transition tables. Previously, we have seen the transition diagrams. So, what is transition tables? Transition tables are just like the transition diagrams. They show the finite automata, but in different form or in a table form. Before jumping to the transition tables, let's see these 5 tuples that rules the transition table. The first one is the Q, or the set of all the states. The next one is the sigma, or the set of all the inputs. And after that we have Q naught, which is the initial state, and F is the final state, or the ascertained state. Next to that we have delta, which is the transition function from the Q, and this transition function must be from the set of all states and all the inputs. So let's see the graph, how it looks. For example, let's say we have this transition diagram, and as you see, it has many transitions, and it has 3 states, Q1, Q2, Q3, and some of them are the transition are inside, meaning that For example, in Q1 or in the starting point, we have 0. When input 0 is on the Q1 or on the state 1, it's going to be returned back to the Q1. This is how it looks. Other than that, the rest is the same. For example, in the Q2, when the input is 1, it is going to be returned to Q2 I mean. And also for the Q3, when the input is 2, it's going to be returned to Q3. So this is how it looks. We have the starting point and the accepting state. So how do we represent this one? The thing is, first, let's pick out the values. As you said, first, we have the states or the queue, and how many states that we have? 3 states, Q1, Q2, Q3. Next to that, we have the inputs, and we have 3 inputs, 0, 1, and 2. And our initial state is Q1, and the accepting state is Q2. And these are the transition states that we have, or the transition functions that we have. The first one is from the Q1, when we are in the Q1, and when the input is 0, we are going to get the Q1 value. It is going to be returned. Also the next function, let's see the next function, and it says that on the Q1, when the input is 1, we are going to go to Q2 or Q2 here. And on the Q1, when the input is 2, we are going to go to Q3. From Q2, when the input is 2 here, this transition, we are going to go to Q3. And the rest goes on. This is how we represent the transition function from the diagram. By directly looking at the diagram, you can make these transition functions. Next, let's see the table. This is how it looks, the transition table. In the left side, we have the states, and at the top, you have the inputs written. And to represent the initial and starting points, I have make the arrow and the circle on the initial and the starting point here. And this is how we cross them. And this left side is going to be represented at the present state, and these are the features. We can say that the next steps, we can represent them as the next steps, because currently we are in the Q1. When the input is 0, we are going to go to the Q1, or we are going to stay on the Q1. While on the Q1, if the input is 1, we are going to go to the Q2. So this is how it works, and the rest goes on. For the Q2, if the input is Q1, we are going to go to the Q1. This is the diagram as you see it. And if the value is 1, or the input is 1, we are going to stay on the Q2. This is the simple transition diagram that I created. You can also practice it on the previous diagrams. So this is how we represent the transition tables. These transition functions tell the automation how to move from one state to another based on the current state and the input symbol. Next, let's see the acceptability of string by deterministic finite automata. Let's say that we have this transition table. We can clearly, from the previous note, we can clearly now point out the transition functions. Also, we can draw the transition diagram. So, if you want to create the transition function, the first one would be q not 0 with the value of q0, and the rest goes on. Our starting point from here, we can pick it is q0, and the accepting state is q1. These are all our values. For q0, when the input is 0, we are going to stay on the q0. when the input is 1, we are going to jump into the Q1 state. And on the Q1, it goes on. So when we draw the transition diagram, it's going to look like this. This is Q0 and Q1. I forgot to draw the starting point here, the initial diagram or the arrow that represents the Q node, but there should be here. This is how it looks. And the accepting state is the Q1. So let's say we have a string that is consisting of zeros and ones. And let's say if we want to check using this transition function, if it is accepted or not. For example, let's pick these three strings. The first one is 1010, and the next one is 0011, and the third is here. That these all three are going to be accepted using the DFA or this transition function. Let's see. The first one is 1010. The first letter is 1. So currently we are the starting point is Q0. So on the Q0, when the integer is 1, we're going to jump into Q1. Or when the transition is 1, we're going to go to that Q1. And on the Q1, the transition state is when the input is 0, we are going to stay on the Q1. Next, we have the number 1, which makes a jump to the starting point or the other state or Q0. And the last one is 0. 0 means it's going to stay here, right? Because when on the Q0, when the integer is 0, it's going to return back to Q0. So this string is going to be rejected because, as we have said, the last digit or the last number is going to be on the Q node, which is not on the ending or the accepting state. So it's going to be rejected. Next, let's see the next string, which is 0011. 0011 is going to start from here, from the starting point. Since the digits are going to be 00, it's going to be hold like it is going to be on here for the first two digits, and for the third, it's going to transition to the Q1. Next to that, the fourth digit is going to make it return back to the Q node. So this is going to be also rejected. When we go to the fourth one, when we look at it, it's going to say 1 1. So it's going to go to Q1 state, then return back to Q node. Then it's going to stay on the Q node for the true numbers. Then it's going to go to Q1 and return back again, then Q node. So this is also is going to be rejected. Now let's see another strings. For example, this one, when you look at it, it says 0 0. First, it's going to the transitions are on the Q node only. Then it's going to jump to Q1 when the number 1 appears, then return back. And for the third number, it's going to go to the accepting state. So this is going to be accepted. When you see the last one, it says 1 1. First, it jumps to the Q1 state, then returns back, then 0 0. Then it goes back again with this one digit. Then at the end, it says 0. So in the Q1, it's going to stay on the Q1. So this is going to be accepted by the DFA. So this is how we look at if the string is acceptable by DFA or deterministic finite automata or not.
Hello everyone.
Now that we have seen the acceptability of DFA or deterministic finite automata, now let's change the non-deterministic finite automata to deterministic finite automata. So without further ado, let's jump into it. Here we have a NFA or non-deterministic finite automata. As you see this transition diagram, there are a couple of things that makes this diagram an NFA. The first thing is, for example, in state A, using the integer 1, it can jump to another transition. It can transit to state B or it can stay on state A. Also, if you see that on state C, from the using the integer 2, it can jump to state B or state A. So it's very ambiguous, so it's non-deterministic finite automata. Plus it has a dead zone or a trap. What's a dead zone or a trap is for an integer or for a value when, for example, if you take C for a value of 1, it doesn't have any value, it doesn't have any transition, so it's going to be a dead zone or a trap for integer 1. When we create the transition table for it, this is how it looks. For state A, or when integer 1 appears, it can go to, it can stay on state A or it can go to state B. So for integer 2 on state A, it can transit to state C. And also for B, it works like that. And for the C, as you see here, we have a blank space, or we can call it this one a trap or a dead zone. So this is a non-deterministic finite automata. So how do we change this non-deterministic finite automata to DFA or deterministic one? So the thing is, we are going to recognize these two values into one. For example, in the first one, in AB, we are going to consider AB as a one state. So let's create the diagram first, or the transition table. So this is how it looks. At first, we have the state A, right? So for in the state A, using the integer A, integer 1, it's going to jump to state AB. We are going to create a state named AB here. And in state 2, I mean in using integer 2, it can jump to C. So now next what we are going to do is we are going to create a new state named AB. So we are going to write it here on the left side. So we have now an integer AB and I mean a state AB. So from this AB, what we are going to do is when integer 1 appears, we are going to take the union of A and B because this is AB. So for integer 1, when we union A and B, there is common A here. So we are going to take only one of them, then we are going to pick B. So this is how it looks. When on state AB, when number 1 appears, it's going to stay on there. And for integers 2, when we take the union of A and B, it's going to be B and C. So we have now any other states besides AB. So we are going to create a state named BC again. So we have now another state named BC. So from BC, using integer 1, we have only one value, which is A. So we are going to pick that one, A. And from BC, using integer 2, we can jump to B union C, which is AB. Next, we have the value of C. So when we give it the value on the C, previously we have a dead zone or a trap here, so it was an empty state. But now we don't, in DFA, it's not allowed to have a trap or dead zone, so we are going to name a new state, and I'm naming it D. So using integer 1, we are going to jump to state D. And from state C, using 2, we can jump to AB because this was earlier before. Now we have AB. Next, we have state D. So for the test D, whether we are using integer 1 or 2, it's going to be returned back to itself. So it's going to be DD. So there is no new state that's appearing here, so everything is working fine. So let's see how to draw this diagram or transition diagram. The first thing that we have to create is the starting point, which is this one, A, and the accepting point ones are, previously it was only C here as you see in the diagram, but now it's going to be a state that includes C. So we are going to have two accepting states here. Let's draw the diagram. First, we have the starting point A. From A, using 1, we are going to go to AB, and using 2, we are going to go to C. This is how it looks. And next we have AB, state AB. From state AB using 1, it's going to return it to back to itself. And using integer 2, it's going to go to state BC. This is how it looks. BC is our accepting state. That's why it's concentric circle. Now for the BC, we have the value of here for integer 1, A, and for integer 2, we have AB. This is how it looks. And for the C, this is how it looks. For integer 1, it's going to transit to D, state D, and for integer 2, it's going to have a transition to AB. And for the last one, D, which is the last state, and it's going to have a return on transition. And this is how we change the NFA to DFA. Perform the following transition from regular expression to NFA, or non-deterministic finite automata. The first one is in bracket 3a plus or union 5f, and in iteration concatenated with 2. The second one is 3 into open bracket a union b, then with iteration. To answer these questions, what we have to do is, based on the given principle that we have seen earlier, we have to divide this equation to small strings and perform the NFA. Then as a whole, we are going to perform it. So what we have to do is, first we have to see the concatenation between 3a and 5f. Then we are going to unionize it, and by using this iteration, and at the end we are going to concatenate it with 2. So we are going to start by small and perform the NFA diagram. So the answer is going to be looking like this. We have the 3a concatenation, and by an epsilon move, we can find this transition for the 3a. Also for the 5f, it's going to be like this. And when we unionize it, it's going to look like this circle. And after that, we are going to add the iteration or these times here. So it's going to add an epsilon move to the back and also an epsilon move to the front like this. After that, we are going to concatenate these two. So this is how it's going to look like. This is the NFA diagram or the non-deterministic finite automata diagram. Also, if you look for the second location, this is going to be the diagram that we have for the NFA. First, you are going to create the A union B. Then you are going to add the iteration to the A union B, then concatenate it with 3, like this. Create the transition table for the transition diagram shown below. Show all the necessary steps. While doing this table, don't forget to pick out all the 5 tuples and also show the transition function. Later then work on the transition diagram. To answer this question, first we have to select the given variables that we have from this diagram. So when we select the inputs that we have, the states that we have, and the transition table, the transition equations that we have, it's going to be a lot easier. So this is the first, we have the all the states that we have, A, B, C, D, E are all these the states. And from here that we can see that our inputs are the small a and b in all transitions, and our Q naught or our starting is going to be a, and our the finishing state is going to be e. So when we select when you see the transitions from a using an input a, we are going to transit to state b, and from a, also from state a, we can transit to C using the input B. So while doing these transitions for all the states, we can find a lot of transitions here. So based on that, we are going to build our given table. So this is how it's going to look like. Our starting state is going to have an arrow here, and our ending is going to have a circle on it. So this is how it looks. From state A, using an input A, we can go to state B. And using state input B, we can go to state C. And as you look here, this is the answer for the transition table for this diagram. Convert the following NFA to DFA, or non-deterministic finite automata to deterministic finite automata. Show all the necessary steps, like first pointing out the transition function, then doing the diagram, and so on. To convert this NFA to the DFA, what we have to do is first we have to create the NFA table for the given diagram. Then from that we are going to change it to the DFA. So when you create the NFA for this diagram, it's going to look like this. Using from A, using an input 0, you can be in the state A or in state B. And also using the input 1, you can be on state 1 again. And on B and the C, you can clearly see that for some inputs, there are no transitions happening. So this is on NFA, so we are going to change this to DFA. So how do we change it? The answer is by removing these ambiguous transitions. For example, for the zero transitions, we have the state from A, we can transit to state B or stay on state A. So we have to remove that. So we have to create another state by merging these given states. For state A, we can go to AB. we are going to merge AB and create a new state that's called AB here. And for input 1, we can stay on state A. And on the B, we are going to create a new state that's called D, which is going to be a new state. And for both the inputs, we are going to return back to itself. It's going to be a null state that we have, and we are going to use it on C also. And from this AB, we have, as I said, we have new state. And when we go to using an input 0, what we are going to see is you can select the transitions of A and B. A and B. So we are going to go to a new state called ABD. So for this ABD also, we are going to create a new transition. And for this ABD, we are going to get new values, new states for the AB, for the AC. We are going to perform these transitions for all of the values. And at the end, we are going to circle all the values that have the state C inside them. So we have the finishing states on C, AC, and ACD, but we have only the one starting state. Hello everyone. In this section, we are going to see about syntax analysis or a parser. So, without further ado, let's jump into it. So, we can call that syntax analyzer as the parser. So, what is the role of parser? Syntax analysis is a fundamental phase in compilation process that ensures the syntactic correctness of the source code and produces a hierarchical representation, which is essential for subsequent stages of compilation. As you see here, we have the diagram that shows the lexical analyzer and the syntax analyzer. Syntax analysis along with lexical analysis is considered part of the front-end compiler. The front-end is responsible for processing the source code and creating an intermediate representation. Syntax analysis is also known as a parser. It is a crucial phase in compilation process of programming language. It involves analyzing the syntactic structure of the source code to ensure that it conforms the specified grammar rules of the programming language. The primary goal of the syntax analysis is to create a hierarchical representation of the code, typically in the form of parse tree or an abstract syntax tree, which serves as an intermediate representation of the subsequent compiler phase. So from the graph, you can see that after the syntax analyzer get the token streams from the lexical analyzer, with the help of context-free grammars, it changes to the token stream or the parse tree that is readable for the next stage. So the core activity of syntax analysis is parsing, where the subsequent of token is analyzed to determine if it adheres to the grammar rules. Parsing involves recognizing the syntactic constructs of the language and organizing them hierarchically. Common parsing techniques include recursive descent parsing, LR parsing, and LL parsing. We are going to look at these parsing techniques later. So, a parser is a program that analyzes the syntactic structure of the source code according to the rules defined by the programming language or grammar. And it uses the context-free grammar, as we have seen earlier. And context-free grammars are formalisms for describing the syntactic structure of language. Syntactic analysis begins with a formal definition of the programming language grammar. The grammar outlines the rules that specify how valid a program in language should be structured. So, in the parser, there are a couple of things that are going to be done. The first one is error detection and reporting. Syntax analysis includes mechanisms for detecting and reporting syntax errors in the source code. When an error is encountered, the parser generates an appropriate error message, aiding developers in identifying the fixed issue. And the next one is ambiguity resolution. Some grammars may be ambiguous, leading to multiple valid parse trees for a given input. Syntax analysis may involve techniques for resolving ambiguity to ensure a unique interpretation of the code. So, beside delivering the parse trees, the syntax analysis also work in error detection and reporting, plus ambiguity resolution. So, now for specifying syntax, we present a widely used notation called a context-free grammar. Context-free grammars are formalisms for describing the syntactic structure of language. They can define context-free language, which includes more complex and hierarchical structures. So, as you see here, in context-free grammars, the advantages are hierarchical language structures. The first one is programming languages often have a complex hierarchical structures that cannot be fully captured by regular expressions. So CFGs or context-free grammars provide a higher level of abstraction, allowing for the definition of nested and recursive constructs. They naturally handle hierarchical structure of programming languages such as nested blocks and recursive function calls. The next one is readability and maintainability. CFGs or context-free grammars offer a more readable and maintainable way to describe a syntax of a programming language. They can capture the hierarchical relationship between language constructs, making the grammar more intuitive and for human understanding. So that we can call them that they are very expressive. CFGs can express a wider range of syntactic structures, including nesting and recursive patterns, as we have said earlier. The next one is parsing full language structures. While regular expressions are excellent for tokenizing and recognizing simple patterns, they fall short when it comes to parsing the overall structure of a program. CFGs are essential for more advanced stage of parsing that involves understanding the full syntax of structure of the source code. That's why we are using CFGs instead of regular expression in syntax trees. And at the last, the CFGs are essential for support for ambiguity and ambiguity resolutions. CFGs can handle ambiguity in language definition, and techniques such as leftmost or rightmost derivation and parsing trees can be employed to resolve ambiguities. This flexibility is crucial in designing languages that are both expressive and unambiguous. So, let's see what the CFGs are composed of. A context-free grammar consists of terminals, non-terminals, a start symbol, and production. So, first let's see terminals. Terminals are basic symbols for which strings are formed. The term token name is synonym for terminal and frequently will be used in words like token for terminal when it's clear that we are talking about just the token name. We assume that the terminals are the first components of the token output by the lexical analyzer. So we call them here terminals. Next we have non-terminals. These are syntactic variables that denote set of strings. The set of strings denoted by non-terminals help define a language generated by the grammar. Non-terminals impose a hierarchical structure of language that is key to syntax analysis and transition. So these non-terminals are statements and expressions, while terminals are tokens coming from the Lexer. So the third one is production. Phrase structures rules specifying the manner in which terminals and non-terminals can be combined to form strings, and they define the rule of the language. The production of a grammar specifies the manner in which the terminal and non-terminal can be combined to form strings. And at the last, we have the start symbol. The top level phrase, from here the production begins, is the start symbol. It determines which non-terminal represents the language as a whole. In a grammar, one non-terminal is distinguished as a start symbol, and a set of strings is denoted in the language generated by the grammar. Conventionally, the production of the start symbol are listed first. So let's see an example. Here we have a context-free grammar. So let's pick out the terminal, non-terminal, and the productions from here. So as we said that first, the terminals are the terminals that symbols and characters that came from the token, or their tokens. So from here, we can clearly know that this is the terminal, the plus sign. Next here, the times, and also the T, and open bracket, close bracket, and N. These are all tokens. So they are terminals. So the next one is, let's pick the non-terminals. From here we can know that the non-terminals are the expressions. So these are non-terminals that are shown in the capital letter. Next, let's see the production. So the production is the whole statement, or the form of the string. This is the whole production that we have now. At the whole, the string is going to be said as the production. So this is one production, one production, one production, and all. And the start is going to be by default the first string that comes. So let's see the national conventions. To avoid always having to state that these are terminals, these are non-terminals, and so on, some of notational conventions are made. The first one is, what are terminals? And terminals are represented in lowercase letters early in alphabets, such as the small letter A, B, C, or things like that. Here we have T, and so on. And operator symbols such as plus sign, times, and so on, other operators, are going to be the terminals. Punctuation symbols such as parentheses, comma, and so on are also terminals. Boldface strings such as ID or if, which represents a single terminal symbol. And this kind of, for example, if you say ID or something like that, they are going to be terminals. And when you see that non-terminals, they are uppercase letters early in the alphabet. So here we have E, T, F. These are uppercase letters and they are non-terminals. The letter S, which it happens, it usually is the start symbol when it appears. Currently we don't have it, so this is the start symbol. But by default, most of the time we use the capital letter S. Lowercase italic names such as export or statement, they could be the non-terminals, but we don't see them most often. When discussing programming constructs, uppercase letters may be used to represent non-terminals for the construct. The uppercase letters are, as we said, terminals, and the lowercase are non-terminals. Unless stated otherwise, the head of the first production is the start symbol, or this one. Now, let's see how to parse a given statement. So, during parsing, we take two decisions for an input. First, we have to decide the non-terminal which is to be replaced, and next, we have to decide the production rule by which the non-terminal will be replaced. To decide which non-terminal to be replaced with production rule, we can have two options. The first one is leftmost derivation and the next one is rightmost derivation. And to decide the production rule by which the non-terminal will be replaced, we have two rules. The first one is bottom-up parsing and the next one is top-down parsing. Don't worry, we are going to look at each of them next. So first, let's see the production rules or derivations. The construction of a parse tree can be made precise by taking a derivational view, in which the production are treated as a rewriting rules. Beginning with the star symbol, each rewriting step replaces a non-terminal by the body of its own production. So, a derivation is basically a sequence of production rules in order to get the input string. So we have two types of derivation. The first one is leftmost, the next one is rightmost. In the leftmost, input is scanned and replaced from the left to the right, while in the rightmost, we scan and replace the input with the production rule from right to the left, which is refers to the leftmost one. So for example, let's say we have an input string or a token that comes from the lexical analyzer like this: ID, union ID, and times ID. And our grammar is going to be like this, or our CFG is like this. So we could have two kinds of derivation, the rightmost and leftmost. So this is how it looks for the leftmost and the rightmost. First we pick the start symbol. Here we choose the second CFG here, E is equal to E times E. And then we are going to change the leftmost one rather than the right one in changing. So we are going to change this E, the first E, by the first grammar that we have here. And next, after that, we are going to change the left one again. Here we have the E, so we are going to change it with the third grammar that we have by ID. After we change that, we are going to go to the leftmost one next to that, which is the second ID that we have. After that, we are going to go to the third one or the last one. This is called the leftmost derivation. In the rightmost derivation, first we pick the first grammar, and then we are going to start changing the grammar by the input string from the rightmost side. We are going to change this E or this non-terminal by the other production or by the second production. After that, we are going to change it to the terminal from the right side. We are going to change the last one first, then after that we are going to change the second one, and so on. This is the difference between the leftmost derivation and the rightmost derivation. Let's see the parse tree. We have been saying that from the CFGs that we have, we are going to create the parse tree. So what is a parse tree? A parse tree is a graphical depiction of the derivation. It is convenient to see how strings are derived from the start symbol. And the start symbol of the derivation becomes the root of the parse tree. It's going to be at the top side. And it contains terminals at the leaves. And also it contains non-terminals at the interrail nodes. And in order to traversal of the leaves is going to be original input. Parse tree shows the association of operations. The input string doesn't. So let's see the example, the parse tree. Let's say we have this token and we are going to use the leftmost derivation. And we have the grammar here. Within this grammar, we are going to change this token to the parse. So we pick the second grammar. Then using the left derivation, we are going to change this non-terminal and so on using the leftmost derivation. And the grammar is going to look like this. At the root, we have the non-terminal at the root, or the start symbol. This is the start symbol. And as we said, the terminals are going to be at the leaves, and these are the leaves of the parse tree. And the nodes are going to be non-terminals, as you see them. These are the nodes, and they are non-terminals. This is how we create the parse tree. While doing so, a grammar is ambiguous if it has more than one parse tree for some string. Ambiguity is bad because it leaves meaning of some program not well defined. And also, it might result in an unintended result. We can create for some grammars 2 or more parse trees. For example, let's see this grammar that we have. These are the grammars that we have. If you don't know what this means, this is the giving the next grammar. We have here 1 grammar, 2 grammar, 3, and 4. We have 4 grammars. We can represent it by E, means E times E down here below, but also we can represent it like this. So let's say we have the input string like this, int times int plus int. If we draw the parse tree for this, we could have these two parse trees. Using both of them, you can represent this input string. So it may cause an ambiguity while working on these issues. So what we have to do is we have to put the constraint in order to work on this, or we have to change we have to change the grammar of the code. If you see this example also, it could have an ambiguity because we can create more than one parse tree. For this, we have the grammar E plus E, E minus E, and is also an ID. For this input string, we can create this parse tree. These are the star symbols. As I said, these are non-terminals, and at the leaf we have the terminals. If we create this parse trees, you can see that it is very ambiguous. You can create this, also this one. So the solution is either rewriting the whole grammar without ambiguity by changing the grammar, or by setting and following associativity and precedence constraints. No method can detect and remove ambiguity automatically, but using these two, we can remove the ambiguity, rewriting the whole grammar, changing the grammar, or by setting following associativity and precedence constraints, by setting the constraints on it. For example, this grammar, as you said, we have seen it earlier, is very ambiguous. It has 4 grammars, so we have seen the example using the example that this is ambiguous grammar. So we can change it to another grammar by adding another non-terminals, and we are going to see how to change this one also later, so don't worry about it. But the first one is changing the whole grammar or putting the precedence constraints on it. Okay, we have seen the parse trees, but there is one thing that causes an issue while doing the parse tree, which is left recursion. Left recursion is a situation that occurs in context-free grammars, when a non-terminal can derive itself directly or indirectly from the left side of the production rule. Left recursion can pose challenges for certain parsing techniques, particularly top-down parsers like recursive descent parsers, as it can lead an infinite recursion during parsing. To avoid left recursion, grammars are often modified or transformed. So as you said that it could cause an issue in top-down parser. We are going to look at it about top-down parser later, but the general schema of top-down parser is by creating the root first and designing the parse tree from top to the bottom. While doing that, this left recursion can happen, and a grammar becomes left recursive if it has a non-terminal a whose derivatives contains a itself at the leftmost symbol. For example, let's see this symbol. This grammar has its own non-terminal at first sight, meaning that when we represent this a using this, it could have like an infinite loop or an infinite recursions to the bottom, because at first we have the in the left side we have itself as a non-terminal. So while changing the variables with the tokens or the terminals, the non-terminal is going to go to the non-stop down below. So the disadvantage of left recursion is that it will create an infinite loop in top-down parser. So it has its own solutions. The solution is that changing this grammar to this kind of form. Let's say we have this kind of grammar first, which is left recursive, and we have to change the structure of this grammar to this style. This a prime is a different value or a different non-terminal besides the a. Here we have the non-terminal. This is a new non-terminal that we are going to create. So by changing this grammar to this form, we can remove the left recursions. So, for example, consider a context-free grammar of expression with addition or multiplication. And it could have here, as you see it, E represents the expression T, and a T represents the expression here, and also T represents terms, and F represents factors. The grammar allows for addition or plus sign and multiplication, parentheses, and identifiers. However, this grammar contains left recursion in the production rule of nt. You can see that the non-terminal nt appears on the left side of the respective production rules, potentially the leading to left recursion or issue during the parsing. So as you say that we have seen how to remove the left recursion, the grammar can be transformed to new grammar, and the idea is to replace the left recursive rules with equivalent right recursive rules. The modified grammars would be different. So as you see, this one, the E and also the T grammar are contains right themselves in the leftmost side. So this causes a recursion. So we have to change it. For example, if you use this parse, if you want to parse this token, it could have a left recursion. So to change this, we have to implement the code that we have seen earlier. We have to change this form, we have to change this grammar to this form. So if we change this E, the first grammar, it could be a little bit different from this one. This is how it looks. So if we change it like this one is going to be changed to two grammars, this and this, as you see here. And the second one is also going to be changed to two grammars, the third and the fourth one here, as you see it. By using the rule, we can change it now. So using this this grammar, we can parse this token like this. First, we pick the symbol first, or the first grammar, and using the leftmost derivation, we can start parsing the tree, and this is how it's going to look like. And okay, so in this modified grammar, before jumping there, the left recursion has been eliminated by introducing a new non-terminals, E prime and T prime. the production rule have been adjusted to create right recursive alternatives. An epsilon is used to represent the possibility of an empty string here, or here. So when you see the parsing with the modified grammar, parsing can be proceeded without the risk of left recursion. The parser would use appropriate parsing techniques such as recursive descent or other parsing algorithms to recognize and analyze the input according to the transformed grammar. So, in summary, left recursion in context-free grammars can be problematic for certain parsing techniques. Eliminating left recursive involves transforming the grammar to avoid direct or indirect self-references. As you see, it was self-referenced in the leftmost derivation. So by making parse tree more feasible and avoiding infinite recursion issues using that equations that we have seen. Next, let's see left factoring. Left factoring is a technique used in context-free grammars to eliminate common prefix among alternative production rules for a non-terminal. This helps to making parsing more efficient and avoids ambiguity. Left factoring is typically applied to improve top-down parsing methods, like recursive descent parsers. So, if more than one grammar production rule can have more common prefix strings, then the parser cannot make a choice as to which the production it should take to parse in the string. For example, let's say this non-terminal have many strings, this one, and so on. So the parser cannot decide which one to choose from this one and this one. The solution is using this equation to change it or to add another non-terminal to this grammar. So this is how it looks. We are going to see it with the example. So consider the following context-free grammar expression here. In this grammar, E represents expressions and the production rules allow the addition multiplication operation on identifiers indifferent of them. However, this grammar exhibits common prefix among the alternative production rules of E. So it would cause an issue, for example, if you want to parse this token. So to address the common prefix, left factoring can be applied. The idea is this: to factor out the common prefixes and introduce new terminals to represent the remaining alternatives. The modified grammar would be like this. By changing this expression to this expression using this formula, we can get that this grammar, adding E prime here. Here, E prime is introduced to capture the remaining alternatives after the common prefix ID. The E prime non-terminal handles the cases where there is either an addition multiplication or nothing after the identifier. When you see the parsing with the left factored grammar, parsing becomes more efficient, especially for top-down parsing methods. The parser can now easily decide whether to expand E prime non-terminal based on the presence of the plus or the times in the input. So let's see the example that we have here. ID plus ID times ID. In this derivation, the grammar successfully recognizes and drives the input expression according to the left factored grammar. So by changing this grammar to this, we can now change this ID or this token to parse it correctly. So when you see the benefit of left factoring, it improves parsing efficiency. Left factoring simplifies the decision-making process for the parser by removing common prefixes, making it more straightforward to determine the correct alternative. And also it avoids ambiguity. Left factoring helps in avoiding ambiguity that might be arising from the common prefix among the alternatives in production rule. We have seen that in here it was very ambiguous to choose from this grammar and this grammar previously. Next, also its applicability to top-down parser. Left factoring is particularly beneficial for top-down parsers like recursive descent parsers, where efficient decision making is crucial. In summary, left factoring is a technique used to eliminate common prefix among alternative productions. This simplifies parsing and improves efficiency, especially for top-down parsing methods. The resulting grammar is often more readable and less prone to parsing issues. Remove the left recursion of the following expressions. We have two grammars here. And remember, the pipes are used in the grammars and they represent an alternative productions for the given non-terminal. To answer this question, first we have to look at the grammars that we have. For the first one, as you see now, the non-terminal is appearing on the left side of its own grammar that's given. So this is going to create a left recursion, meaning that if you are going to use this grammar that you have, it's going to continue that calling itself again and again. So it will cause a left recursion. So it's for the second one. As you see here that the expression non-terminal is calling itself in the left side, which causes a left recursion. Also the term here. So we have a formula to remove the left recursion. By using this formula, we can transform this grammar to a grammar that don't have a left recursion. So the result is going to be looking like this. We are going to have an a prime value that is new, and it's going to help us remove the left recursion from our given grammar like this. For the second one also, we would have an answer like this by adding a prime value for expression and also for the term that we have. Remove the left factoring of the following expression. We have two grammars here, and also remember that these are pipes that represent two alternative productions for the given non-terminal. To answer this question, first we have to look at the grammar that we have been given. In the first grammar, we have a C non-terminal and if E then S else. And the next grammar that we have is if E then S. So by looking at it, you can see that both of these grammars seem the same because with one condition we can apply both of them. So it will cause an ambiguity in our grammar when we are parsing our table. So we have to remove this left factoring from our given expressions. Also, if you look at in the grammar too, we have this kind of issues. Like if the condition, then the statement, else the statement. And also for the second, we have the same kind of condition with different results. So we have to remove the left factoring. Just like the left recursion, we have a formula to remove the left factoring. And this is how it looks. For the given a is equal to, which gives us alpha, beta, and alpha, gamma, we are going to add a new a prime, and we are going to distract this given grammar into two. So let's look at the first answer. So this is how it's going to look like. This is the new corrected left factoring removed grammar. And also for the second one, this is going to look like this. For the given statement that we have here, this is going to be the answer by using the formula that we have seen earlier. Now, let's see types of parsing. The way the production rules are implemented divides parsing into two types, the top-down parsing and bottom-up parsing. I've been talking about these two parsing systems previously, and as I said, top-down parsing uses the parsing starts from the top while the bottom-up parsing starts from the bottom. So first, let's see the top-down parsing. Top-down parsing can be viewed as a problem of constructing a parse tree for the input string, starting from the root and creating the nodes of the parse tree in pre-order. Equivalently, top-down parsing can be viewed as finding the leftmost derivation in input string. So these are the basic two things in top-down parsing. The first one is it starts from the top parsing, which is the roots of the parse tree, and also it is from left to right derivation. And terminals are seen in order of appearance in the token stream. And this is the structure of the top-down parsing. This section begins with the general form of top-down parsing, which is recursive descent parsing. This requires backtracking to find the correct A production to be applied. The next one is the predictive parser, which is the special case of recursive descent parsing where no backtracking is required. Predictive parsing chooses the correct production by looking ahead of inputs a fixed number of symbols. Typically, we may look at 1. So we may look at the LALR parser most of the time. So generally speaking, the difference between the recursive descent parser and the predictive parser is the recursive one, whenever an error occurs, it goes back and changes the rules, while the predictive parser looks ahead of the production. So this is the basic difference between two. When we see the recursive descent parsing, a recursive descent parsing programs consist of a set of procedures, one for each non-terminal. Execution begins with the procedure for the start symbol, which alters and announces the success if its procedure body scans the entire input string. Generally, recursive descent may require backtracking. That's it. It may require repeated scans over the input. However, backtracking is rarely needed to parse the programming language constructs. So backtracking parsers are not seen frequently, even for situations like natural language parsing. Backtracking is not very efficient, and tabular methods such as dynamic programming algorithms are preferred. So recursive descent parsing is not much common to look at it. So the basic thing, as I said, is it uses the recursive method in the procedures, and if one derivation of production fails, the syntax analyzer restarts the process using different rules of same production. And as I said, it suffers from backtracking. Let's look at it with an example. Let's say we have these grammars. The first one is our start, and the next one is another grammar. And our token stream is open bracket, int, and close bracket. So using the top-down parsing, let's see how to implement using recursive parsing. So this is the thing that we have to implement. First, we create an one node tree consisting of A. As I said, we create one node tree consisting of A. Then we are going to have two pointers, one for the tree and one for the input. Will be used to indicate whether the parsing procedure is. Initially, they will be on E and the first input symbol respectively. So this is the first letter in the our string, and it will be the other one will be on the E, on the first E. Then we use the first E production to expand the tree. This is our first production of the start symbol, so we use this production to expand the tree. The tree pointer will be positioned on the left symbol of the newly created subtree. So this is how it looks. Now, as the symbol pointed on the tree pointer matches that of the symbol pointed by the input pointer, both pointers are moved to the right. This pointer is going to move to the int and also the next one. Whenever the tree points on non-terminal, we expand it using the first production of the non-terminal. Whenever the pointer points on different terminal, the production that was used is not correct. Thus, another production should be used. We have to go back and step just before we replace the non-terminal and use another production. So here, as you see now, the t is consisting of an int, right? But we are going to face an error because we need the open bracket here. So there is a mismatch. So we have to backtrack, or we have to go back and change our production rule. So this is how it looks. Next, we are going to choose the second production rule, and then after that we are going to change this t or e using the another production rule, which is t. Now it looks perfect because we have the opening bracket, int, and the closing bracket. If you reach the end of the input and the tree pointer passes the last symbol of the tree, we have finished the parsing. So we can also see this example. We have the start symbol, which is S, and this is how it looks. It's production, and we have an X non-terminal and that non-terminal. For an input string, which is read, a top-down parsing will behave like this. So we are going to, our string is the word read, R-E-A-D, and we are going to parse it using top-down parser. So this is how it looks first. We are going to choose the first production rule. Then using this, we are going to change the X. Since this doesn't represent the rate, we are going to backtrack because we chose the first production for the X, which is wrong. So we have to change that one. So this is how we represent our expressions using the top-down parser. So let's see the implementation of the recursive descent parsing using algorithms. So the main function initializes the parsing process by calling eProduction here, as you see it here. The main function initializes the parsing process by calling a function and then checks if the end of the input is reached by the $sign. So if it prints successful, then we have finished our parsing. The $sign represents the ending of a string, so it's going to check if it's reached by the $sign. If it is, it's going to print as successful, otherwise it won't. The if function checks if the current character, which is I, if it's matches I character, and then calls the if e prime function. As I state, if it matches the I, then it will call the e prime function. And when you see the e prime function, it checks the current character for the plus sign, and if it is matched the plus character, then it matches the I character, then it recursively calls itself to handle the continuation of the expression. If the current character is not plus sign, then it returns without doing anything. And the match function here checks if the current characters match the expected character t. If it does, it reads the next character using the get char. If it mismatches, it calls the error function, which is assumed to handle the error reporting. So this is how we construct our algorithm for this production. The starting one is this E, and we have this E prime as the second production. And this is how we represent it using algorithms. Next, we are going to look at how to write the C++ code for this algorithm. Now, let's see how to implement our C++ code for the previous production that we have seen using the C++ code. So let's go to our VS Code and open it. Then let's go to new file, and the text file, let's pick the text file, and by default it will ask you to select language, and we are going to select C++. Okay, the first thing that we have to do is include the airstream while writing the C++ code. So include airstream, and next to that we have to write our main code, which is int main, and in here let's create some variable. So let's create it first outside of the main character because we are going to use it later. So let's say char.ch, which is our character, and we are going to invoke it inside our main also. Say it's equal to get char in order to accept character from the user. Then after that we have to invoke our function or our production rule, the start function. So we are going to create an function here, void e if our character equals with I, we are going to create a match, but for now let's just type I. Next we are going to create it. So then let's create the e prime, but it's not applicable to write the e prime function like this. So let's write the e prime like this. We are going to work it like here. After that, okay, let's create the e prime function first. Void e prime. Then inside we check using the if function the characters that we get. If it is the plus sign, then we are going to invoke the match function also here. If it's match, we go to the next one. Then after that we have to check if it matches the character I, and then later we have to make it recursive, so we have to invoke the e prime. Now let's write the match code also. Void match char t, it accepts the character t. Then if the character equals t, then what? We are going to accept get char, we are going to invoke it, else we have to return an error because it's not right. So let's also add another code, which is a void also. Then we are going to respond cout using cout. Let's say the error is going to represent error unexpected character, and then like this. So let's finish our main function. We have jumped that one. Let's go back. As I said, first we have to invoke the our first projection. Then after that, if character is equal to dollar sign, meaning that the dollar sign appears in every string at the end of it. So if it appears the dollar sign, we are going to we are going to respond to the user using cout a message saying successful. What about it doesn't appear to have a dollar sign? Let's write the else function cout, and let's write an error function, an unexpected character after parsing, and let's give it a return value of 0. Now that we have finished our code, let's save it first before running our code. So by clicking Ctrl plus S, we can save it. So let's name it Recursive Decent Parsing. You can name it as you want, and it should be a C++ type file. By default, it's going to choose for you, but if it's not, choose the C++ file. And while doing so, we can see some errors that I make while typing the code. The first thing is I missed on some point the semicolon here, for example. And also I forget to add the exit file code if it's one. And unlike JavaScript and other codes, C++ is very code sensitive, so we have to add the semicolons in every line at the end of it for the error. Also, where do I miss here? Okay, we have to choose the semicolon also here at the end. And one remaining thing is, let's change to double. Now let's save it again. And let's go to the right top side, and there is a drop down beside the run. So let's click on the run C++ file, not the wrong code. And in the top, it's going to appear this drop down, and we are going to choose the second one, or the C with C++ and then g++.xq build. Let's click on that one. It's going to build our C++ file now, and also it's going to open our terminal at the bottom. So now let's write our code, or let's write our string. So let's, for example, let's write I plus I, then dollar sign, I plus I plus I, then dollar sign, and then hit enter. Now it's going to give us a successful, as you see it here. What about if it is something other string? Let's see it. So for example, let's add I plus I minus I, then dollar sign. What is going to be the response for this? Let's hit enter, and it's going to give us unexpected character after parsing. So it's going to give us this error, and this is how it looks. Now, let's look at the first and the follow sets. This is an important part of parser table construction. The first and the follow are concepts used in the context of compiler design and parsing. specifically in the construction of the predictive parsers and LLK parsers. These concepts help in determining the parsing table for the grammars. So it's better knowing about the first state and the follow state before jumping into the predictive parsers. First, let's look at the first state. This helps us to know what terminal symbol is derived in the first position of by a non-terminal. The first of a symbol in a grammar is the set of terminal symbols that begin in the strings derivable from that symbol. It represents the first symbol that can appear in the derivation of a particular non-terminal. For example, let's say we have alpha that produces t and beta. That is, so if you look at the first set, then alpha drives t, or which is a terminal, in the very first position. So t is the first set of the alpha. If you look at on the example here, we have a grammar that's given for us like this. This is our star symbol or our first production. Then these are the rest. So if you are going to pick out the first state for these productions, what we have to do is first point out the non-terminals. So our non-terminals are E, E prime, T, T prime, and F. And mind that this grammar is derived from the one that we have seen earlier before, which was the has an issue of the leftmost derivation. Now it's derived. Okay, now the first thing that we have to do is from the principle, it says that the first non-terminal symbol that we are going to see is the first symbol. So if we are going to look at the E, the first symbol that appears, the non-terminal on E, is not appearing. So we are going to look at the T that's inside the E. So when we go to the T, here is having a non-terminal also here. So we are going to go to the F also again. In F, we are going to find an open bracket. But so we have to, if you are going to work like this, you have to pass through each non-terminal to drive them. So it's better most of the time to start the picking out the first states from bottom to the top, meaning that we have to start from the F, then we are going to go up, because it is easier to get the first state of the grammars that we have. So let's pick out for the F. For the F, the first symbol is, in the first production, it's an open bracket. And on the second one, we have an ID. So this is an identifier. So F has two first states, which is an open bracket and an ID. Next, let's see on T prime. T prime has an asterisk or a star sign as the first state, and also an epsilon as an option. Next, we have the T production, which produces a capital F and T prime. So let's go to the F. So in the F, we find that the first state is an open bracket and an ID. So we are going to take these two for T. We directly pick the values of the first state of T from the F. Next, we have the E prime. And for the E prime, we have the first state of the plus sign here and also an epsilon here. This one is the simpler one, as you see it. And the next one is the E, or the star symbol, which depends on the non-terminal T. So when we go to the T, it also depends on the non-terminal F. So what we can do is simply we can just pick the values of T, the first set of T, without looking at F also. This is what you do. So we are going to pick this ID and the open bracket from the T to our first set of E. So this is the way to pick the first sets. This First sets are used for deciding which production to use in a derivation. Also, they are used for handling the epsilon production or the E production, the production that drives an empty string. Next, let's look at the follow set. The follow of a non-terminal in a grammar is a set of terminals that appear immediately next to the right of the non-terminal in some derivation. What terminal symbols immediately follow a non-terminal in production rules are, when we look at it is, it represents the set of the terminals that appear just after to non-terminal in a valid sentence. To look at it, if a star symbol, then it is going to have the follow set of a dollar sign, because by default the dollar sign represents an ending of a set. So if it is the star symbol at the end, we are going to assume that it has a follow set of a dollar sign. If a is a non-terminal and has a production of alpha is equal to AB, then first of B is in follow of F except epsilon. So from here we can see that when we are picking about the follow of A, we are going to select the first of B, because at the end of the A string we are going to find the B string, so we are going to pick the first of the B as the follow of A. But if it's going to be exceptional for epsilons are not included. Next, if alpha is a non-terminal and has a production of alpha is equal to AB, where B is an epsilon, then the follow of A is the follow of alpha, meaning that, let's say this is the star symbol, and if B is an epsilon, meaning that empty, so we are going to select the follow of alpha. Let's see it using example. So we have this grammar and we have picked the first set previously. So let's pick at the follow set. While doing so, it's not essential to start from the bottom. For the follow set, you can start from the top side. But for the first set, we have said earlier that it's good to start from the bottom. Now let's pick the follow of E. So the follow if is by default, this is the star symbol, so it's going to have a dollar sign. Next, let's look at the grammars and let's look at where E is called. So here E is called. So next to E, we have the close symbol here, the closing symbol. So these two are going to be the follow of E. When we go to the E prime is called in here E. So it's going to, it's going to get the follow of E by default because this is at the end. So next to this, we have the dollar sign and the E prime closing tag. So this is going to take the follow of E also. Next is called, here in E prime, it's recursive. So only two of them are its follow. Next, when we are looking at the follow of T is called in here. So the start of the E prime is going to be the follow of the T. So we are going to select this plus sign, and also where is other place T is called. T is also going to have the value of the E, because E prime is next to T, and E prime could maybe an epsilon, meaning that's empty. If it is empty, then this is going to be empty here. So if this is empty, then T is going to get the follow of E also. So by default, it's going to get the dollar sign and the closing tag. Next, we have the T prime. And for the T prime, it is called here in recursive, and it's also called here. So from here we can get that T is also going to get the follow of t prime is going to get the follow of t, because this is t prime is called at the end of the production of t, so it's going to get the follow of t. Next we have f, and f is called here, so it's going to get the start of the t prime. Also here it's going to get the start of t prime, so what we are going to do is select this star sign, and also the, if you look at that, so the, it's going also to get the end of the value from the t prime, or I mean from the t, because if t prime is going to be empty here, it's going to get the follow of t here, because t prime has an option to be an epsilon or an empty. So when we look at the importance of these two, these sets, or the follow and the first sets, are important for constructing a predictive parsing tables, which are used in top-down parsing. In production, in predictive parsing, you predict which production to use based on the current non-terminal and the next input symbol. The first and the follow sets helps resolve ambiguous and conflicts in the prediction process. We are going to look at next the table of the prediction, so it's going to be more clarified. And this is a simpler way to represent the first and follow set, and it is very good to write it in a table. So in sum, that in the context of LL1, which we are going to see next, parsing where 1 represents the number of tokens of blue kite, constructing a parsing table involves the first and the follow sets to make decision about which production to apply. If the grammar is LL1, the parsing table won't have conflicts, and the parser can be implemented as a simple recursive descent parser or the table-driven parser. So it's essential to know about this first and follow sets before jumping into the next section. So first and follow sets help in making decisions during the parsing process and play a crucial role in constructing parsing for the programming language. Give the first set and the follow set for the given grammar. The question asks us to give the first set and the follow set of the given grammars. As we have said earlier, that the first set is the first non-terminal that we find while in our grammar that we have, and the follow set is the first terminal that we get next to our given grammar. So while doing the first thing that we have to look is the first set, and when we do the first set, it's common to start from the bottom to the top. So we are going to start from B to S. So when we pick at the first set, we're going to have an epsilon and D. And for the A, we are going to have an epsilon and C. And for the given non-terminal S, we are going to have the value of A as its first set. It's going to be C and epsilon, but epsilon means no value. So it could be a small letter A. And this is how it's going to look like. And when we pick up the follow set, we are going to look at the next value next to our given grammar. So when we look at the first set, this is going to be our start set, so it's going to have a dollar sign. And since B is appearing in the last section of the grammar in the start symbol, it's going to take also the dollar sign. For the second grammar, we are going to have the first set and the follow set like this. Next, we are going to look at the predictive parsers. In the recursive descent parser, we have seen some things, but in the predictive, it can predict which production to use by looking for the next few tokens, and also it differs from the recursive descent because it doesn't have backtracking. When we see the predictive parser accept LLK grammars, let's see what does mean. So the first L means left to right derivation for the scan for the inputs, and the next L means leftmost derivation, and the K means the predict based on the K tokens of lookout. And in practice, LL1 is used most commonly. So LL1 is the one that we are going to look at next. So in recursive descent, at each step, many choices of production choice. We have seen that previously. We can choose from different productions, but in here it's not going to appear like this. And in recursive, backtracking used to undo bad choices, but here it's going to be different. In LL1, each step only have one choice of production, so there is no room for the choice of bad choice here. LL1 is a recursive descent variant without backtracking also. And in LL1 parser, we have a stack that is initiated with $, and LL1 parsing table and an input buffer with $, appended at the end. So I have said that in the production, for the start symbol, we have at the end a $, which represents the ending of the production. And also when we are adding the string to our parser, we are going to append a $, at the end of it to represent the ending of that string. So this is the crucial point. So first, before jumping into the parsing, how it works, let's see the parsing table or the LL1 table. We have this grammar that we have constructed earlier, and for this we have created the follow and the first set. This is how it looks, the first and the follow set of this grammar. We can look at it. For the first, you start from the bottom and pick at the first sets, and for the follow you can choose start from anywhere and you can select the follow sets. After this, we have the LL1 table we are going to construct. At the top we have the terminals here and also the $, and in the left side we have the non-terminals appearing here. So what we are going to do is we are going to select for the first set, let's say we have ID here, right? So in the ID we are going to use this section or this grammar of the E. So what about next? In the first state we have the opening bracket. So in the opening bracket we are going to go there and we are going to put the production of the E. So we don't have any first state, so we are going to jump to the next, which is the E prime. And for the E prime, we are going to look at the first state. And in the first state, we have the plus sign. So we are going to go to the plus sign here. And in the plus sign, we are going to put the production of the E prime. Here we have two productions, which is the first one is plus T and E prime, and the next one is epsilon. We are not going to choose the epsilon one. We are going to choose the first one. And also, okay, this is let me skip it through. So we are going to put the plus TE prime in the plus sign, and for the epsilon part, what we are going to do is we are going to put the epsilon in the follow set of the E prime here. So what we are going to do is we are going to look at the follow set of E prime, and in the $, and in the closing tag we are going to put the epsilon production of E prime. And this is the basic rule. If we have an epsilon in the first set, we are going to look at the follow set and put an epsilon production in them. This is the principle. Next, we have the T, and for the T, we are going to look at the first set, and we are going to put the production in ID and opening tag. After that, we have the T prime, and the T prime contains an epsilon and is an asterisk. For the asterisk, we are going to put this production, which is asterisk ft prime, and for the epsilon, we are going to put that epsilon production of T prime in this plus sign, dollar sign, and the closing tag. And at the last, we have the F production, and the F production has a first state, an ID on ID and opening tag. So on them, we are going to put the right one in the right section. For the ID, we are going to pick this ID production, and for the opening tag, we are going to pick this production, which is open bracket e close bracket. This is how we produce the LALR parsing table simply by looking at the first and the follow set. So remember that if we have the first set for the production, we are going to put that accordingly. From the first set, we are going to put the production in the right section. If you have an epsilon, we are going to look at the follow set, and in the follow set, we are going to put the epsilon production of that non-terminal. This is the way to create the parsing table for LL1. Next, let's see how to implement this parsing. So let's say we are tasked to parse this int times int using the grammar given below. So we have this grammar, and we are tasked to parse this int times int using the grammar. So what we have to do is first pick the first and the follow set. So we have to construct the first and the follow set, and for the time being I construct that. But to look at it first, we have to create the table, and for the first set we are going to start from the bottom to the top. So when we look at the first of the y non-terminal, we have an asterisk and e or an epsilon, and for the x we have the plus sign and an epsilon. These are assumed to be an epsilon, so we have that. And for the t, we are going to look at the open bracket and an int here, and for the e, we are going to look at the first set of the t. So we are going to pick this t to the first set of an e. And for the follow set, we are going to look at from the start to the bottom. And for the start symbol, we have the dollar sign by default, and is mentioned in the T non-terminal. So we are going to look at the next stage, which is a closing tag. And by doing so, we can construct all of the follow sets like this. Next to that, we are going to create the parsing table using this first and the follow set. And this is how it looks. And by going into the open bracket and int, we are going to put the production of e like this in both of them. And also for the t, we are going to pick, for the open bracket, we are going to pick this production because we are getting the open bracket in this production, not in the int y. So we are going to pick the first production for the open bracket, and for the int, we are going to pick this second production of t. And for the epsilon on the third one, x, we have the plus sign and an epsilon, and in the plus sign we are going to pick this production, and we are going to put it in the plus sign table column. Okay, so and for the epsilon we are going to look at the follow set, and in the follow set dollar sign and the closing tag, we are going to write the empty production of x. And so as for the y, we are going to do that. This is how we create the parsing table. Next to that, let's see how to implement the parsing generally. So at first I've said that we have a stack and an input buffer. So this is how it looks. In the input buffer we are going to put our int times int, and at the end we are going to have a dollar sign, right? So also in the stack we have the stack, and at the bottom we have the dollar sign. Then we have the first or the start production, or which is A, and by starting from this we can create our structure. So this is going to be the structure. At first we have the stack, which is holding A and dollar sign, and our input is int times int and dollar sign, and the action is going to be a tx, because if you look at it in the E section from this parsing table, when an input of int appears, we are going to change it, or we are going to produce tx. So we are going to transform this E to tx directly using this action. So next we are going to pop up this E and we are going to change it using tx here in the stack. Now we have tx and the input is not changed. And let's look at the t production for the int, and we are going to transform this t into int y by looking at the table. So the action is going to be int y here. So t is transformed into int y here, and x is where it was, and input is still the same. So now we have in the stack int and also in the inputs int. So this is a terminal, so we are going to pop up both of them because we have found the input in the stack. So they are going to be removed from the stack and the inputs because it is terminal. Next we have y and x dollar sign and asterisk int dollar sign. So let's look at the table of y, and when it's appearing an asterisk, we are going to transform this to this production. So we are going to change it. We are going to put the asterisk t in here, and we are going to transform this y to this production. Next we have the asterisk and asterisk in our stack and inputs buffer. So we got the terminal. So what we are going to do is we are going to remove these two. Next we have the t and x, and here we have an int. So we are, by looking at the table for the t, when int appears in the input buffer, we are going to pick this production. So we are going to transform this t to an int y. Then we find the terminal here, so int is cancelled by the int. So next we have y and x, and here a dollar sign. So what we are going to do is in the dollar sign, let's look at the y production. So we are going to transform y to an epsilon because it's showing us in the dollar sign table in the column. We have to transform it to an epsilon. So by removing it, we are going to write an epsilon here and remove the y, because if you write it here epsilon, it's meaningless. So we are going to remove it directly. And also for the x, if you look at it in the dollar sign, we are going to put an epsilon. So we are going to write here epsilon and remove x. So at the end we have the dollar sign and dollar sign. It is showing, these dollar signs are showing that we have reached the end of the stack and the input. So the parsing is completed successfully. So it's going to accept it. So this is the parsing, how it works by using the stack and the buffer. Using the grammar, construct an LL1 parsing table and check if the input is acceptable. We have the grammar in the left side and an input string for the given grammar in the right side. The question asks us to construct an LL parsing table. which is a top-down parsing table, and check the input strings that we have given here next by using this grammar. So the first thing that we are going to do is remove the left factoring in the given grammar. As you see it here, we have a left factoring in the second grammar that we have here. If you look at it for the given non-terminal A, we have two grammars, and the first one is T plus A and the next one is T only. So we have to remove the left factoring from the given grammar. And also for this non-terminal T, we have F coming in both of its grammars, so we have to remove the left factoring from the given value. So this is going to be our newest grammar that we have here. So you have to remember always to check the left factoring and the left recursion to remove the ambiguity and the error that you may find while parsing. Next to that, by using this left factored grammar, we are going to create a first set and follow set table. And this is our first set and follow set values that we have for our given grammar. Next to that, by looking at the first set and the follow set, we are going to create the parsing table that we have for LL1 table. So this is how it's going to look like. For the given S, we are going to look at its first set. It says that we have an ID as its first set, so we are going to put the grammar of S in the ID section here. So the dollar sign represents that S is the start symbol, and the dollar sign shows it is the ending section. And also when we took the E non-terminal, it has two values for the open bracket, and for the ID we are going to put its values. So for both of them we are going to put the E values that we have. This is not the grammar, we are using these grammars that we have here. And for the E prime, we have the plus sign and the epsilon. While the epsilon appears, what we are going to do is, in the follow set, we are going to write an epsilon value. So in the follow sets, we have the dollar sign and the close bracket. And in both sections, we are going to put the dollar sign. And by doing like this, we are going to fill the parsing table. Then next to this, by using this parsing table, we are going to check the input string that we have. So this is how it's going to look like. At first, we have in the stack the S or our start symbol that we have, and in the input buffer we have this ID is equal to ID plus ID times ID, and at the end we have the dollar sign, meaning the ending of our given string and grammar. So first what we are going to do is we are going to take an action by changing the ID to A. So by doing so like this, we are going to find the values. When we find the terminal, we are going to change the values based on that. And at the end, we are going to find the stack is going to be accepting the values of the given string. So the input given is parsed by the given grammar. Hello everyone. Next, we are going to see the bottom-up parsing. Earlier, we have seen the top-down parsing. Now, the next topic is bottom-up parsing. The bottom-up parsing begins parsing at the leaves or the bottom and works up towards the roots or the top side. This is the main difference between the bottom-up parsing and the top-down parsing. And the key decisions in the bottom-up parsing are when to reduce and what productions to apply as the parse proceeds. And these are the two crucial things to see while working on the bottom-up parsing: when to reduce and what production to apply. And at each reduction steps, a particular substring matching the right side of the production is replaced by the symbol of the left of that production. If the substring is chosen correctly at each step, the rightmost derivation is traced out in reverse. And we can think of bottom-up parsing as the process of reducing a string with, for example, starts with a symbol of grammar. At each reduction step, a specific substring matching of the body of a production is replaced by the non-terminal at the head of that production. So we are going to look at most of the bottom-up parsing, so no worries. So these are the types of bottom-up parsing. When you see the bottom-up parsing, it is a shift reduce and it has LR parsings inside it. And SLR, LR, and LALR parsers are some of the parsers inside the bottom-up parsing. So the first one is shift reduce parsing. So this shift reduce parsing uses two unique steps for bottom-up parsing, which is shift step and reduce step. These are the basic two things that we are going to use while working on the bottom-up parsing. The first shift step refers to the advancement of the input pointer to the next input symbol, or the shifter symbol. This symbol is pushed onto the stack. The shifter symbol is treated as a single node of the parse tree. And the next one is the reduce step. When the parser finds a complex grammar rule on right hand side and replaces it to left hand side, it is known as reduce step. This occurs when the top of the stack contains a handle. To reduce, a pop function is performed on the stack, which pops off the handle and replaces it with the left hand side non-terminal symbol. So while building on shift reducing parser, a stack holds the grammar symbol and there is going to be an input buffer that holds the string to be parsed. And the next one is the handle always appears at the top of the stack just before it identifies as the handle. And as I said earlier, that $sign is used to mark the bottom of the stack and also the right end of the input or the ending of the input string. And by default, the stack is going to be empty when starting, then it's going to fill by the string. So for example, let's use this grammar and by shift reduce, let's try to parse this input id1 times id2 and we have this grammar. So what we are going to do is first create a stack and inside the stack we are going to push the inputs. So I have designed the table for us and by default, okay, the starting is this one and we are going to start from the empty stack which has by default a $sign. It represents the ending and we have the input buffer that contains our string id1 times id2 and at the end we have $sign and by default this is going to be appearing. So the parser or the shift reduce parser is going to shift, it's going to take an action or shift, and at first we have an id1, so it's going to shift id1 to the stack. As you see it's going to move it to the stack. Next, in the input, we are going to be left with this times id2 $sign. So what we are going to do is in the stack we have an id, so we are going to reduce it to the non-terminal f because we have here in the grammar you can see that the f can be transformed to an id, so we are going to reduce it back to the f. So we are going to change this id to the f. And next also we are going to reduce this f to a t because if you see the second grammar here, t can be also transformed to an f. So we are going to reduce it back to t. Next we are going to shift or we are going to move the input string from the input to the stack. So we are going to shift the star sign or this character of the star. Next, we are going to shift also the second ID. After that, we are going to left with an empty input buffer, and we are going to reduce these remaining values. We are going to first reduce this id by f, because the grammar allows us to reduce it. And from here now we can see that we can reduce t times f to a t, and at the end also we can transform this, we can reduce this t to our start symbol or our e. So we are going to reduce it, and at the end we are going to be left with our start symbol, which is an e here. So it's going to accept it. The action is going to accept it, so the parser parsed this input correctly. Next, let's look at the LK parser. So LR parsers are a non-recursive shift-reduce bottom-up parsers. The L in the first or in the left side represents to left-to-right scanning of the input, and the R for constructing the rightmost derivation in reverse, and the K for the number of input symbols is the lookahead that are used in making parsing decisions. By default, if you omit the K, it means that it's assumed it's 1. And this LR parser uses a wide class of context-free grammar, which makes it the most efficient syntax analysis technique. So now let's see the types of LR parsers. The first one is LR0. The next one is SLR1 or simple LR. The next one is LALR1 or lookahead LR. And the last one is canonical LR. And as we go from top to bottom, the complexity becomes bigger, and also the power of the LR parser is going to increase as you go down. But the first one is going to be simple and easy to parse, and the last one is going to be a little bit more difficult to parse or to understand it. So let's look at the first LR0. While doing the LR0 table construction, these are some keywords that we are going to work with. The first one is LR0 item, or just simply an item. This is a product. This an LR item is a production of grammar G with the dot at some position of the right side. An item indicates what is the part of the production that we have seen and what we hope to see. And next we have the item set, and after that we have the LR state, which is a set of all items, and LR state is a collection of LR items that represent a particular configuration of LR parser. It corresponds to the set of items that are valid in a particular parsing context. To construct a canonical collection of grammar, we define augmented grammar and two functions that are closure and goto. So we are going to look at these two also. When we go to the first one, the augmented grammar, this is the modification of the original grammar used in LR parsing. It includes the additional parsing of S prime to produce S, where S is our start symbol of the original grammar and S prime is the new start symbol. This modification is made to ensure that the parser can recognize when it has reached the end of the input, and the purpose of the new starting position is to indicate the parser when it should stop parsing and announce the acceptance of the input. Don't worry about it, we are going to look at it next, so it would be more clarified. Next we have the closure operation, so the closure operation is used in LR parsing to compute the set of LR items that can be derived from the given set of LR items. It involves considering the production rules associated with the items and including additional items that represent the possible next symbol in the next rows. So at the last we have the goto operation. This goto operation is used in LR parsing to transition from one LR state to another based on the given grammar symbol. It involves the shifting of the .lr items to represent the movement of the parser through the grammar. So let's look at all these keys next with example. So before jumping into our parsing, we have to have some steps to go into. The first one is, while given a grammar, the first thing is to add an augmented production in the given grammar. Next, to create a canonical collection of LR items, and then draw data flow diagram from it. After that, we can create the LR table. So let's dive into our example. Let's say we have this grammar, which is S produce AA and A produce a terminal A and A or B. So the first thing that we have to do is create the augmented grammar. And so what we are going to do is create an S prime here that produces S. And as I said earlier, the purpose of this new starting production is to indicate the parser when it should stop parsing and announce the acceptance of the input. So we are going to look at it in the table, where at the end it's going to accept, this S prime is going to accept the grammar, the given string. Next, after that, we are going to have the canonical collection of items, and as I said, there is going to be a dot that represents the items, and by default, these are how it starts, and it's going to stop. This kind of collection of items are going to be bigger or much more, and at the start, we are going to have this collection of items from this augmented production. And as we go through, the collection of items becomes a little bit more, because this is going to produce another collection of items. Also, we are going to look at using the diagram next. When we come to the data flow diagram, first we have the augmented production here, and we are going to assume it at our first state. And from this, using all these productions, we can go and we can also shift these dots to the right side one at a time. So when we do that, first we are going to find these other states. Let's look at them one by one. First, let's use this production, and using the non-terminal S, we go from this state to this state, and also we are going to shift this dot sign to the right side. Next to that, we have this production, or S produces dot AA. So when we shift the dot in this state, we find another non-terminal. While when we find a non-terminal in the new state, what we have to do is we are going to write all of its productions. So currently the A has its own production, so we are going to write it here. So let's move to the third production here, which is A produces dot A and non-terminal A. When we do that, what we are going to find is we are going to shift the dots to the middle side, one piece at a time. So when we do that, we are going to find another non-terminal here. So when we do that, we are going to also write the productions of A down here below. These both are the same. The writing is also only the difference between these two. You can write it like this or like this. And at the end, we have the fourth production. And using B, we can produce this state, and the dot is going to be shifted to the right side. Now, as you see here in this one and in this one, the dot is in the rightmost side, meaning that there is no terminal or non-terminal beside him in the right side. So these states are finished. So let's work on these two. So when we see this state, it has two productions. So when we go to the A, we are going to find another state, and also when we do this, we are going to find another states. So when we finish that, for example, when we using the A, we can get new production, which is like this, where a dot is going to appear. So this is going to be the end. And also when we use this another production, we find another state which leads us to this state, because it's going to give us when we use this production, it's going to give us a dot a. So it appears to be giving us this state, so we are going to go to this state as you see it. And when we use this production dot b, it's going to transform it to b dot, so we are going to get this production. And also for this, when we do that, for the first production, we get a new state that shows like this. And when we use this second production, we get it on itself. So we are going to loop it back inside here as you see. And for the third, we are going to get this state. So to clarify all the states, we can give them a name. So let's say this one I0, then I1, I2, I3, I4, I5, and I6. Currently we have 7 states. So this is how we represent it using the data flow diagram. After building the data flow diagram, we can now build the table of the parser. So there are rules that we have to follow while doing the table. So the first thing is that if a state is going to some other state on terminal, it is going to be a shift move. For example, this is a shift move because the state is going to another state using terminal, and also this is a shift move. And the next one is if a state is going to some other non-terminal, some other state using non-terminal, it's going to be a go-to move. So these two are going to be a go-to move. These two are shift move. And also if a state contains a final item in the particular row, then we write a reduce not completed. So when the shift, when we go to another state and we find these items or states, we call them a reduce nodes. So let's build our table. So this is how we are going to create our table. This is how it looks. I moved the states a little bit lower to show the table here directly. So this is how we are going to write it. So for the terminals, there are actions, and I said that there are shift moves when you use them, and these are our states in the left side. And for non-terminals, we use the go-to moves, as I told you. So this is the basic principle. To repeat it again, for when we are using a terminal to go from one state to another, we say it's a shift move, and when we use non-terminal, it's a go-to move. And when we find an item that that has a final item, or that has a dot in the rightmost side, it's going to be a reduce not complete. When we look at it, the first state that we have are some moves, and 4 moves it contains. For example, using the terminal A, we go from state 1 to state 3. So we are going to assume that we are going to write here it is a shift, and we are going to a 3, right? State 3. So we are going to say that shift 3. And using the terminal B, we are moving from state 0 to state 4. So we are going to say here shift 4. And for the A and the S, which are non-terminals, we are going to use this go to, and we are going to only write the where we are going from state 1 to the destination. So using S, we are going from 0 to 1. So in state 1, we are going using S to state 1. So we are going to write only 1 here. And using A, we are going to state 2, which is 2. So we are going to write 2 like this. S represents shift, and this is how we say. So S3 means shift to 3. So from the 0 state, using shift 3, we jump to these 3 states. And if we look to the next ones, for example, this one is the accept one, and also when we look at the others, we can work on this diagram. So for example, for state 2, using A, A is, as I told you, a terminal, so it's going to be a shift move. We jump to S3, so we are going to write S3. Using B, it jumps or it shifts using to 4, so we are going to write S4. And using non-terminal, we have, I think, a move to 5, so we are going to write it like here. And we are going to write all of them as I told you. And here we can see that I4 is I4, I5, and I6 are reduced ones. So these are the reduced nodes. And previously I have said that the the augmented grammar helps us to know the ending or the accept one. So instead of writing here the reduced one, we are going to write the accept here. We are going to jump from state 1 to using dollar sign here. So we are in the state 1 here, right? So when we get that using the S prime, we are going to accept the data because the next it represents the dollar sign, which accepts the value. So this is how we write it. So to clarify it more, this is the table. You can practice it by looking at the graph. So after this, let's have an example that has an input AA, BB, and using this table or LR table, we are going to check if the parser parses is this grammar, this input or not. So this is our table that we have derived earlier. So this is how it looks in the buffer. And we are going to have AABB and the dollar sign at the end. And in the stack, this is going to be an empty stack. So it's going to only have a dollar sign. So what we are going to do is first look at the stack that we have, and the last point is going to show us or direct us to the state that we are in. So currently it's empty, so meaning that we are in the first stage and the input buffer is A. So if we look at it in the first state or in the initial state, when we get an input of character A, it says to shift to 3. So we are going to write shift A3 here. And we are going to pop up this A to the stack. Now we are going to look at 3 and look into the input. So our step 3 says that to shift A. Currently we have A, so in the state 3 it says to shift again to 3. So we are going to pop up A again, and this is how it looks. Now we are in the state 3, and our input is B. So if you look at it, it says that to shift to S4, or I mean B4. So this is how we do the parsing in the LR. So now we are going to pop up B again, and we are going to look at the state 4 here, and our input buffer is B, so we are going to look at B. So it says to reduce 3, so we are going to reduce R3 by using the grammar. We are going to reduce this B into A, or we are going to transform it to A, reverse it. You can call it reverse. Now we have this. When you transform it, we have A6. Next, we have an input B and an A6 here. In the state 6, when you go to B, when we go get B, it says to reduce to 2. And we have the grammar here that serves us the right one. By doing all this, at the end, we reduce all of the values, and in the end, we are going to accept, because at the end we are going to get S, or our initial input, by reducing all the values. First we shift them all, then we reduce them, or we reverse the production, and we get the non-terminals, and at the end we get the S, or our starting symbol. That time we say that it's accepts, or our parser finishes the parsing, so it accepts this. If you look at the grammar, I mean the diagram from this, we can create our tree by looking only on the stack values. If you look at it, we have S1 here at the top, S here, then A2 and A5. Just we can pick the A's from here, and first we are going to transform one of the A to B. So we are going to get A and B here, A and B, this B, and then we are going to again transform this A to this AA, like this, and also here we are going to transform this A again to AA, and in the end we are going to transform this non-terminal to terminal B, so we can get the parse tree just by reverse working the table, or the stack of the LR table. Using the grammar, construct an LR parsing table and check if the input is acceptable. In the left side, we have the grammar, and in the right side, we have the input string. And remember to work all the procedures that are required to construct the LR parsing. This question asks us to build the LR parsing table and check the given inputs that we have. And an LR parsing table is a bottom-up parsing table, so it will be different from our LR parsing table that we have seen earlier. So let's pick one of the questions and look at how it works. The first thing that we have to do is create an augmented production. The augmented production helps us to find the ending, or when we find this E prime produces E, it's going to accept our value, meaning that we are going to find the star symbol, or our given general grammar that we have here. So we are going to create the augmented production. Then next to that, we are going to create the canonical collection of items. First, I created this canonical collection of item. The first one, it's going to be multiples. So we are going to look this canonical collection of items using diagram next. So this is how it's going to look like. So we have the first canonical collection of items like this, and we have around 8 canonical collections. So what we are going to do is we are going to shift this dot to the next, and if there is a non-terminal next to it, when we shift it, we are going to write the non-terminals values next. So if you see here, by using a when we shift this value, we are going to find this, and since there is no non-terminal to the right side, we are going to stop there. And also for the t and for the f, and later we have the values we are going to shift from left to the right, and we are going to find a non-terminal e. So while doing so, we are going to also import the values of non-terminal and its all other values also like this. So by doing so, we are going to create the data flow diagram like this, and we are going to give them the state values: state 1, state 0, 1, 2, 3, 4, 5, 6, 7, and so on. So what we are going to do is when we jump from one state to the another using terminal, we are going to say shift, and when we go using non-terminal, it's going to be radius. So by using the data flow diagram, we are going to create the LR parsing table, and this is how it's going to look like, the LR parsing table. So from here now we can check the input string if it's accepted or not. So when we do the table of the checking using the stack and input buffer, this is how it's going to look like. First, we are going to have an empty stack because we are using the bottom-up parsing. At the end, we should get the e prime or the augmented productions first start. So when we find this, as I said, we are going to accept the values, and by doing so like this, now we can check that the given input string is accepted using our grammar. Hello everyone. In this section, we are going to look at semantic analysis. So without further ado, let's jump into it. So what's semantic analysis? In simple terms, semantic analysis is the phase in compiler design that checks if the syntax structure constructed in the programming drives any meaning or not. Semantic analysis is the crucial phase in the process of compiling a programmed language. It focuses on understanding the meaning of the source code beyond its syntactic correctness. The primary goal of the semantic analysis is to ensure the program makes sense and adheres to the intended semantic or programming language. So, semantic analysis is also known as the context analysis. It is a phase in the compilation process where the compiler examines the meaning of the source code to ensure the logical and meaningful correctness. It goes beyond the syntactic structure and checks for adherence to the intended semantic of the programming language. So if you look at some example now, let's say that we have an int a equals with a string named value. Though this should not be an issue in the lexical and syntax analyzer phase, as it is lexically and structurally correct, but it should generate a semantic error. Because, as you see it here, we declared a as an integer, but we gave it a value of a string. So before the semantic analysis, it is correct when we look at it structurally. So it will pass the lexical and syntax analysis. But in the semantic phase, it is going to generate an error because, as I said, the semantic analysis is going to look at the meaning of the given string. So this is by false when you look at it in semantic analysis. It should be a number here, 1, 2, or something like that, not a string. So when we look at the key objectives of the semantic analysis, the first one is type checking. One of the fundamental aspects of semantic analysis is type checking. It ensures that the type of the expression and the operation in the program are consistent with the language rules. For example, it verifies that you don't add a string to an integer or attempt to call a function with the wrong number of type of arguments. We have seen that it would generate an error when we try to give a string value for an integer. The next one is scope analysis. Semantic analysis involves determining the scope of variables and resolving reference of variables and symbols. This includes identifying a variable declaration, ensuring proper scope rules, and resolving names to their corresponding declarations. The next objective of the semantic analysis is declaration checking. The compiler checks that the variable and the functions are declared before they are used. It ensures that a variable is not used before it is declared within its scope and that the functions are properly declared and defined. The next objective of the semantic analysis is semantic error detection. Detecting and reporting semantic errors is an essential aspect of this phase. This includes identifying the issue that might not be caught during the syntax analysis, but could lead to logical error or unexpected behavior in the executed program. The next objective of the semantic analysis is the structural constraints. Ensuring adherence to structural constraints imposed by programming language, such as correct use of control flow statements, proper loop termination condition, and valid function return types. And the last objective of semantic analysis is attribute checking. Analyzing and verifying attributes associated with the language constructs. This may involve ensuring that variables are used consistently, verifying the correctness of the function calls, and checking the validity of the expression. So from these key objectives that we have seen earlier, we can know that the semantic analysis is also one of the essential parts in the compiler design. So what are the semantic errors that we may find while working? So the semantic error that we get may be a type mismatch, as we have seen. For an integer giving a string, we give a type mismatch. Undeclared variable, for example, if without declaring a variable, for example, without giving int a is equal to 5, without saying that, if we just say a is equal to 5, it will give us undeclared variable error. Reserved identifier misuse, or for using identifiers that are used in the higher level, would cause an error also. Multiple declaration of variables and accessing an out of scope variable. This all would cause a semantic error. This won't cause a lexical and syntax error in the parsers, but it will be detected in the semantic error. So this is a crucial place to check the meaning of the string that is passed. So when you see the importance of the semantic error, the first one is error prevention, as we see it here. Semantic analysis plays a crucial role in preventing logical errors by catching issues that might lead to an incorrect program behavior. This helps improve the robustness and reliability of the compiled code. And the next one is optimization opportunities. By understanding the semantic of the program, the compiler can identify optimization opportunities, such as constant folding and decode elimination. which can enhance the efficiency of the compiled code. And the next one is standardization. Semantic analysis enforces adherence to the language specification and standards, ensuring the consistency and the predictability in the behavior of the written language. So, in general, the semantic analysis is the vital phase in compiler design that ensures the program not only adheres to the correct syntax, but it carries the intended meaning of the programming language. Through type checking, scope analysis, and detection of semantic errors, the compiler contributes to the production of reliable and optimized executable code. Next, let's see the syntax-directed translation, which is a crucial place in semantic analysis. This syntax-directed translation refers to a method of compiler implementation where the source language translation is completely driven by the parser. The parsing process and the parse trees are used to direct the semantic analysis and the intermediate code translation of the source program. We are going to look at the parsing tree that we have designed earlier in the parsing phase, and we are going to use it in the syntax directed translation. And this syntax directed translation can be separate phase of compiler, or we can augment the CFG or our grammar with the information to control the semantic analysis and translation process, such as grammars are called attributed grammars here. Now let's see the syntax of the direct definition. Or the syntax directed definitions are a generalization of context-free grammars in which the grammar symbols have an associated set of attributes. Productions are associated with the semantic rules for computing the value of the attributes. So when we write the semantic or the syntax directed code, first earlier we may have this production that we have A produces A plus T, but in the semantic rule we are going to write the value. So we are going to write it like this: E1, the E1 value is equal to E2 value plus T's value. So this is how we write the semantic rule in this phase. Self-formalism generates annotated parse tree, where each node of the tree is recorded with the field of each attribute. We are going to see this annotated parse tree later. Let's say that we have these syntax rules. So how do we check the semantic rules of this syntax? So what we are going to do is we are going to look at the values of each production that we have. So we are going to write it like this: E produces E plus T, and in the semantic rule it is going to be represented as E1's value is equal to E2 value plus T's value. So the addition of these two values is must be equal with this value. This is the basic principle in the semantic rule. So we are going to write all the non-terminals like that, and when we find the actual meaning, the terminal in our production, what we are going to do is we are going to write the lex value or the lexical value inside the ID or the actual value there. So with using the previous production rule, if we change this given string, we are going to get a tree and we are going to parse it, and from that parse tree we can get the annotated graph here. So this is how it's going to look. We are going to first design our graph based on the parsing that we have seen earlier, but after that what we are going to do is we are going to change the values of each node and each tree. So in the end of each tree where we have the terminals, so we are going to change the actual lex values using them, and as you see that when we reduce it to the non-terminal is going to take its value, because we said if you look at previous the production, as we said that f produces an id, so when we reduce it, the id value must be given to the f value. By doing all that in the tree that we have here, we can get the values. So when we go to the node in here, what we are going to do is we are going to multiply 3 by 5, because we have the in the parsing tree we have the terminal that says multiply, and this is what we do. We are going to look at the meaning of the grammar that we have. So we are going to multiply it, and we are going to get 50 here. So this is how we are going to write, and also in the right side we are going to reduce the values from terminals to non-terminals, and at the end we are going to add these two values. If you are going to add it directly, we are going to get 19. Also, using the parse tree in the syntax direct translation, we get the correct value of 19. So this is the annotated graph that we have here. Now let's look at the type checking. There are two types of type checking that we have. The first one is the static checking, when a compiler must check if the source program follows semantic conventions of the source language. This is called the static checking. And the next one is dynamic checking. And this is executed during the execution of the program. So the two differences, the static one checks the source program follows the semantic conventions of the source language, and the next one is the dynamic one is executed when the program runs. So let's see the type checkings. So we have the first we have the type checks. So in the type checking we are going to reach the first one is type check, which checks if an operator has the right type of operand. The next one is flow of control checks. In here, the statements that cause the flow of the control to leave the construct must have the same place to which the transfer of the flow of the control. For example, a break instruction in C that's not an enclosing statement. The next one is a uniqueness check. There are situations in which an object must be defined exactly once. And for example, in Pascal, an identifier must be declared uniquely. And also in other ones, if we use the variables, for example, like const and something like that, they must be unique when we declare a variable. The next one is name related checks. Sometimes the same name must appear two or more times. For example, in ADA, a loop or a block may have the name that appears at the beginning and at the end of the construct. So these are the things that type checking is going to check. So the type checker is a module or a compiler devoted to type checking. So for example, let's look at some task. The operator mode is defined only if the operands are an integer. If it's not an integer, then the type check is going to give us an error. But the operator mode must be only defined during an integer. And indexing is allowed only in array, and the index must be an integer. So you can't use a float number in the indexing. This is also going to be checked in the type checking. And a function must have a precise number of arguments, and the parameters must have the correct type. The type checker checks all these things or all these tasks. Now let's see types of types. So what kind of types that we have in our compilation? The first one is the basic types, and the next one is constructor types. The first one is the basic types are atomic types that have no internal structure as far as the program is concerned. So they include types like integer, real, boolean, character, and enumerator types. So these are basic types that are given by default, And in every programming language, we have these types. And the next one is constructor types. These are types that are constructed using the basic types. So they include arrays, record sets, and structures constructed from the basic types or the constructor types. And pointers and functions are also the constructor types. So now let's see the type system. It is a collection of rules for assigning type expression to the various parts of the program. Type systems are specified using the syntax-directed definition. And a type checker implements a type system. So we are going to say a program is a sound type system where the program that passes the static type checker cannot contain runtime type errors, such as languages are said to be strongly typed languages. Now let's see the equivalence of type expressions. There are two types of equivalence. The first one is structural equivalence and the next one is name equivalence. So we are going to say two types of expressions that are structurally equivalent if they have the same basic types. For example, integer is equivalent only for integer, and the next one is formed by applying the same constructor to structurally equivalent types. For example, pointer is structurally equivalent to pointer, and the second one is name equivalence. So we have name equivalence between two type expressions if only if they are identical, meaning that, for example, we can't say that 1 and 2 are name equivalent because they are not identical, but in structure they are identical because they have the same type and they are formed by applying the same constructor to structurally equivalent types. When you see this example, these two are both pointers. This ptr and asterisk integer, they represent pointer. But in the first one, in the structure equivalence, they are structurally equivalent. But in the name equivalent, they are not equivalent because they are not identical. This is written in this form and the second one is written in this form. So this is what you say the equivalence of an expressions. Is the given statement semantic correct? If there is a semantic error, explain the reason why. In this question, we are tasked to check the given statements if they have semantic error or not. So let's start from the first given statement. We have int result is equal to 10 divided by a string 2. This quotation represents a string, so this 2 is not an integer. So it would have a semantic error, which is a type mismatch, because we are using string in int. Next, we have a float result is equal to 5 divided by 2. So as you see it here, the float represents a value that have a decimal point. So when we divide 5 by 2, we are going to get 2.5. So the float can represent this value. So it doesn't have no issue. Next, we have int x is equal to y plus 3. This statement looks correct, but there is one issue. We don't know the value of y. So since we don't know the value of y, it's going to have an error, semantic error, which is undeclared variable. And in the int, we have this int result is equal to calculate sum 5 and 3. And as you see here, we have going to have an error, which is the functional call compatibility, because we have a string here. This 5 represents a string rather than a number, so it would have a function called compatibility issue. Hello everyone. In this section, we are going to look at the intermediate code generation. So, without further ado, let's jump into it. In the process of translating a program in a given source language into the code for the given target machine, a compiler may construct a sequence of intermediate representation, which is an intermediate code. Intermediate code generation is the phase in the compiler design process where the compiler generates an intermediate representation of the source code. This intermediate code serves as an abstraction between the high-level source code and the target machine code. The primary purpose of the generating intermediate code is to simplify the complexity of the source code for further analysis, optimization, and translation into the final machine code. So as you see it in the graph shown below, there are two parts in the compiler, which the first one is the front end and the next one is the back end. The front end includes the lexical analyzer, parser, static checker, and intermediate code generator. Once the intermediate code is generated, the next phase is in the backend or the code generator. The front end translates the source program into an intermediate representation, and the backend generates the target code from the intermediate representation. Some compilers may not have an intermediate code generation, meaning that after the parser, they directly generate the target machine code. But having an intermediate code is very essential in the compiler design. So most of the time, this intermediate code appears in all compilers. So let's look at the intermediate code generator. So when we look at the use of machine independent intermediate code or intermediate code generator, if it is machine dependent, meaning that it doesn't have intermediate code, it's going to directly generate the target machine after the target machine code after the parser. The machine intermediate independent the machine in the independent intermediate code generator has more advantage than the previous one because retargeting to another the first one is retargeting to another machine is easy, meaning that if for example if you are translating a C++ code to, for example, let's say a machine code, it's going to pass through the compiler, and if our compiler have an intermediate code, we would have a simpler code that is very easier to translate to another code. So if we change to translate that C++ code to, for example, let's say Java, we are going to start from the intermediate code that is generated rather than coming back from the initial phase to translating back. So retargeting to another machine is very easy. The next one is it simplifies the complexity of the source code for further analysis, or when you see the abstraction level. Intermediate code is more abstract than the source code, but less abstract than the target machine code. It captures the essential features of the source code while removing some of the syntactic and semantic complexities. The next one is optimization can be done on the machine independent code. The intermediate code provides an opportunity for the compiler optimization. Before translating the code into the final machine code, the compiler can apply various optimization techniques to improve the efficiency and the performance of the given program. The next one is facilitation of analysis. Intermediate code facilitates various analysis during the compilation process, such as control flow analysis, data flow analysis, and optimization analysis. These analyses help the compiler to make informed decisions about the code restriction and optimization. The next one is portability. Generating an intermediate representation enables the compiler to separate the concern of the source language features from the intricacies of the different target architectures. This enhances the portability of the compiler, allowing it to generate machine code for multiple target platforms from the same intermediate code. Next, ease of translation. The generation of intermediate code simplifies the translation process from the source code to the target machine code. The compiler can focus on translating an abstract and optimized intermediate code rather than dealing directly with the complexities of the source code or target architectures. And in the end, we have types of intermediate code. The common forms of intermediate code include three-address code, quadruples, and abstract syntax tree. Each form has its advantage and chosen based on the requirements of the compiler and optimization techniques it intends to apply. So, in summary, intermediate code generation is a crucial in compiler construction that involves creating an abstract representation of the source code. This representation enables further analysis and optimization before the final translation to target machine code. Next, let's look at the intermediate language that you have. There are different types of intermediate language that you have, and the first one is the tree form. And in the tree form, you have abstract syntax tree, direct acyclic graph, and in the linear form, you have notations, especially the post notation, and the three address code. In the three address code, we have quadruples and triples, and we are going to look at each of them one by one next. Let's see directed acyclic graphs. Like the syntax tree for an expression, a directed acyclic graph has leaves corresponding to atomic operands and interior codes corresponding to operators. The difference is that a node n in directed acyclic graph has more than one parent, if n represents a common subexpression. In syntax tree, the tree for a common subexpression would be replicated as many times as the subexpression appears in original expression. Thus, directed acyclic graph not only represents expression more clearly, it gives the compiler important clues regarding the generation of efficient codes to evaluate the expressions. So, directed acyclic graphs are often used to represent expressions and relationships between the sub-expressions. Directed acyclic graphs are an effective data structure for optimizing and generating intermediate code by capturing common sub-expressions and avoid redundant computations. So, as I said, now the node can have more than one parents, and we are going to look at it next. Let's say we have this expression that we have. So using the directed acyclic graph, we can represent it like this. And as you see it here, some of the strings have more than one parent, as you see it here. The leaf of A, the leaf of A has two parents because A appears twice in the expression. Here and here. More intensively, the two occurrences of the common sub-expression B minus B minus C are represented by one node. The node labeled as like this minus sign, B minus C. Since we are using B minus C twice, this expression is shared between this side and to the right side also. That node has two parts representing in two uses in the sub-expression. A times B minus C and B minus C times 3. Even though B and C appear twice in the complete expression, their nodes each have one parent, since both uses are in the common expression B minus C, in the context of compiler design and intermediate code generation. So we can clearly see that some of the use of the intermediate code expression of the directed acyclic graph from this graph. The first one is expression representation. Each node in the directed acyclic graph represents an operand and an operator in expression. And the edges or the directed edges represent the flow of data or control between the nodes. Next, the common subexpression elimination. As you see it here, the directed acyclic graphs help in identifying and eliminating the common subexpressions, where the same expression appears multiple times in the code. So here, this can be an example because b minus c is shared between two expressions here. By representing expression in directed acyclic graph, redundant computation can be avoided, leading to more efficient code. And the next one is efficient code generation. Because as we say that there is a reuse of the components, so it will be very efficient using the directed acyclic graph. And the other one is minimization of operations. By identifying common sub-expressions, the compiler can minimize the number of operations needed to compute the final result. And at the end, we have optimization opportunities. There is something called constant folding. Constant expressions and arithmetic operations can be folded into single node in directed acyclic graph, reducing the number of instruction and the general code. And the next one is strings reduction. Operations involving power of 2 or multiple of 2 can be optimized to use shifts, and directed acyclic graph helps identify such opportunities. If you say like this, so let's see the properties of the directed acyclic graph. The first one is acyclic nature. The acyclic nature of directed DAG or direct acyclic graphs ensures that there are no redundant computations or circular dependencies in the representation of expression. The next one is topological ordering. This DAG or directed acyclic graph can be topologically ordered, allowing the compilers to generate code in sequence that respects the dependencies between expressions. And the third one is node labeling. Nodes in DAG may be labeled with information such as variables, names, constants, or operations. And the last one is multiple representations. And we can know that there is more flexibility in DAG. And different DAGs can represent the same expression. And the compiler can choose the most efficient representation based on the optimization goals. So, in summary, directed acyclic graphs play a significant role in compiler design, especially during intermediate code generation. They provide a concise and optimized representation of expressions, enabling the compiler to eliminate common sub-expressions and generate more efficient code. Abstract syntax tree. The abstract syntax tree is a hierarchical tree-like data structure that represents the abstract structure of the source code in programming language. In intermediate code generation, an abstract syntax tree is a crucial intermediate representation. So what differs the abstract syntax tree from the direct acyclic graph? So here, each node in the tree corresponds to specified syntactic element. The nodes of the tree represent the language constructs such as expression, statement, and declaration. The edges between the nodes represent syntactic relationship between these constructs. And also, just like the DAG or direct acyclic graph, the AST eliminates certain syntactic redundancies. Let's see this with example. So this is the example that we have. The syntax tree or the abstract tree is a condensed form of parse tree useful for representing language structures. So if you see here, this is the parse tree for a plus b in the given grammar. We are going to have an n-terminal called e, and it's going to give us a, and also here, as you see, operations also have their own leaf. But in the abstract tree, the operations are going to be the nodes, and they are going to connect two terminals like this. And from this we can find the characteristics of abstract syntax tree. The first one is hierarchical structure. The AST represents the hierarchical structure of the source code, capturing the relationship between different language constructs. Each node in the tree corresponds to specific syntactic element. And the next one is the nodes and the edges. The nodes of the tree represent the language constructs such as expressions, the statement and declarations. The edge between the nodes represents syntactic relationship between these constructs. As you see, there is a relationship between a plus b, and it is represented by this graph. The next one is elimination of redundancies. The AST eliminates certain syntactic redundancies present in the concrete syntax of the source code. For example, parentheses in expression are not explicitly represented in AST because the tree structure itself conveys the order of the operation. So as you see, the e's are eliminated from the given tree. Also, the parents are going to be eliminated because the tree is going to represent itself. So there is not going to be a parenthesis. The next one is the abstraction of concrete syntax. The AST abstracts away details of the concrete syntax while preserving the essential structure and semantic of the code. It is more concise and manageable representation for subsequent compiler phases. Now let's see the role of AST in intermediate code generation. The first one is representation of syntax. The AST serves as the intermediate representation that captures the static or the syntactic structure of the code more directly than the concrete syntax. The next one is simplification of analysis. During intermediate code generation, the AST is often traversed to simplify and transform the code. This simplification step involves the removal of certain static complexities and the extraction of relevant information. As I said earlier, the parentheses are going to be removed, and also some of the non-terminals, as you see, are going to be removed because, as I said, the nodes are going to be the operations most of the time, and it's going to be more simplified. The next one is expression evaluation. ASTs are particularly useful for representing expressions. They provide a clear structure of understanding the order of operations and the relationship between the operands and the operators. It's as we have seen in the graph, the relationship is more clarified. Next, the code optimization. The AST is foundation for various optimization techniques. Compilers optimization often involves analyzing and modifying the structure of the AST to improve the efficiency of the generated code. And the last one is going to be source-to-source code transformation. The AST is a convenient representation for applying source-to-source transformation. This transformation can involve rewriting parts of the code in more efficient or optimized form. So, in summary, an abstract syntax tree plays a central role in intermediate code generation phase of a compiler. It provides a structure and abstract representation of the source code, enabling a subsequent phases to analyze, optimize, and generate intermediate code more efficiently. Next up, let's see notations. In the context of intermediate code generation, notation is often used to represent expressions in a way that eliminates the need for parentheses and clarifies the order of operations. Different notations are used to represent expressions, and these notations are prefix notation or Polish notation. The second one is infix notation, and the third one is postfix notation. In prefix notation, or the first one, we can call it also Polish notation. The operator precedes its operands. Every operator appears before its operands, and there is no need for parentheses to indicate the order of operations. Polish notations is a mathematical notation in which every operator follows its operands. So let's see an example. Okay. Here we have A plus B times C. In the Polish or prefix notation, it's going to look like this. The Polish notation can be used to represent the expression in a form that is easy to parse and analyze. So when you see this example, using the Polish expression, what we have done is the operand is going to come first. So when you do that, when we do this algorithm, the first thing that we do is B times C because of the board maths theory. B times C, then the operand is going to come into the left side, then we are going to add it with A. So when we add it with A, the plus sign is going to be on the left side as you see it here. But for the B times C, the operand is on the left side for B and C. Using Polish notations can simplify the parsing and evaluation of expressions because it eliminates the need for parentheses and clearly indicates the order of operations. These characteristics make Polish notation particularly useful in the context of intermediate code generation, where the goal is to represent expressions in a form that facilitates subsequent analysis and translation. The next one is the infix notation. In infix notation, the traditional mathematical notation, operators are placed between their operands, and parentheses are often used to indicate their order of operation. When we see the example, for the given example, the infix notation is going to be like this. It's going to direct us to which one we should first do, and it's going to give it a parenthesis. So it's not mostly used in the intermediate code generation, but it has its own advantage because it directs which operation comes first. Most of the time we use the prefix or the postfix notations in the intermediate code generation. And the third one is postfix notation. We can call this postfix notation also reverse Polish notation or RPN because we are going to make the reverse of the prefix notation. In the postfix notation, the operator follows its operands. Both Polish and postfix notations are stack-oriented and can be efficiently evaluated using the stack data structure. When you see this example, for the given expression, the postfix notation is going to look like this. The first thing that we have to do is the multiplication in this grammar. So we are going to multiply B with C, and the operand is going to be in the right side of the given grammar. And okay, the next we are going to add it with B type BC. So the plus sign is going to be in the rightmost side of the given grammar. So this is how we do it. Postfix notation is a practical for an intermediate representation, as the operands are found just before the operator. Both Polish and postfix notations are stack-oriented, as I said earlier. And the postfix notation is linearized representation of the syntax tree. We can get the syntax tree if we look into the postfix notation in linear form. The postfix is tag friendly and allows for straightforward translation to machine cores. Postfix notation is commonly used in some stacks-based virtual machines. The use of notation or similar representation may be part of the strategy to simplify the expression parsing and facilitate subsequent optimization or translation process. So the main thing in the notations here, especially in the postfix and the prefix, they, there's not going to be a parenthesis, and the operands and the operators are going to be in the left and on the right side based on their coming. Let's see this example on the postfix notation. We have to transform this infix expression to the postfix notation. So by default, the intermediate code generator uses the stack to change this expression or this infix notation to the postfix notation. How it does it is first initialize the empty stack to store all the operators. Then it scans the expression from the left to the right, and for each operand and or operator, if it's an operand, it outputs it. If it's an operator, it pops operator from the stack and output until the stack is empty, or the top operator has lower predecessors. Then push the current operator onto the stack. And at last, after scanning the expression, pop up any remaining operators from the stack and output them. This is how the intermediate code generator uses the principle. But also we can change this infix expression to the postfix by using the mathematical operation, which is the BODMAS operation. So it says body of division, multiplication, addition, and subtraction. So we are going to focus on first the parenthesized ones, then the division, then multiplication, and addition and subtraction. So the first thing that we have to do is we have to change the each individual given parentheses to the postfix notation. So a divided by b is going to be transformed into ab and the operator, and we are going to leave this times c minus there, and then we are going to target also the d times e, and we are going to change that one to d times de times, and we are going to leave the plus f there. After that, what we can do is we have the multiplication here, so we are going to multiply c with ab hyphen or division operator. So what we are going to get is ab division operator c, and the middle multiplication is going to be on the right side, and the minus is going to be left there, and de times plus and plus f is going to be like that. Next, what we are going to do is we are going to subtract ab divisor operator c times by this one. So what we are going to get is we are going to shift this one to the left side and put this to here. And at the end, we are going to add f to the expression that we have here. So when we do that, the f is going to be stored here, and the plus sign is going to be stored in the right smooth state. So this is the postfix notation of the given infix expression. This is how we change the given expression to the postfix expression. Change the given infix expression to the postfix notation. we have this expression and we are tasked to change it to the postfix notation. To answer this question, what we have to do is we have to remember the given instruction to change the postfix notation. The first one is we can use the left to right in the stack method, or we can use the BODMAS theory. So while doing so, first we are going to target the brackets, then based on their mathematical preference, we are going to work on them. The first thing that we have to do is change this f divided by g to the postfix notation, like this. And after that, we are going to change all these three given expressions like this. A minus b is going to be changed to ab minus, and c minus d is going to change cd minus, and also this one we are going to look at it as a whole, and e plus fg x operator is going to change like efg operator and again operator. Next we are going to multiply these two and we are going to have ab minus cd minus times operator plus and the rest. After that we are going to add this expression with this one. While doing so, we are going to get this expression or this postfix notation. So this is the answer for the given infix expression. Now let's see three address code. A three address code is a type of intermediate code that represents instructions with at most three operands. Each instruction in three address code performs a simple operation on one, two, or three operands, and typically corresponds to a single operation in the source code. So three address code is designed to be a low-level representation that simplifies the complex expression and statements, making them a simpler and to subsequent optimization and code generation. As I said, the three address code has three operands. In here we have 3x, y, z, and the operation is going to be one operator. So in the three address code, there is no custom or built-up arithmetic operator that's permitted. You are going to use the general plus, minus, divide, and subtract only. And only one operator at right is possible. So x plus y plus z is not allowed. So one operator in the right side only is possible. Here the operation, I mean. For example, let's see this given expression. We have a minus b plus c. So in the three address code, we are going to follow the BODMAS when we do our operations. So we are going to change this one to three address code. And it's going to look like this. First, we are going to add b plus c and give it t1 value. And for the t2, we are going to give a minus t1, where t1 is declared here. So this is how we use the three address code. And as I said, it's going to use only three operands. 1, 2, 3, and only one operator, as you see here. Let's see another example. Here we have a plus b minus in bracket b plus c, then closed, times b minus c. And don't forget to use the BODMAS theory when we do this one. So first let's start from the b plus c and assign it to t1. And for the t2, let's use b minus c. After that, let's multiply b plus c by b minus c. So how we do it is that T3 is equal to T1 times T2. And for the fourth one, let's add A plus B. And in the fifth, we can have T4 minus T3 or our subtraction. This way we can represent the 3 address code. So from this example, we can see the characteristics of the 3 address code. The first one is operation with 3 operands. Each instruction in 3 address code involves a maximum of 3 operands. 1, 2, 3 in all of the examples. And it's very simple. We can see the simplicity. 3 address code simplifies the complex expression and statement found in high-level programming language to, as you see, it's the simplified way. The next one is explicit representation. The representations is explicit and concrete, making it suitable for subsequent analysis and translation to the machine code. Next up, the assignments. Many instructions involve assignments where a value is computed and stored in a variable. Here we have assigned b plus c to t1. And for the fifth one, we can see that the characteristics of the 3 address code is the control flow. 3 address code can represent the control flow constructs such as conditional statements and loops. And in the end, the common operations include arithmetic operation, assignments, or conditional branching and memory operations. Let's see now the advantage of the 3 address code. So the first one is the simplicity that I said earlier. It's simple and easy to work with and making it suitable for analysis and optimization. The next one is direct mapping to machine code. 3 address code instructions can be more easily translated to machine code because as we see them, they are very easy to understand. Next, we have the straightforward register allocation. The limited number of operands simplifies register allocation. So in general, the 3 address code serves as the bridge between high-level source code and the target machine code, providing a structure and explicit representation for subsequent compiler phases. Next up, let's see the representation of 3 address codes. We can represent using the quadruples, triples, and indirect triples. The quadruples have 4 fields: operand, argument 1, 2, and the result. This is the common one that we have seen earlier, and this is the most used one. The next one is the triples, which have the 3 fields, and we are going to look at them next. And also there is something called indirect triples also. We are going to look at each of them in the next section. Now, let's look at quadruples. The description of 3 address instruction specifies the component of each type of instruction, but it doesn't specify the representation of these instructions in data structure. In compiler, these instructions can be implemented as objects or as record fields for the operator and the operand. And there are 3 representations that are quadruples, triple, and indirect triple. The first one is quadruples. A quadruple or just a quad has 4 fields, which are op or operator, argument 1, argument 2, and the result. The op field contains the internal code for the operator. For instance, the 3 address instruction x is equal to y plus z is represented by placing the plus in operation or operator, y in arg1, z in arg2, and x in the result. And while doing the quadruple, there are some exceptions. The first one is instructions with unary operator like x is equal to minus y or x is equal to y, don't use the arg2. And for copy statements like x is equal to y, or operator when the operator is equal sign, while most of the operations, the assignment operation is implied. And the second exception is operators like params use neither arg2 nor result. And for the third one, conditional and unconditional jumps put the target label in result. So let's look at to some example how to implement the quadruples. Let's say we have this given expression that we have, and the first thing before jumping into the quadruples is to transform this expression to the three address code. So what we have to do is first specify the minuses in the given expression. As you see here, we have b times minus c plus b times minus c. So the minus c can be represented like this. Then by doing all the three address code, we can represent the given expression like this. The special operator minus c is used to distinguish between the unary minus operator, as in minus c, from the operator minus operator, from the binary minus operator, as in normal b minus c or something like that. But this is different, so that's why we are using the minus instead of the minus. So, but we can represent it like that also. And one thing that you have to notice is that it has only two addresses from the given. There is no second arg as you see it here. So what we have to do is next we have to build a table, quadruple table, and this is how we do it. At the top or in the column, we are going to write the op or operator, argument 1, argument 2, and the result. And in the left side, we are going to have the steps. So the first step in the quadruples is this one. T1 is equal to minus C. And for the operator is going to be minus. And the argument 1 is going to be C. And T1 is the result. But there is no argument. And for the second one, when we see it, T2 is the result, and B and T1 are the arguments, and times it the operator. For the third one, T3 is the result, minus is the operator, and C is the argument one. For the T4, this is the result, and B and T3 are the arguments, and times it the operator. And for the fifth one, T5 is going to be the result, which is the combination of T2 plus T4. And at last we have our result A, which is equal to T5, and T5 is our first argument. Our operator is going to be the equal sign here, and A is going to be our result. This is how we represent the quadruples. The first thing when we get the expression is we have to create the three address code like this. By looking into the three address code, we are going to generate the quadruples like this. And at the top, we are going to write operator and two arguments that we have and the result. And by the way, these are the four. That's why it is named quadruples. Quad means four. So for readability, we use the actual identifiers like A, B, C in the field of the arguments 1 and 2 and the result, instead of the pointers to the symbol table entries. Temporary names can either be inserted into the symbol table like the programmer defined names, or they can be implemented as object of class temp with its own methods. So this is how we implement the quadruples. Next up, we have the triples. A triple has three fields which you call op, arc, and arc. And this is different from the quadruples because this doesn't have a result. Using the triples, we refer the result or an operation x or x operation y by its position rather than by explicit temporary name. Thus, instead of temporary t1 in triple representation, we would refer to the position, and parenthesized numbers represent the pointers into the triple structure itself. So let's look at example to understand more about the triples. And when we do the triples, the quadruple table is used primarily for temporary names. So let's use the same expression that we got from the quadruples. So what we have to do is we have to generate first the thread address code. Next we have to generate the quadruples table by looking into the thread address code. Then from these two we are going to generate the triples. As we said that it is different from the quadruples because it doesn't have a result and it's going to have the refers to the position rather than giving some temporary name like T1, T2, T3. So let's look into it. We are going to have three columns operation or operator, argument 1 and argument 2. And we are going to write the steps like this. Okay, the first expression that we have or the first grammar that we have is here. We have minus c. And from here we can see that the op is minus and the argument is c, so we are going to input minus c here. Next we have b times t1, so we are going to write in the operator part times and in the argument part b, but instead in the second argument, instead of writing t1, we are going to refer t1. So when we look at the t1 from the table, it has the address of 0, so we are going to write 0 in the argument 2 by looking at the actual address of the given temporary name. So on the third one we have minus c, and minus c is represented by t3 and it doesn't have argument 2, so we are going to write minus and c here. Next we have b times t3. Times is our operator, so we are going to write it here, and b is our argument 1. But t3, the position of t3 is 2, so we are going to write 2 instead of t3 in the arg2. And as I said, the parenthesized numbers represent the pointer into the triple structure itself, so we have to write the parentheses when we write the numbers. It represents the position. Next we have t2 plus t4, and plus is our operator, but t2 is 1 in the position 1 and t4 is in the position 3. And at the end we have a is equal to t5. Equal sign is our operator and t5 is in position 4. So this is how we represent the triples by using the table from the given expression. First we are going to generate the thread address code, then the quadruples, then by looking into the thread address code and the quadruples position, we are going to generate the triples table. Change the given expression to the quadruples and triples. We have this mathematical expression, and we are tasked to change this to quadruples and triples. To have the quadruples and triples from the given expression, we have to follow the instruction that we have seen earlier. The first thing is we have to create the three address code. So from this, let's create the three address code. First, we have T1, which represents minus b, or this negative b. Next, we have T2, which represents c plus d. And our T3 is going to be T1 times T2. And our last grammar is going to be a is equal to T3. This is our three address code. By looking this three address code, we can generate the quadruples table. So this is our quadruples table. We have the 4 columns: operator, argument 1, argument 2, and the result. And in here we have the position address. For the first, when you look at it, the operator is minus b and the argument 1 is b. We don't have the second argument, and our result is T1. And for the T2 is the result. C and D are arguments, and plus is the sign. And for the third one, T3 is our result. T1 and T2 are arguments. And times sign is the operator. And at last, we have A as the result, and equal sign is going to be our operator, and T3 is our first argument. This is our quadruples table. Now, by looking into the quadruples table and the serial code, we can generate the triples. This is how it looks, the triples table, and it doesn't have the results. That makes the triples differ from the quadruples. Instead of having the result like this, we are going to write the position, so this is the difference. Now first let's look at this given expression, which is minus b. Our operator is going to be minus, and the second argument is going to be b. Next we have c plus d. Plus is our operator, and argument 1 is c, and argument 2 is going to be d. And on the third one, we have T1 and T2, and these are these variables that we named them here. So instead of writing them, we are going to look at the position of them. So T1 is on position 0 and T2 is on position 1. So instead of T1 and T2, we are going to write their positions here, like this. And at the end, we have A is equal to T3, and T3 is in the position of 2. So we are going to write arguments in the first argument 2, and our operator is going to be equal sign. This is the triple table. Hello everyone. In this section, we are going to see runtime environments. So without further ado, let's jump into it. A compiler must accurately implement the abstractions embodied in the source language definition. These abstractions typically include names, scopes, data types, operators, procedures, parameters, and flow of control constructs. The compiler must cooperate with the operating system and other system softwares to support this abstraction on the target machine. To do so, the compiler creates and manages the runtime environment in which it assumes its target programs are being executed. This environment deals with a variety of issues such as layout and allocation of storage locations for the objects named in the source program, the mechanism used by the target program to access the variables, the linkage between the procedures, the mechanism for the passing parameters, and the interface to operating system. also input-output devices and other programs. So the runtime environment is a crucial component of the execution phase in the life cycle of a program. It consists of various elements that manage the execution of a program during its running time, ensuring proper memory allocation, variable scope, and function execution. The runtime environment plays a vital role in translating high-level code into executable machine instructions. So the runtime environment works in the runtime memory. As you see, this is the structure of the runtime memory that we have. And it consists of the code space, static data, stack, free memory, and heap. At the top, you have the code, and it's a memory location for codes that are determined at compile time. Next, we have the static data memory. This is the location of static data, can also be determined at the compile time. Next, we have data object allocated at runtime, and we can call that activation records. We are going to look about the activation records later. And we have the free memory that we have in order to, if our stack is larger or our heap is larger, we are going to consume this free memory. And at the last, we have the heap, and the heap helps us to store dynamically allocated data objects at runtime. For example, malloc area in C language use this heap most often. So to maximize the utilization of space at runtime, the other two areas, the stack and the heap, are at opposite ends of the remainder of the address space. These areas are dynamic. Their size can change as the program executes. These areas grow towards each other as needed. The stack is used to store the data structure called activation records, as I said, that generates during the procedural calls. We use the stack for the procedure calls and the heap for dynamically allocated data. Now, let's see the key components or the key aspects on the runtime environment. The first one is memory management. We can call this stack versus heap. The runtime environment includes memory segments, notably the stack and the heap. That stack utilized for managing local variables, functional calls, and control flows. And it follows last in first out structure or LIFO structure, while the heap supports dynamically memory allocation, allowing for flexible memory usage but may face fragmentation challenges. We are going to look at about stack and heap in the next topics also. Next, we have the activation records. This is activation score records is also known as the stack frames, and these activation records organize the execution of functions. They comprise the components like return address, parameter, local variable, and saved registers. Activation records are created and destroyed during functional calls, providing a structured way to manage function execution. Next, we have the managing scope. The scope determines the visibility and the accessibility of variables within the program. And we have static scope and dynamic scope. This static scope is decided at compile time. Variables that have fixed scopes. And dynamic scope is decided at runtime. Scopes that can change based on the call stack. Proper management of the variable scope is crucial for avoiding conflicts and ensuring the correct variable access. So if you say this much about runtime, so why is runtime crucial in our compiler course? So we have to know the first important thing about runtime is its memory allocation and deallocation. Efficient memory management is vital for optimizing program execution. The runtime environment ensures proper allocation and deallocation of memory, preventing memory leaks and enhancing resource utilization. Next, we have the function execution. Activation records facilitate the organized execution of functions. Managing the call stack ensures that functions are invoked and returned in the correct order, preserving the program's control flow. Next, we have variable scope and lifetime. Proper scoping rules are essential for maintaining the integrity of variables. The runtime environment governs the scope and lifetime of variables, preventing unintended conflicts and ensuring data integrity. Next to that, we have dynamic memory allocation. The heap, as part of the runtime environment, enables dynamic memory allocation. This is crucial for accommodating data structures of varying sizes and supporting features like pointers. And at the end, we have the adaptability across platforms. A well-designed runtime environment allows compiled programs to run on different platforms without modification. This adaptability is critical for ensuring portability and widespread applicability of compiled process. So, in a sense, the runtime environment bridges the gap between the high-level code written by the developers and the low-level machine instructions executed by the computer. Its proper design and management are pivotal for the correct and efficient execution of programs generated by the compilers. Understanding the runtime environment is the key to creating a robust and portable software. Now, let's see the memory management in runtime. We have talked about stack and heap in the memory allocation on the runtime. So the first is the stack. So what is a stack? A stack is a linear data structure that follows the last in first out principle. That means the last element added to the stack is the first one to be removed. Think of it like a stack of plates where you add or remove plates from the top, right? So in the context of runtime environment, the stack is crucial memory structure that follows the last in first out principle. It is a region of memory managed by the program's execution system, specifically designed to handle the dynamic storage and retrieval of data during the program execution. You can see from this diagram that this we can call this one as an empty stack, and we can push our programs to the stack like this, and when we push, the stack is going to fill, and when you pop out, meaning that our instructions are maybe they're or executed or something like that, we pop out from the stacks, and this is why we call it last in first out. The stack operates on the principle that last item or data or instruction pushed onto the stack is the first one to be popped off. As you see, the third one is the last one to be pushed, but it is the first one to be popped out. This characteristic simplifies the memory management and facilitates the efficient data access. So let's see the stack usage. The first one is local variables. The stack is primary storage location for the local variables within function. Each function call creates a new stack frame containing local variables, and this frame is popped when the function returns. The next usage of stack is the function calls. The stack manages the call stack, keeping track of function calls and returns. When a function is called, a new stack frame is pushed into the stack, and when the function completes, the frame is popped off. We are going to look at about this call, or we called it earlier that it's called the activation record, and we are going to look at it more next. Next, we have the control flow. The stack plays a crucial role in managing control flow. It stores return addresses, allowing the program to navigate back to the calling points after a function completes its execution. So it has more advantages like efficient memory access. The stack memory access is highly efficient due to its LIFO or last in first out nature. This makes it particularly suitable for managing functional calls and local variables. Next, we have the automatic memory management. The stack automatically allocates and deallocates memory for function calls, eliminating the need for explicit memory management by the programmer. And also it has some limitations like limited size. The stack is finite in size and its capacity is typically set during the program initialization. This limitation can lead to stack overflow if the stack becomes too deep due to extensive functions calls or large local variables. And the last usage is temporary usage. As a volatile storage space, the stack is not suitable for long-term storage. Data stored on the stack is automatically deallocated when the associated function completes. So, in conclusion, the stack is the fundamental component of runtime environment, providing an organized and efficient mechanism for managing local variables, function calls, and control flows. Its LIFO nature simplifies memory access, making it well suited for tasks where order and immediacy are critical. While advantageous for certain operations, its limited size is necessitates careful consideration to prevent the stack overflow issue in the program with the extensive function calls or large local variables. Understanding the stack's role is pivotal in designing efficient and reliable runtime environment. Now, let's try to implement the stack in our C++ code. As we have said, stack is a linear data structure that follows the last in, first out principle. This means the last element added to the stack is going to be the first one to be removed. So let's open our C++ code, and first let's select a language. Let's select C++, and let's start writing our code. The first language that we are going to import is, or the first library is, include stream. This library or provides the input and output functionalities. It includes the library like cin and cout for reading from the and writing the standard input and output streams respectively. And also it includes other facilities that we use in C++. So this is the basic library that we import most of the time. And the next library that we need is include vector. And we are going to use this library because in the stack we are going to use this dynamic array that grows or shrinks in size, and vector are part of the standard template library and they offer dynamic array like functionalities with additional features such as atomic memory management and various members functions and manipulation. So we are going to use this vector for our code. Now let's write our code. Type name t, and let's create our class stack. Let's use our vector here to create our stack. Next, let's have a public empty in order to check the if the stack is empty or not. Then return elements dot empty. If our stack is empty, it's going to return an empty. Next step, let's have a size module that checks the size of the stack that we have. So it returns elements dot the size. And one thing that you have to make sure is that C++ is very case sensitive, so you have to make sure everything is written correctly. And this helps us to push an element to our stack. Push back value. And also let's add a void pop in order to remove elements from our stack. So if we have to check first if it's empty, it's going to say elements dot popback. If it's not empty, we have used this operator or exclamation. If it's not empty, it's going to pop up the last element. Else, it has to give us some error message, right? So let's write the else value. It's going to give us error error stack is empty. Then end line. Now let's add the return to the top element of the stack. So t top const if it is empty. If it's not empty first, we have to check, right? Okay, close brackets. Then we have to return elements dot back. If it is empty, we are going to give an error message. Else std c error stack is empty. End line. And okay, there was some mistake here. It should be constant. Okay, after that, what we have to do is okay. Then we have to return empty, the default value, or throw an exception as needed. Now let's write our main function. Int main. Okay, first let's call our stack here, and let's create an int stack. Now let's push some values to our int stack. So let's call it int stack dot push, and let's add the number 10 to our stack. Okay, let's add another value to our stack. We are going to see the values with popping them out one by one. So first we push the value of 10, then 20, and at last 30. So the last element that we added was 30, so our top element is must be a 30 when we pop that. Int stack dot top. Currently we are looking at the top by using this function. Then end line. Next, let's pop another value. Int stack dot pop. This is going to remove the top value. Now let's see the output. See out the top elements after pop. Int stack dot top. And end line. Let's give it a return value of 0. Doing this. Now let's save our function like stack and make sure that it is saved as a C++ file. Okay, it's showing me an error because I missed int here. So now everything is looking fine. So what we are going to do is go to the right top and run the C++ file here. And let's use the G++ build. Okay, we are getting an error. It says that elements was not declared at first place. So, okay, I am plural. Okay, the error is here. I said element instead of elements. Now it should work now. Let's run it again. Mm, okay, I forget to add here also elements. So what you can do is first by clicking on Control F, you can find element values. This is one advantage of using the VS Code. So element is nowhere used now, so it should be elements. Let's save it now and let's run the C++ file. Now our file is executed. So let's go again and run it. So we get the value as you see it here at the, it says the top element is 13 because first the last element that we pushed was 13, then the top element after pop is 20. So we popped the stack one element, so 30 is removed now in this stage. So after this, the top element is going to be 20, so it's giving us a 20. So this is the simple way to, by using the vector, that we can create a stack element like this. Now let's see heap. A heap refers to a region of computer's memory that is used for dynamic memory allocation. Unlike a stack, which follows last in first out structure, a heap is more flexible and dynamic data structure that supports the dynamic memory allocation and the allocation during the runtime of a program. So the heap is the portion of the store that is used for data that lives indefinitely or until the program explicitly deletes it. When you see the heap structure, this is how it stores the data. Let's say we have an array and the heap is going to make its tree first. We have the root and the last node here. The root is going to be stored on the first array or array number 0, and the last node is going to be stored in the last array. So this is how the heap stores its data. So in the realm of runtime environment, the heap is critical memory segment distinct from the stack. It serves as dynamic storage area, allowing for flexible memory allocation and deallocation during the execution of the program. By looking at this graph, we can see the dynamic nature or characteristics of the heap. The heap is characterized by its dynamic nature, enabling the allocation and deallocation of memory at runtime. This stands in contrast to the stack, which operates in LIFO or last in first out basis. So when we see the usage of the heap, the first one is dynamic memory allocation. This is the crucial aspect of the heap. The primary purpose of the heap is to facilitate dynamic memory allocation, especially for data structures whose size are not known at compile time. Functions like malloc in C are commonly used to request memory from the heap. So we can see the advantage of the heap, like flexibility in memory allocation. Unlike the stack, the heap allows for dynamic and flexible memory allocation. This is particularly beneficial when dealing with the data structure whose size may vary during the program execution. Next, we have persistent storage. Memory allocated on the heap persists beyond the scope of individual functions or program blocks. Data stored in the heap remains accessible until explicitly deallocated. As I said, the data stored in the heap may last longer than the stack. Also, these things come with some difficulties. The first one is fragmentation issues. Over time, as the memory is allocated and deallocated on the heap, fragmentation may occur. This can lead to inefficient use of memory space, with free memory becoming scattered in small, non-contiguous chunks. And the next one is manual memory management. Memory allocated on the heap often requires a manual management, meaning that developers must explicitly deallocate memory when it is no longer needed. Failure to do so can result in some memory leaks. And at the end, we have the slower access time. Accessing memory on the heap tends to be slower than accessing the stack due to its dynamic and less organized nature. As we have seen the graph, it stores its data dynamically, so accessing your data faster would be a little bit difficult. So there are some considerations on the stack, like balancing flexibility and responsibility. While the heap offers flexibility, it places more responsibility on the programmer for managing memory. Proper allocation and deallocation practices are crucial to prevent issues like memory leaks. So when you see the use case, the heap is often employed for scenarios where data needs to persist beyond the lifespan of individual function, or where the size of the data structure is dynamic and unpredictable. In conclusion, the heap is vital component on runtime environment, providing a dynamic and flexible memory allocation mechanism. Its dynamic nature allows for versatile memory management, but developers must be mindful of the potential issues such as fragmentation and manual memory management responsibilities. Understanding the characteristics and trade-off of the heap is crucial for designing robust and efficient runtime environment. Now, let's see the activation record. An activation record is also known as the stack frame. It is a data structure that organizes and manages the execution of a function. It serves as a container for essential information related to the function call, ensuring proper execution and providing the structured layout to the call stack. When a function is called, it creates an activation record. You have to remember this one. When the function is called, it creates the activation record. Procedure calls and returns are usually managed by the runtime stack called the control stack. Each live activation has an activation record on the control stack. So when you see the phases in or the lifetime of activation record, it has three phases. That activation record have specific lifetime paired to the execution of associated functions. The first one is the creation. An activation record is created and pushed onto the call stack when the function is called. This process includes allocating memory for the local variables, parameters, and other relevant informations. The next one is the execution phase. During the execution of the function, the activation record serves as the workspace for the storing immediate results and managing control flow. And the last one is distraction. Once the function execution is complete, the activation record is popped out from the stack. This step involves deallocating memory and releasing the resources associated with the function call. So as you see it, using this diagram, first let's say we have an empty stack. So when a function is called, there is going to be a creation of the activation record that stores the data for the function, the important data for the function. Then after the execution, it will going to be distracted, or the distraction occurs after the execution of that given function. Until then, it will stay in the stack. Next up, let's see the visualization. Understanding the organization of activation records is aided by the visualization using the structure on the call stack. A diagram can illustrate the hierarchical arrangement of multiple activation records, such as the functions that are called and returned. So we shall conventionally draw the call stack with the bottom up, with the bottom of the stack higher than the top. So the elements in the activation record that appear lowest on the page are actually the closest to the top of the stack. I mean this one. This should be the top of the stack. And the contents of the activation record vary with the language being implemented. So here is the list of kinds of data that might appear in the activation record. Some of them may appear or some of them may not appear. So most of them it's volatile, but these are the common records that appear on the activation record. So let's see the first one, which is the temporary values. These are temporary values such as arising from the evaluation of expression in cases where those temporaries cannot be held in registers. Next up, we have the local data. These are the belongs to the procedure whose activation record this is. And we have next the saved machine status with the information about the state of the machine just before the call to the procedure. This information typically includes the return address or the value of the program counter to which they call the procedure must return, and the content of register that were used by the calling procedure and that must be restored when the return occurs. Next up, we have the access link. This may be needed to locate data needed by the called procedure but found elsewhere. After that, we have the control link, which points to the activation record of the caller. And after that, we have the returned values. The space for the return value of the is called the return values. If any, again, or not all called, the procedure returned a value. And if one does, we may prefer to place the value in the register for efficiency. And at the top, you have the actual parameters used by the calling procedure. Commonly, these values are not placed in the activation record, but rather in registers. When possible for greater efficiency, however, we show a space for them to be in completely general. So this visual representation highlights the hierarchical stack of the activation record, with each frame representing the function call. And we can call this as a one frame. So one function, when one function is called, this frame is going to be inserted to the stack. The return address guide the flow of execution, and the local variables and the parameters are allocated with each frame. So in a sense, activation records play a pivotal role in maintaining the integrity and organization of the function execution. They ensure that each function call has its dedicated space, facilitating the efficient execution of program in structured manner. Understanding this activation record is fundamental to comprehending the inner working of runtime environment. Next up, let's see the managing scopes. A scope refers to the region with the program where the particular identifier, such as a variable or function, is valid and accessible. It defines the visibility and reach of an identifier. And understanding the scope is crucial for managing variables lifetime and avoiding naming conflicts. Sometimes we may face a naming conflict because they were global variables or something like that. So to avoid that kind of issue, it's better knowing about managing scopes. By default, scopes are classified into two: static scope and dynamic scope. So the static scope or the lexical scope is determined at the compile time, and the scope is defined by the program structure. Variables are bound to their scope based on their textual structure of the code. And the common language are like C, C++, and Java. When you see the dynamic scope, it is determined by the runtime, and the scope is influenced by the calling sequence of the functions, and the variables are bound based on the order of the function calls, and they are less common but found in languages like Perl. Now let's see the lifetime of variables. The lifetime of variables refers to the duration during which the variable exists in memory. Variable lifetimes are managed with their respective scopes. So the first one is local variables, the next one is global variables, and the third one is static variables. So let's look at each of them one by one. The first one is the local variables. It exists within the scope of the block of the or the function with they are declared, and they are created upon the entering the scope and destroyed upon the existing. And these local variables don't persist across different invocations of the same function. So if you invoke the variable in the function, they don't persist on it, so you may face an error. Next, we have the global variables. This exists through the entire execution of the program, and they are created at the program startup and persist until the program termination. And these global variables can be accessed from any part of the program, leading to the potential issue like unintended modifications. And at last, we have the static variables. These have a lifetime equivalent of the entire program execution, and they are created at the program startup and persist until the program termination, and they retain their values between the function calls. So let's look these local variables, global variables, and static variables in example. So consider the following C code snippet to illustrate the variable scope and the lifetime. As you see here, we have declared variable x here outside our function, and inside our function we also declared another function int, which is 5, and we have a static int value declared here with 0 value, and we are printing out the values of each integers that we created, and we are invoking the given example function here in the int main. So when we look at it, we can specify the global, the local, and the static one from the given function. So the first one is the global variable because it's declared outside, and we have the local and static variables. So when you see y, that has the local scope within the example function, and it is created and destroyed each time the function is called. Next up, we have the x, which is the global variable, and it has a global scope and persists throughout the entire program execution. And the last one is z, which has the local scope within the example function, but retains its value between the function calls due to its static nature. So Understanding the scope and variables lifetime is critical for writing robust and maintainable code, preventing unintended side effects and optimizing memory usage. It contributes to the overall structure and behavior of the program in the programming language. Give the local, global, and static variables from the given C++ code. To answer this question, first we have to look at the theories that we learned earlier. Local variables exist within the scope of the block or the function where they are declared, and the global variables exist throughout the entire execution of the program. And the static variables have the lifetime equivalent to the entire program execution. So by looking at this code, we can find the local variable here. This int skit is equal to 20 is the local variable. This is created upon the entering the scope and this is going to be destroyed on exiting. The next one is the global variable. The global variable is int top is equal to 10 and this exists within the scope of the block or this exists through the entire execution of the program. And the last one is the static variable. The static variable is shown below. And these have the lifetime equivalent to the entire program execution and it retains their value between the functional calls. Now, let's look at optimization techniques. Optimization refers to the process of improving the performance and efficiency of a compiled code. The primary goal is to enhance the execution speed, reduce memory usage, and minimize the overall resource consumption of the generated program. Optimizations are applied during the compilation phase, transforming the original source code into more efficient machine code. So let's look at the key objectives of optimization. The first one is execution speed. Improving the runtime performance of the compiled program by reducing the number of executed instructions and optimizing the use of hardware resources is called execution speed. The next one is memory usage. Reducing the memory footprint of the compiled code, which can lead to more efficient use of system resource and improved cache row locality, is called memory usage. And the next one is core size. Minimizing the size of the generated machine code, which is particularly crucial in embedded systems or environment with the limited storage. And the last one is the power consumption. Reducing the power consumption of the generated code, which is essential for battery powered devices and energy efficient computing. Now we look at the key objectives in the optimization. Let's look at the purpose of or the benefits of optimization. The first one is performance improvement. Optimized code generally executes faster, leading to improved program performance. The next one is resource utilization. Efficient use of source resources, including memory and processor capabilities, is very efficient. The next one is compatibility. Optimization ensures that the compiled code is compatible with the target architecture, maximizing its effectiveness on the specific hardware. The next one is cost reduction. Optimization can lead to more economical use of resources, particularly the relevant in cloud computing or resource-constrained environments. And the last one is enhanced user experience. Faster, more efficient programs contribute to the better user experience, especially in interactive or real-time applications. So, optimization is one of the key aspects when we compile our code to the machine. Optimization is critical phase in the compilation process, where the compiler transforms the original code to the produced an executable that achieves better performance and resource utilization. It plays a pivotal role in ensuring the software runs efficiently on the wide range of hardware architectures and environments. Now we talked about the optimization. Now let's see the methods of the optimization. The first one is constant folding. This is the first method in optimization techniques. Constant folding is an optimization technique that involves evaluating the constant expression at compile time instead of runtime. So let's see how it works. The compiler analyzes the expression containing constants and performs arithmetic operation during compilation. Then the result is simplified expression with the constants replaced by their computed value. Let's see it with an example. Here we have a C++ code that's written, and as you see it, it has int a and int b that takes an input, and this function takes an input and gives an input here. And in this example, the addition operation a plus b occurs at runtime, even though a and b are constants in the specific context. The compiler might not optimize the addition operation. So when you come to the optimized version, the constant folding is more explicit. The calculate sum function is now directly returns the result of the addition of the constant a and b. Additionally, the variables x, y, and y, x, y, and the sum are declared as constants here, providing the compiler with the information about their immutability, potentially enabling further optimization. And remember that the modern C++ compilers often perform various optimizations automatically, and the impact of the explicit constant folding might be varying depending on the compiler and its optimization settings. So if you see this code, now let's see the benefit of the constant folding. The first one is reduce runtime computations. The second one is it improves the code efficiency by eliminating unnecessary runtime calculations. And the third one is it generates more compact and potentially faster code. The second method in optimization is dead code elimination. Dead code elimination is the process in which the compiler identifies and removes the code that doesn't contribute to the final program output. Dead code refers to the code that is unreachable or never executed. Modern compilers are typically capable of performing dead code elimination during the optimization phase. So dead code is the compiler analyzes the program to identify the code that cannot be reached. Then it removes the dead code from the compiled code. This is the method. Let's see the example. Here we have a C++ code that shows us the dead code elimination. In the given, the one in the left, we have a dead code that's written if x is equal greater than y, and it's gives an output of the block will never be executed. But since x is less than y, as you see it, this code is not going to be executed. In the example, if the statement checks if x is greater than y, but it's clear that the condition will never be true based on the preceding assignments. The code inside the if block is considered the dead code. Then in the optimized version, the dead code inside the if block has been eliminated by the compiler. The condition is now to be false at the compile time, so the entire block becomes unreachable and is removed during the optimization process. So this is how the dead code elimination works. But keep in mind that dead code elimination is just one of the many optimization performed by the compilers. The effectiveness of this optimization can vary between different compilers, and optimization settings always rely on proper testing and profiling to ensure that your code is optimized as expected. Now let's look at the benefits of dead code elimination. The first one is reduced code size and improved readability. The next one is enhanced program execution by eliminating the unnecessary computations. And the last one is streamlines maintenance by removing redundant or obsolete code. Now, let's see common sub-expression elimination. This is also the method of optimization our given compiled code. The common sub-expression eliminates its technique that it identifies and eliminates the redundant evaluation of the same sub-expression. So how it works is that the compiler identifies, repeats the computations within the code and replaces them with a single computation, storing their result in temporary variable. This reduces the redundant calculations and improves the runtime efficiency. Let's see an example. Here we have a C++ code that has some codes that are redundant here. If you look at it, in here we have an integer result1 with x times x plus y, and for integer result2 we have x times x plus y, and this is how it looks. In this example, the sub-expression x times x is common both on result1 and result2. Without optimization, this sub-expression might be evaluated twice. So when we come to the optimized version, the common sub-expression x times x is calculated once and stored in the variable common expression. Both result1 and result2 then use the pre-computed value. This eliminates the redundancy and it improves the efficiency of the code. And also, the modern C++ compilers perform various optimizations automatically. And common sub-expression elimination is one of those optimizations. The impact of manual intervention for the common sub-expression elimination might be limited, as compilers are often effective in identifying and optimizing the such patterns. Now let's see the benefits of the common sub-expression elimination. The first one is it optimizes the execution speed by avoiding redundant computations. The second one is it reduces the need for excessive memory storage of repeated sub-expression results. And the third one is it enhances the code readability and maintainability. These are some of the methods of code optimization of the given compiled code. Optimize the C++ code given below. We have seen the methods to optimize our given C++ code earlier. So by using these methods, optimize this given C++ code. To optimize this given C++ code, we use three methods. The first one is constant folding. The second one is dead code elimination. The third one is common sub-expression elimination. When we come to the first one, the constant folding says that the compiler analyzes expressions containing constants and perform arithmetic operations during the compilation. And the result is simplified expression with the constant replaced by their computer values. So when we look at the code, there is an optimization that we can do here. For example, in the given function at the top, here we are doing these mathematical operations, but we can merge them into our return value once, and we can change these variables. The second one is dead code elimination. The dead code elimination says that unused code must be removed. So when we look at the code, here int result 3 is not used anywhere. So we have to remove it. Also, it doesn't have a quotation at the end, so this is going to give us an error. So this is one of the advantages of optimization also. And the third one is common sub-expression elimination. And it says that when two or more variables use same kind of value, we can give them one result. We can give them one value and use it in both of the given variables. So as you see it here, both of the int result 1 and 2 use this 10 times 2. So what you can do is make it a one variable and use that variable. So the answer is going to look like this. As you see it here now, at the top in the first function, we merged all of the given variables, and by using the constant folding and by using the dead code elimination, we removed the int 3, or the result 3 from the given function, and by using the common sub expression elimination method, we remove this 10 times 2 to one variable here, 20, and also we use this constant folding, meaning that we multiplied the given variable to 20. So this is the result of this is the optimized code of the given C++ code. Hello everyone. In this section, we are going to see the code generation. So without further ado, let's jump into it. The final phase in our compiler model is the code generator. It takes as input the intermediate representation, or IR, produced by the front end of the compiler, along with the relevant symbol table information. And it produces as output a semantically equivalent target program. Code generation is the critical phase in the compiler design process, responsible for translating intermediate code generated by the compiler's frontend, as I said. And it is going to translate it to the machine target code or assembly language. This transformative process is essential for enabling the execution of high-level programming language constructs on a specific hardware architecture. So when we see the requirements imposed on the code generator are several. The target program must preserve the semantic meaning of the source program and be of high quality. That's it. It must make effective use of the available resource or the target machine. Moreover, the code generator itself must run efficiently. So as I said here at the top, we say the source target program transformation is semantically preserved in the code generation. And the next one is the code produced by the compiler should be of high quality. It should be effective use of target machine resources, and heuristic techniques can generate good but suboptimal code, because generating optimal code is undecidable. The challenge is that mathematically the problem of generating an optimal target program for a given source program is undecidable. Many of the sub-problems encountered in the code generation, such as register allocation, are computationally intractable. So in practice, we must content with the heuristic techniques that generate good but not necessarily optimal code. Fortunately, heuristics have matured enough that a carefully designed code generator can produce code that is several times faster than the code produced by the naive one. So while working on the code generation, there are key points that we have to look at. The key points in this chapter are going to be this one. The first one is the purpose of the code generation. As I said, the primary objective of the code generation is to bridge the gap between the abstract high-level representation of a program, or expressed as the intermediate code, and the low-level instruction that the computer hardware can execute. And the next one is intermediate code is going to be the bridge in this code generation. And the next key point here is the role in the compiler workflow. As I said, this is the last part of the compiler, the code generation. We change the given intermediate code to the machine code or the assembly one. And we are going to see also the translation process, how it appears, and also the hardware specific considerations. And also the key point in this chapter is going to be the optimizations for efficiency. And at last, the importance of a well-designed code generation. A well-designed code generator is crucial for producing code that is not only correct but also perform efficiently on the target machine. Decisions made during the code generation can significantly impact on the overall quality and the speed of the compiled program. So in the code generator, there are three primary tasks. The first one is instruction selection, and the next one is register allocation and assignment, and the last one is instruction ordering. Instruction selection involves choosing appropriate target machine instructions to implement to the IR statements. And the next one, register allocation and assignment, involves deciding what values to keep in which registers. And the last one, instruction ordering, involves deciding in what order to schedule the execution of instructions. In summary, the code generation serves as the linchpin between the high-level abstraction of a program and the machine-specific instructions required for the execution. Its role is pivotal in ensuring the successful translation of the program into the executable code, while striving for the optimal performance on diverse hardware architecture. So, while the details are dependent on specific of the intermediate representation, the target language, and the runtime system, tasks such as instruction selection, register allocation, and assignment, and instruction ordering are encountered in design of almost all code generators. The most important criterion for the code generation is that it produces the correct code. Correctness takes on special significance because of the number of special cases that a code generator might face. Given the premium on correctness, designing a code generator so it can be easily implemented, tested, and maintained as it is important design goal. So these are the issues that happen in the code generator that we have to look at. The first one is input to the code generator. The next one is the target program. The next one is memory management, instruction selection, register allocation, and evaluating order. These are the 6 issues on designing the code generator that we have to look at. The first issue in the code generation is input to the code generator. Input to code generator is an intermediate representation of the source program produced by the frontend, along with the information in the symbol table that is used to determine in runtime address of that object denoted by the names of the IR. The input to the code generator is the critical component in the process of transforming high-level source code into the machine executable instructions. This phase relies heavily on the format and representation of the input, and the use of well-defined intermediate representation plays a central role in the effectiveness of the code generation. When we see the importance of well-defined intermediate representation, the first one is language independence. A well-defined intermediate representation allows the code generator to be independent of the source program. Like this independence is crucial for reusability, as the same code of generator can be applied to different high-level language that share a common instruction representation. And the next one is ease of transformations. A standardized intermediate representation facilitates the ease of transforming high-level constructs into the machine code. The uniform structure of the IR simplifies the mapping language specific features to target machine instructions during the code generation process. The next one is consistent abstraction. By abstracting away language specific details, the intermediate representation provides a consistent and standardized abstraction of the program's structure and behavior. This consistency is essential for designing a code generator that can handle diverse language features. And the fourth one is facilitation of optimization. A well-structured intermediate representation enables the implementation of various optimizations during the code generation process. Optimizations such as the constant folding and their code elimination. And they can be applied more effectively when the IR provides a clear and uniform representation of the program semantics. And the last one is intermediary checks. During the code generation phase, the intermediate representation or the IR serves as the intermediary check for the correctness and integrity of the program structure. Errors or inconsistent in the IR can be detected and addressed before the final translation to the machine code. So when we see about the inputs, the intermediate representation of the source program, we have seen them earlier in the intermediate code generation part, and they can be linear tables or non-linear. The many choices of the IR or intermediate representation includes the like three address representations such as quadruples, triples, indirect triples, or virtual machine representations such as bytecode and stack machine code, and also linear representations such as postfix notation, and the graphical representations such as syntax trees and direct acyclic graphs. We have seen all of these ones in the previous section, so you can refer to the previous section if you want to know about these intermediate representations. And also it includes the symbol table information. As I said, the symbol table information is very crucial in every aspect of the compiler phase. In conclusion, the input to the code generator embodied in well-defined intermediate representation serves as the bridge between the intricacies of high-level source code and the machine-specific instructions. This intermediary layer not only facilitates language independence and uniformity, but also it acts as the foundation for the implementation of the optimizations and ensures the correctness of the code generation process. In this chapter, mostly we use the three address codes. The next issue in the code generation is target program code. In the code generation within the compiler design, the concept of target program refers to the culmination of the effort to translate high-level source code into the machine executable instructions tailored to specific hardware architecture. This phase involves the careful consideration of the characteristics, architecture, and instruction set of the target machine. And understanding of these factors is paramount for the successful creation of an efficient and functional target program. So the considerations that are related to the target program include the instruction set architecture of the target machine has significant impact on the difficulty of the constructing a good code generator that produce high quality machine code. So implementing code generation requires understanding of the target machine architecture and its instruction set. So the architecture of the target machine is the foundational consideration in this topic. So the backend code generator of compiler may generate different forms of code. Absolute machine code, which is executable, relocatable machine code, which is object file assembly language, or the bytecode forms for interpreters JVM. So producing an absolute machine language, or the first one, as an output has an advantage that can be placed in the fixed location in memory and immediately executed. Programs can be compiled and executed quickly. So the advantage of absolute machine code is its speed while compiling and executing. The next one is the relocatable machine code. Producing a relocatable machine language program, which is often called as an object module, as an output allows a subprogram to be compiled separately. A set of relocatable object modules can be linked together and loaded for execution by a linker loader. Although we must pay the added expense of linking and loading, if we produce relocatable object modules, we gain a great deal of flexibility in being able to compile subroutines separately and to call other previously compiled programs from an object module. If the target machine doesn't handle relocation automatically, the compiler must provide explicit relocation information to the loader to link the separately compiled program modules. So the second one, relocatable machine code, has an advantage of compiling in different places, as I said now. And the first one, absolute machine code, has an advantage of speed in compilation and execution. The third one is the assembly language. Producing an assembly language program as an output makes the process code generation somewhat easier. We can generate symbolic instructions and use the macro facilities of the assembler to help generate code. The price paid is the assembly step is after the I mean it is the assembly step after the code generation. And at last we have the bytecode forms for interpreters. So this is the new topic that we most of us don't know. So the stack-based architecture were revived with the introduction of Java Virtual Machine or JVM. This JVM is the software interpreter for Java bytecodes, an intermediate language produced by the Java compilers. So the interpreter provides a software compatibility across multiple platforms, a major factor in the success of Java. So these bytecode forms are essential for Java compilation. In this topic, for readability, we use the assembly code as the target language, as long as the address can be calculated from the offset and other information stored in the symbol table. The code generator can produce a relocatable or absolute address for names just as easily as the symbolic addresses. So in conclusion, the consideration related to the target program involve a nuanced understanding of the target machine architecture, instruction set, memory organization, and other characteristics. The code generator acts as the bridge between high-level abstraction of the source code and the intricacies of the target machine, ultimately shaping the generator code to optimize performance, correctness, and adaptability across the diverse range of platforms. The next issue in the code generation is the memory management. Memory management stands as the pivotal aspect of the code generation within the compiler design, wielding substantial influence over the efficiency and correctness of resulting target program. As the code generator transforms high-level source code into the machine executable instructions, decisions related to the memory allocation, organization, and utilization play a crucial role in shaping the behavior and performance of the compiled program. So when you see the importance of the memory management, the first one is resource optimization. Efficient memory management is the paramount for the optimizing the utilization of the system resources. Strategic decisions in memory allocation directly impact the runtime performance of the compiled program, influencing factors such as execution speed and resource consumption. The next one is prevention of memory leaks. Memory leaks where allocated memory is not properly deallocated can lead to the degradation of the performance and system instability over time. Effective memory management decision includes the proper allocation and deallocation mechanisms to prevent such leaks. The next one is stack and heap allocation. We have seen about stack and heap in the previous chapter. The stack serves as the region of memory storing local variables and function call information. Decisions about stack allocation involve managing the space allocated for function parameters, local variables, and control flow information. The stack follows the last in, first out structure, facilitating efficient function call and return operations. And the heap, when you see the heap allocation, the heap is used for the dynamic memory allocation, accommodating objects with the lifetime extending beyond the scope of single function. Memory management decisions related to the heap include allocating and deallocating memory blocks as needed. Proper heap management is crucial for preventing memory fragmentation and ensuring efficient use of memory resources. The fifth one or the fourth one is the memory organization. Decisions regarding our memory organization encompass the arrangement of different memory segments, such as code segment, data segment, heap, and stack. Ensuring proper segmentation and alignment is vital of the correct execution of the program. And the next one is data structure alignment. Aligning data structure in memory is important for efficient memory access. Proper alignment ensures the data is stored in a way that optimizes the access speed, especially on architectures with alignment requirements. And the next one is global and static data. Decisions about memory management extend to the global and static data, which may have different lifetime and storage requirements. Global variables are typically stored in the data segment, and decisions about their allocation and initialization impact program behavior. And the last one is the memory safety. Ensuring memory safety involves preventing common program errors such as buffer overflow, null pointer dereferences, and dangling pointers. Proper memory management decisions contribute to writing robust and secure code. So when you see the balance between efficiency and correctness while in memory management, the first one is there are trade-offs between speed and resources. Memory management decisions often involve trade-off between the speed and resource consumption. For example, the stack allocation is generally faster than the heap allocation, but comes with the limitation of size and scope. And so is for the heap. The size is larger than the stack, but when we compare it with the speed, the heap is much slower than the stack. The next one is garbage collection. In language with automatic memory management or garbage collection, decisions about when and how garbage collection occurs are critical. Balancing the benefit of automatic memory management with its associated cost is a key considerations. So, in conclusion, memory management decision in the code generation strikes a delicate balance between optimizing resource utilization and ensuring program correctness. Stack and heap allocation, overall memory organization, and consideration of global and static data collectively shape the behavior and performance of the compiled program, underscoring the pivotal role of the memory management in the code generation process. The next issue in the code generation is instruction selection. Instruction selection in the code generation is the pivotal process that involves translating high level language constructs into the sequence of target machine instructions. This crucial phase bridges the gap between the abstract representation of a program in high level language and specific set of instructions that target the machine can execute. The complexity of this task arises from the challenge of mapping diverse and expressive high-level language constructs to the often more limited and specialized instruction set of target machines. The code generation must map the IR program into the code sequence that can be executed by the target machine. The complexity of the performing this mapping is determined by a factor such as level of the IR or the intermediate representation, the nature of the instruction set architecture, and the last one is the desired quality of the generator code. If the IR is high level, the code generator may translate each IR statement into a sequence of machine instructions using the code templates, such statement by statement code generation. However, producers poor code that needs further optimization. If the IR reflects some of the low-level details of the underlying machine, then the code generator can use this information to generate more efficient code sequence. The, the nature of the instruction set of instruction machine has strong effect on the difficulty of the instruction selection. For example, the uniformity of the and completeness of the instruction sets are important factors. If the target machine doesn't support each data type in a uniform manner, then each exception to the general rule requires special handling. On some machines, for example, floating point operations are done using separate registers. Instruction speed and machine idioms are other important factors. If you don't care about the efficiency of the target program, instruction selection is straightforward. For each of the strategy statements, we can design a code skeleton that defines the target code to be generated for the construct. For example, Let's see this three address code. Every three address statement of the form x is equal to y plus z, where x, y, and z are statically allocated and can be translated into the code sequence. So when you see this, what we have to do is we are going to use this three address code and generate the assembly code. So the first thing that we have to do is we have to load one of the two given values. So we are going to load y into our register that given R0. R0 is our first register. So we load LD represents the command to load y, the y value into R0. And next we are going to add the value of y to, or the value of dead to R0. This represents that one. We are going to take the value of dead and put it into the value of R0. And next we are going to store this addition of or y plus z value into the value of x. So we are going to store it like this. So let's see another example. Here the fourth statement is redundant since it lost the value that just has been stored. And so in the third, if it's not subsequently used. So we are going to suit this one. First we are going to load the value of b to R0 like this. This is the comment, by the way, not part of the code. This is the comment. The forward slash represents a comment. So we are going to load the value of b to R0 or our first register. Next we are going to add the value of c to our register. Our register previously had the value of b, so we are going to add b plus c like this. And next what we are going to do is we are going to store the value of our register to our value a like this. And mind that the structure of the code. First we are going to write the command, then we are going to write the value, and next we are going to write the value where the story is going to happen. In here, for example, when we load, the value is going to be b and it is going to be stored in R0 or our register. When you add this one, we are going to take the value of c and our register R0 and we are going to add them and store it in R0. And here we are going to store the value of R0 to a. So that our final store is going to be in the a value. Previously we have seen how to store it, but this is more just redundant, so this is not correct. This is the structure to write our code. So now we are here. So we store the value of R0 to our a. Next what we are going to do is we are going to also work on this given string or three address code. First we are going to load the value of a to R0. This is the redundant that I was talking about, because we moved the value of R0 to a, and now we are going to load it to R0. This is redundant. Next what we are going to do is we are going to add the value of e to our register, and next we are going to store the value of R0 to d. So the quality of the generated code is usually determined by its speed and size. If you say about redundancy like this. On most machines, a given IR or intermediate representation program can be implemented by many different code sequences with significant cost difference between the different implementations. A naive translation of the intermediate may therefore lead to the correct but unacceptably inefficient target code. We need to know the instruction code cost in order to design a good code sequence. But unfortunately, accurate cost information is often difficult to obtain. Deciding which machine code sequence is the best for a given threaded construct may also require a knowledge about the context in which that construct appears. But we assume that using the correct and optimized thread race code would help us to fix this issue. So assume that a machine is simple processor with fixed instruction cost, and the realistic machine have deep pipelines, iCache, Dcache, and etc. So when we define the cost of instructions, so it is going to be like this: 1 plus cost of the source mode plus cost of the destination mode. So when we move, for example, let's say this is our instruction. So when we move the value of register 0 to register 1, when you store the content of R0 into R1, the cost is going to be 1 to move from one register to another one. When we move the value of R0 or register to the value of M or memory location M, the cost is going to be 2. And when we move from one location to our register, the cost is also going to be 2. And when we move 4 into register R0 into M, or store the content of 4 plus content of R0 into M, the cost is going to be 3. And when we move the 4 asterisk for R0 into M, the store contents times the contents 4 plus the contents R0 into M, the cost is going to be 3. And when we move the value 1, this 1 represents the hash represents that we are adding the value 1. So this is the number 1. When you store the value to R0, the cost is going to be 2. And when you add these 2, the cost is going to be 3. So we always have to try to optimize our thread race code given, or when we write our instruction or an assembly code, we always have to make or try to give the optimized code in order to reduce the cost. So let's see this example. A is equal to A plus 1. We can write this instruction using different methods or different styles of assembly code. The first one is going to be like this. We are going to move the value of A to R0, then we are going to add 1 to R0, and we are going to move this R0 to our given memory location of A. So if you count this, the cost is going to be 6, because from the previous section we see that to move value from memory to register is going to cost 2 to each, and when we add or when we move value of 1 to our register, the cost is 2. So in addition, the 3 2 the each cost 2, so the addition is going to give us 6, so the cost is going to be 6. The next method that we can write this given instruction is like this. We can just simply add the value of 1 to our given memory location. This way we are going to not use a register, but it has its own costs also. The cost is going to be 3. And also there is another method to write this instruction, which is inc a, meaning that this inc represents increment. Increment means increment by 1, or add 1 to the value of a. So this command inc is an increment by 1. So the cost is going to be 2. So we always have to strive to give our instructions the optimized given assembly code. So also I talked about this one earlier. So there is a need for the global code optimization. Let's say we have these two codes that we have. So let's work it together to write the assembly code. So we move the value of C to our register first. Then we add the value of B to our register. Next, we move our register value to the given memory location of A. Next, what we are going to do is in the D, in here for the D, we are going to move the value of A to our R0 or register. Then we are going to add to the register. Next, we are going to move the value of our register to the given memory location of D. So this is the way that we have seen earlier. So this code is not optimized because, as you see, there is a redundant use of R naught here, because we move the value of R naught to A, then we again move the value of A to R naught. So this part is redundant. But we can write this code or this assembly code in different way. What you can do is we can start from move the value of C to R naught, then add the value of B to our R naught. Next, we can add the value of E there, because as you see, C plus B gives us A. So we can skip this value, moving the value of A to R from R naught to A and back to R naught. Instead, we can just go to the next instruction, which adds the value of E to our given A, which is stored in the R naught. Next, after we add all three of them, we move the value of R naught to D. So this code is optimized compared to the one in the left. So this is the code optimization. So let's see the challenges in the instruction selection. The first one is diversity of high-level constructs. The high-level programming language supports a wide variety of constructs, which each with its own semantics. Translating this diversity into a concise and efficient set of target machine instructions poses a significant challenge. And the next one is register allocation. Efficient use of register is critical for performance. The code generator must decide when and how to use the register for variables and intermediate values, considering the limitation of the target machine's register set. As we have seen earlier, we have to always be cautious when to use the registers, because the cost is going to get higher and we don't want that to happen. And the next one is balancing complexity and performance. The challenge lies in balance the desire of accurate representation of high-level constructs with the need for performance. Complex language constructs may require intricate sequence of instructions, and the code generator must find the optimal trade-off. And the next one is the machine-specific considerations. Different target machines have different characteristics. The code generator must account for these variations, adapting the instruction selection process to suit the specific feature of the target architecture. So, in conclusion, instruction selection is an announced and challenging process in the code generation. It involves translating the richness of high-level language constructs into a sequence of target machine instructions, requiring a careful consideration of semantics, efficiency, and the unique characteristics of the target machine's instruction set architecture. The code generator's success in the endeavor is crucial for producing executable code that faithfully represents the original program's intent while harnessing the capabilities of the target machine. To answer this question, what we do is first we have to follow the steps that we have seen earlier. So the first thing to do is create a strategy code for the given expression. So how do we do the strategy code? By adding the non-terminals, we can create a strategy code for the given expression. First, let's have a T1, which is A plus B, and T2 is going to be T1 times C, and the T3 is going to be T2 minus D. From this given strategy code, we can now create the assembly code by looking into the strategy code. So we start from the T1, which is A plus B. So we start by moving the a value to our given register R0, and then from there, now we can add the b value to our R0 or our register, and this is how the addition happens. And next we move the R0 value, or we move the value of the T1 from the register to the T1 memory location. Next we move the value of C to R0, and then we multiply it by using the mel given this code. We multiply the C value, which is stored in the R0, with the T1 value. Then we move the R0 value to our T2. Then again we move the T2 value from the memory location to our register, and then we subtract D from the given T2 or R0 value, and at the end then we store the value of R0 to our given memory location of T3. This is the general method or the assembly code that we directly written from the strategies code. But we can optimize this code because, as you see it, there are many redundancies in this code. Like here, we move the value of T2 from register, and again we moved the T2 value to the register. So this assembly code is not optimized. So when we write the assembly code by removing the redundancy, what is going to happen is, first we move the value of A to our register, then we add it with the B. So this is going to be, our register is now A plus B. Then we multiply it with C while it is on the register. Then we subtract D from our given R0, and at the end then we move the value of R0 to our given memory location of T3. This is how we optimize our given assembly code. To answer this question, what we do is, first we have to follow the steps that we have seen earlier. So the first thing to do is create a strategy code for the given expression. So how do we do the strategy code? By adding the non-terminals, we can create a strategy code for the given expression. First, let's have a T1, which is A plus B, and T2 is going to be T1 times C, and the T3 is going to be T2 minus D. From this given strategy code, we can now create the assembly code by looking into the strategy code. So we start from the T1, which is A plus B. So we start by moving the A value to our given register R0, and then from there, now we can add the B value to our R0 or our register, and this is how the addition happens. And next we move the R0 value, or we move the value of the T1 from the register to the T1 memory location. Next we move the value of C to R0, and then we multiply it by using the mel given this code. We multiply the C value, which is stored in the R0, with the T1 value. Then we move the R0 value to our T2. Then again we move the T2 value from the memory location to our register, and then we subtract D from the given T2 or R0 value, and at the end then we store the value of R0 to our given memory location of T3. This is the general method or the assembly code that we directly written from the strategies code. But we can optimize this code because, as you see it, there are many redundancies in this code. Like here, we move the value of T2 from register, and again we moved the T2 value to the register. So this assembly code is not optimized. So when we write the assembly code by removing the redundancy, what is going to happen is first we move the value of A to our register, then we add it with the B. So this is going to be our register is now A plus B. Then we multiply it with C while it is on the register. Then we subtract D from our given R naught. And at the end, then we move the value of R naught to our given memory location of T3. This is how we optimize our given assembly code. The next issue in the code generation is register allocation and code generation assignment. A key problem in code generation is deciding what values to hold in what register. Registers are the fastest computational unit on the target machine, but we usually don't have enough of them to hold all values. Values not held in registers need to reside in memory. Instructions involve registers operands are invariably shorter and faster than those involving operands in memory. So, efficient utilization of registers is particularly important. Efficient utilization of limited set of registers is important to generate a good code. Register allocation is the critical facet in the code generation that directly influences the performance of the compiled program. As the code generator translates high-level source code into machine executable instructions, efficient register allocation becomes paramount for optimizing execution speed and minimizing memory access. This intricate process involves assigning and managing registers to variables and intermediate values, navigating the delicate balance between the limited availability of registers and the need for swift and streamlined execution. So when you see the use of registers is often subdivided into two sub-problems. The first one is register allocation and the next one is register assignment. The register allocation is during which we select the set of variables that we reside in register at each point in the program, or to select the set of variables that we reside in register at a point of the code. And the next one is register assignment, which is during which we pick the specific register that variable will reside in, or to pick the specific register that a variable will reside in. So finding an optimal register assignment is hard and NP complete or non-deterministic polynomial time. Finding optimal assignment of register to variables is very difficult, even with single register meshes. Mathematically, the problem is NP complete or non-deterministic polynomial time. The problem is further complicated because the hardware or the operating system of the target machine may require that certain register user convention to be observed. So it is very hard to use the optimal register assignment, but trying to make it perfect is what we do. Now let's see the significance of efficient register allocation. The first one is speed optimization. Registers are high-speed, on-chip storage locations that provide rapid access to data. Efficient register allocation ensures that frequently used variables and intermediate values are stored in registers, significantly speeding up execution of critical sections of the program. The next one is minimization of memory access latency. Memory access is comparatively slower than register access. Effective register allocation reduces the need for accessing data from slower memory locations, minimizing latency and enhancing overall program performance. The third one is reduced dependency on cache. Registers serve as the fast access buffer, reducing the dependence on cache memory. So optimized register allocation can mitigate cache misses, which occur when data is not present in the cache, further enhancing the speed of the program execution. The fourth one is optimal utilization of processor resources. Efficient register allocation ensures the optimal utilization of the process resources. By managing registers, the code generator maximizes the parallelism and pipelining capabilities of the processor, which contributes to higher throughput. And the fifth one is register renaming and elimination of redundant loads. So register allocation enables register renaming, a technique that eliminates naming conflicts between register and memory locations. This in turn allows for the elimination of redundant loads and stores, further improving the efficiency of the code generation. And at the last, the support for advanced optimizations. Effective register allocation lays the foundation for advanced optimizations such as common subexpression elimination and loop optimization. These optimizations are dependent on the availability and efficient use of registers. So if you say the significance of efficient register allocation, let's see what strategies we use for register allocation. The first one is graph control. The graph control is a popular algorithm approach to register allocation. It models the interference between the variable as an interface graph, which nodes represent variables and edges represent conflicts. The graph is then colored with available registers, ensuring that adjacent nodes have different colors. The next one is linear scan register allocation. Linear scan register allocation is a heuristic approach that assigns registers based on the order of appearance in the code. Variables are allocated registers as they encounter during a linear scan of the code, and spill decisions are made when registers are exhausted. The third one is global and local register allocation. Global register allocation considers the entire program, aiming to minimize spill and improve the overall performance. Local registers allocation focus on individual functions or basic blocks, adapting the limited scope and reducing the complexity of the allocation program. The fourth one is spill cost and spill cost minimization. Spilling occurs when there are not enough registers to accommodate all variables. Efficient register allocation involves minimizing the impact of the spill by strategically placing a spill code and considering the cost of spill in terms of execution time. The fifth one is optimistic allocation and backtracking. Optimistic allocation assigns registers optimistically, assuming that there will be no spills. If spills occur, the allocator backtracks and tries to alternative allocations. This adaptive approach balances the trade-off between optimistic assumption and the reality of resource constraints. And the last one is interference graph reduction. These techniques like coalescing and simplification of interface graph can reduce its size, making graph coloring more feasible. Coalescing combines nodes in interface graph to represent the variables that can share a register without conflicts. So, in conclusion, efficient register allocation is the cornerstone of the performance optimization in code generation. By strategically assigning and managing registers, the code generator maximizes the speed of execution, minimizes the memory access latency, and paves the way for advanced optimization, contributing to the overall efficiency and responsiveness of the compiled program. The selection of an appropriate register allocation strategy depends on the characteristics of the target architecture and nature of the source code being compiled. Evaluation order is the fundamental aspect of code generation. It dictates the sequence in which expressions within a program are computed. This decision carries a significant implication for the generator code, influencing not only the correctness of the program but also its performance. As the code generator navigates the intricacies of high-level source code, the concept of evaluation order becomes a crucial factor in determining how computations unfold and how the resulting machine executable instructions are structured. The order in which computations are performed can affect the efficiency of the target code, and we are going to look at it with example next. But before, when we see the concept in the evaluation order, the first one is like order of sub-expression evaluation. Consider an expression with multiple sub-expressions. Evaluation order specifies the order in which these sub-expressions are evaluated. The choice of evaluation order can profoundly impact the program behavior and performance. And the next one is side effect and dependencies. Some expressions may have side effects, such as modifying variables or invoking functions. Evaluation order is crucial when side effects and dependencies exist, as it influences the timing and sequence of these effects during program execution. And the other one is shortcut evaluation. In language like C or C++, logical and or logical or operator exhibits a short circuit behavior. The evaluation stops as soon as the result is determined. Understanding and exploiting such language specific behaviors are essential for efficient code generation. Let's see an example. We have given this expression that we have, and the first thing that we have to do is first create a thread address code for this given expression. So the thread address is going to be like this. First, let's give it t1 t1 as a plus b, and t2 is going to be c plus d, and t3 is going to be e times t2. E refers to C plus, T2 refers to C plus D, and T4 is going to be T1 minus T3. So from this thread address code, what we do is we generate an assembly code. So by default, what we can do is first, by just going a step forward from the given thread address code, is like we move the a value to our register or R naught. Then we add the value of b to our R naught or our register. Then we move the value to our T1. We move the register value to T1. Next, we move the value of C to R1 or register 1. This is the register 0. And we add D to the R1 register. And then what we do is we move the value of E to our R naught, which is an empty because we moved the value to T1, so it was empty. Now we move the value of E, or we add the value of E to R naught. Then we multiply. This mul is a command to multiplication, and R1 to R naught, and it's going to store the value to R naught. And next we move the value of T1, which is a plus b, to R1, because R1 is now currently empty because we multiplied with R naught and stored the value to R naught, so R1 is empty currently. And then we subtract. This sub represents a command for subtraction, so we subtract we subtract R1 to R naught, so R naught is going to be subtracted from R1, and it's going to be stored in the R1. Next, we move the value of R1 to our T4. And this is the general structure to write the assembly code, right? So by looking at this address code, we go from top to bottom by looking at the given address code, we generate this assembly code. But this code is not evaluated correctly. If you see the some of the orders, if we change some of the orders, we can optimize this assembly code. So let's look at the evaluated assembly code that we have. So what we do is first we move the value of C to R naught. So we're starting from this value or T2. Then we add the value of D to our R naught. Next we move the value of E to R1. So the value of E is now moved to R1. And now we multiply R0 with R1 and the value is going to be stored in R1. So after that, we move the value of A to our R0. We go to the top address code. Then we add the value of B to our R0. So after this, we subtract the value of R1 from R0 and store it in R0. Then we move the value of R0 to T4. So by changing some values from our given address code or assembly code, the evaluation occurs. So now we use less memory and this one is more optimized compared to the assembly code we simply generated by looking directly in the address code. So this is how evaluation works. We have to know where to call the given instruction in order to minimize the use of the given registers. Now let's see the impacts on generator code. The first one is optimization opportunities. Evaluation order presents optimization opportunities. The code generator can rearrange expressions to minimize resource usage, exploit parallelism, or reduce the overall execution time by strategically ordering computations. The next one is compiler dependent behavior. The order of evaluation can be compiler dependent when the language specification allows flexibility. Compiler compiler writer makes decisions that impact how expressions are translated into the machine code. Understanding compiler behavior is crucial for predicting and optimizing program performance. The third one is dependency analysis. Evaluation order affects dependency analysis. The code generator must analyze dependencies between sub-expressions to ensure the correct result and efficient execution. Dependencies influence decisions on register allocation, instruction scheduling, and other optimized techniques. The fourth one is avoiding redundant computation. The strategic evaluation order can help avoid redundant computations by analyzing dependencies and optimizing the order of evaluation. The code generator can reuse intermediate results and minimize unnecessary calculations. And the fifth one is impact on parallelism. Modern processors often have multiple execution units capable of parallel processing. Optimization evaluation order can exploit this parallelism, leading to more efficient utilization on underlying hardware. And the last one is code size and readability. The order of evaluation can impact code size and readability. While certain evaluation orders may result in more compact code, others may lead to code that is easier to understand and maintain. Balancing these factors is essential for writing efficient and maintainable code. So, in conclusion, evaluation order plays a crucial role in shaping the execution flow of a program during code generation. Decisions about the order in which expressions are evaluated impact the correctness, performance, and readability of the generator code. By understanding the dependencies and optimizing the evaluation order, the code generator contributes significantly to the overall efficiency and effectiveness of the compiled program. Evaluate the given code to optimize the given assembly code. We have been given the expression, the thread address code, and the assembly code, and we are tasked to evaluate the given assembly code and come up with the optimized one. To evaluate the given code and come up with the optimized code of the given expression, what we have to do is first look at the given thread address code and given our assembly code. So by looking at two of them, we can know that there are some evaluations that we made, or we can reshuffle our given assembly code to come up with the optimized and less code. So let's see the different evaluation order for our given assembly code. This can also give us the thread address code, but we need to reshuffle the work or the thread address code how they implemented, and then we are going to come up with different evaluation order. So we move first the b value to our given register, and then we add c value to our register. Next, we multiply our given our register with the value of a, but as you see it in the assembly code that we have, we moved the value of r0 to the t1, and that's how we reduce that step by multiplying directly the t1. We reduce these three executions of the assembly code. And next we move the value of d to our register 1 or different register, and we multiply e with our r1 or register 1 as you see it here. And next what we are going to do is we subtract r1 value to r0, and then r0 is going to be the place where our value is going to be stored, and then at the end we are going to move the value of r0 to our t4. So by shuffling the values, or by shuffling how the execution works, we can have an optimized assembly code by looking at this. Now, let's look at just-in-time compilation, or JIT. Just-in-time compilation is a dynamic code compilation technique employed by modern programming language runtimes. Unlike traditional ahead-of-time compilation, just-in-time compilation occurs during the program's execution, translating portion of code on the fly. When we see the dynamic nature of just-in-time compilation, it has adaptability to runtime conditions. JIT compilation is characterized by its adaptability to runtime conditions, responding to dynamic behavior of the program. It is tailored to the compilation process based on the actual usage patterns and execution characteristics observed during runtime. And also, it has feature of selective compilation. JIT doesn't compile the entire code base upfront. Instead, it selectively targets the specific portion of the code that are frequently executed or identified as hotspots. The selective approach optimizes the compilation effort for the most crucial part of the program. So, when we see some components of the JIT compilation, the first one is interpreter and compilation thresholds. Typically, a JIT-enabled runtime includes an interpreter for immediate execution. Compilation thresholds are set to trigger the transition from interpretation to compilation based on the frequency of the code execution. And the next one is profiling and feedback mechanism. So JIT compilation relies on profiling information gathered during the program execution. Feedback mechanisms such as runtime profiling guide the compiler to optimize the code based on the actual usage, improving the performance iteratively. So we can say that the advantage of the JIT compilation are adaptive optimization and the other ones. When you see the advantages of the compilation, the first one is adaptive optimization. JIT compiler adaptively optimizes code based on the runtime profiling, allowing for fine-tuning of the execution path. This adaptability leads to the better performance in real-world scenarios. So as I said, JIT compilers dynamically optimize code based on the profiling information gathered during execution, which enables tailoring optimization to actual usage patterns and enhancing overall performance. These compilers are dynamically optimized codes based on the actual usage pattern, improving overall performance. And these JIT compilers dynamically optimize, as I say, and they enable tailoring optimization to the actual usage pattern, which overall enhance the performance. The next one is reduced memory footprint. Unlike the static compilation, which generates a complete executable code, Git compilation can selectively compile and optimize only frequently executed code. This can result in smaller memory footprint, especially in applications with large code base. Select compilation allows Git to optimize and generate code only for frequently executed paths, and this can result in small memory footprint compared to the static compilation. So this compilation provides a level of platform independence, adapting code generation to the specific execution environment, and it enhances portability across different architectures. And also the selective compilation targets frequently executed code, reducing overall memory footprint compared to the static compilation. And unused or less frequently executed code is not unnecessarily compiled, and it saves resources. The third one is the cross-platform execution. JIT compilation provides a level of platform independence by generating code that suits the specific characteristics of the execution environment. It enhances the portability across different architectures. So let's see the implementation in runtime environments. The first one is Java Virtual Machine or JVM and HotSpot Compilation. The Java platform is a prominent example of JIT compilation in action. And also hotspot compilation, which is the specific implementation of JVM, identifies and optimizes frequently executed code paths. And it emphasized adaptive optimization. The next one is .NET Common Language Runtime, or CLR. The .NET Runtime utilizes JIT compilation to convert Common Intermediate Language, or CIL code, into native machine code. Like the JVM, it adapts to runtime conditions to enhance the execution efficiently. So if you say the implementation and the advantage, what are the challenges in considerations during the JIT compilation? The first one is warm-up period. The JIT compilation may have a warm-up period while initial execution is less optimized. Profiling information gathered during this period helps refine the subsequent optimization for improved performance. The next one is overhead. There is an initial overhead as the code is compiled during execution, potentially impacting startup times. And the long-term performance gains often outweigh this initial overhead. So in conclusion, the JIT compilation stands as the dynamic and adaptive approach to code optimization, breathing life into the program by responding to real-world execution patterns. Its ability to balance adaptability, memory efficiency, and cross-platform execution makes JIT compilation a cornerstone in modern runtime environments. Now, let's look at the difference between dynamic compilation and static compilation, navigating the spectrum of the code transformation. First, let's look at the static compilation or the traditional approach. This static compilation represents the conventional method where the entire source code is translated into the machine code before the program execution, and this is the most common one or the common method in compilation. The compilation process takes place once and producing a standalone executable file that encapsulates the entire program's functionality. So if you want to run one program, the whole program have to be executed. So when we are working, for example, while debugging, we may face some issues to in this static compilation because it takes too much time to process one code. So while generating, it may take more time. So it will be very difficult in the debugging phase. And when we see the creation of standard alone executable, that static compilation results in the generation of the standalone executable file, encapsulating the entire program's logic and functionality. The compiled binary is self-contained, typically including all necessary libraries and resources. So what drawbacks that static compilation have? The first one is longer startup times. Due to the need to compile the entire code base before execution, static compilation can lead to longer startup time. Users may experience delays as the program initializes and prepare for execution. And the second one is less adaptability to runtime changes. Since the compilation occurs before runtime, the compiled code lacks the flexibility to adapt to changes in execution conditions. Any adjustment or optimization must be addressed during the subsequent recompilation. Now let's look at the dynamic compilation. So when we contrast dynamic compilation with static compilation, dynamic compilation in contrast introduced a more flexible and adaptive approach by compiling the portion of the code during the program execution. And we can mention like JIT compilation in this phase, highlighting the essence in just-in-time or JIT compilation. Dynamic compilation translates specific code segments on the fly during runtime. The compilation process is triggered by the actual usage of patterns and demands of the program. As I said in the JIT, that in dynamic programming, the the first compilation starts on only the codes that are used frequently. Then on the fly or during the program running, it compiles the other codes. So when you see the advantage of dynamic compilation, the first one is better optimization based on runtime information. JIT compilation leverages runtime profiling and feedback mechanism to optimize code based on actual execution patterns. This adaptability ensures that the compiled code aligns with the program's dynamic behavior. And the next one is adaptability to varying execution conditions. So dynamic compilation allows for adaptability to varying execution conditions, accommodating changes in program flow and resource availability. And this responsiveness enhances the program's ability to optimize for specific scenarios during runtime. So let's look at the program or the practical implementation. So the first one is Java Virtual Machine or JVM and JIT compilation. The Java platform is a prominent example of the dynamic compilation with the JIT. And the JVM translates Java bytecode into naive machine code during the execution, optimizing the frequently executed portion of the improved performance. And the next one is interpreters and compilation thresholds. Dynamic language often employ interpreters initially for immediate execution. Compilation thresholds determine when the portion of the interpreter codes are dynamically compiled, striking a balance between interpretation and compilation. So, what are the considerations and trade-offs on the dynamic compilation? The first one is startup time versus the runtime adaptability. So static compilations, while potentially leading to longer startup times, they produce a fully optimized and executable code. And dynamic compilation with its adaptability may have a warm-up period but can optimize code based on the real-world usage. And the next one is resource utilization. So dynamic compilation allows for selective compilation of frequently executable code, potentially conserving resources compared to all encompassing static compilations. So in conclusion, the choice between dynamic and static compilation involves a trade-off between startup times, adaptability to runtime changes, and its resource utilization. Understanding the strengths and weaknesses of each approach enables developers to tailor compilation strategies to the specific requirements of their application. Next up, let's look at HotSpot compilation in Java Virtual Machine or JVM. So the hotspot compilation represents a specific implementation of the just-in-time compilation with the Java Virtual Machine or JVM. Unlike the traditional static compilation, hotspot compilation dynamically optimizes the code during the program execution. So when we focus on the hotspots, the central to the hotspot compilation is its focus on identifying and optimizing hotspots within the code. The hotspots are sections of the code that are frequently executed during the program runtime. So let's see the adaptive optimizations in the hotspot for the dynamic compilation. The first one is inlining. And this inline incorporates small frequently called methods directly into the calling code, reducing methods to call overhead. And these three are Hotspot employs adaptive optimization techniques to enhance the performance of the frequently executed code. The next one is loop unrolling, and this expands loops to reduce loop control overhead and increase the instruction level parallelism. And the third one is de-optimization, which allows for dynamic correction of the optimization decisions if they prove suboptimal during the runtime. So the adjustments based on the runtime profiling, that hotspot leverage runtime profile continuously gather information about the code execution patterns. This profiling guides adaptive optimization, enabling hotspot to dynamically adjust its optimization strategies based on the real-world program behavior. Now let's see the third compilation. So Hotspot introduced the concept of third compilation, providing a multi-stage compilation to code translation. Code is initially interpreted for immediate execution, and then based on the usage pattern, it undergoes different levels of compilation within the increasing optimization. And when you see the compilation threshold, the JVM sets the compilation threshold to determine when the code translation from the interpretation to compilation. This adaptive approach balances the trade-off between the startup time and long-term execution efficiency. And now let's see the code caching, which avoids recompilation of frequently executed methods. That hotspot addresses the potential overhead of recompiling frequently executed methods by implementing a code caching. Compiled code is cached to avoid unnecessary recompilation, promoting the efficient reuse of the optimized code, which impacts the startup time and execution efficiency. The code caching positively impacts the startup times as the frequently executed methods don't undergo repeated compilation. So the overall execution efficiency is enhanced as the cached code is readily available to rapid execution and which reduces the latency. So when you see the consideration and the benefits, the first one is balancing adaptability and performance. Hotspot compilation achieves a delicate balance between adaptability to runtime conditions and long-term performance optimization. These adaptive strategies, coupled with tired compilation and code caching, contribute to an efficient and responsive runtime environment. So, in conclusion, hotspot compilation in the JVM stands as the testament to the dynamic capability of the JIT compilation. By focusing on the hotspots, leveraging adaptive optimization techniques, incorporating tired compilation, and implementing code caching, Hotspot embodies a sophisticated approach to the balancing adaptability and execution efficiency in the Java ecosystem. Hello guys, in this section we are going to see domain-specific language with some exercise on. So without further ado, let's jump into it. Let's start from the definition of the domain-specific language. So what's a DSL? A domain-specific language is a computer language that is targeted to a particular kind of program, rather than a general-purpose language that is aimed at any kind of software program. So, domain-specific languages have been talked about and used for almost as long as computing has been done. So, to answer what a domain-specific language is, it is a programming language that is designed to solve a specific problem within the particular domain. Unlike the general purpose programming languages like Java or Python, DSLs are tailored to specific domain, making them more expressive and easier to use. And DSLs can be used to solve a wide range of problems, from data processing to web development to scientific computing. They are particularly useful in domains where there are complex rules and requirements that need to be enforced. And big companies that use sophisticated works use these DSLs to because they are tailored to some specific targets of work to be done. So they are very crucial in companies that use the scientific computing, data processing, and other things. So how does this domain specific language work? So DSLs work by providing a set of abstractions that are specific to a particular domain. These abstractions allow developers to write code that is more concise and expressive, while still enforcing the rules and requirements of that domain. And DSLs can be implemented in various ways, including as embedded language with the general purpose programming language or as a standard language that are compiled or interpreted. We are going to see about this feature later. But now let's see why we use the domain specific language. What are the use of the domain specific language? So there are many reasons why we might want to use the domain specific language in our project. Here is just a few that are listed here. The first one is increased productivity. So DSLs can help you write code faster and more efficiently. by providing abstractions that are specific to your domain. You can write code that is more concise and expressive, which can save you time and effort. I'm not saying that writing DSL is easier, I'm saying that writing a code for specific target would be easier using the DSL because we would have only specific and concise expressions to use on our DSL, so it would be very fast and efficient our work. The next one is improved readability. DSLs can make your code more readable and easier to understand. By using abstractions that are specific to your domain, you can make your code more self-documenting, which can make it easier for other developers to understand and modify. So most of the time, DSLs are written for specific targets. So they have a concise expressions on the code. So they will be very easier to read rather than the general purpose programming language. And the third one is better maintainability. So DSLs make your code more maintainable by enforcing the rules and requirements of your domain. By using languages that are tailored to your needs, you can ensure your code is always in compliance with the requirements of your domain, which can make it easier to maintain over time. So these are the three use cases that I mentioned, but the use of the domain specific language are very vast, and but these are the most or the crucial aspects in why we use domain specific language. So let's see the disadvantage also. We have seen the advantage of using the DSLs. Now let's see the disadvantage. The first one is the cost of designing and implementing and also maintaining the DSL. Since we are writing a DSL or the domain specific language, it's going to cost us more money because we are not using the general purpose language or the written language. The next one is the cost of education for DSLs users. So since we write new code, we must teach others to use our DSLs, especially our if it's company, our employees must know the how the DSL works. And the third one is the limited availability of the DSLs. As I said, since its cost is very higher to build DSL, there is a limited availability of DSLs. The fourth one is the difficulty of finding the proper scope for the DSL. This is also the crucial aspect while designing a DSL because sometimes we tend to think that our scope is larger and we work on that, and after we finish our program we find that there are some things that are not included in the scope, so it would be very difficult on that case. So it's always essential to think before jumping into writing the DSL, to think how the scope must be. So the fifth one is the difficulty of balancing between domain specificity and general purpose programming language constructs. This is most of the time appears in the internal DSLs and we are going to look at it. The last one is the potential loss of efficiency when compared to hand-coded software. So the loss of efficiency when we say that, because since we are using DSL, we are going to write the DSL code, so it would take our time, so which loss our efficiency. So these are the disadvantages. So before jumping into the types of domain-specific language, DSLs are very common in computing, as I said. For example, CSS or regular expressions, make, and SQL. These all are DSLs. Now let's see the types of domain-specific language. There are two main types of DSLs. The first one is external DSL and the next one is internal DSL. So when we start from the external DSL, external domain-specific languages are standalone languages that are designed to solve a specific problem within a particular domain. They are typically implemented using a parser and compiler or interpreter. External DSLs have their own custom syntax, and you write a full parser to process them. This is the strong tradition of doing the Unix community. A variation of this is to encode the DSL in a data structure represented such as XML or YAML. So some examples of the external DSL are like SQL, regular expression, and YAML. When we see the internal DSLs, these are embedded languages that are designed to solve a specific problem within the particular domain. They are typically implemented using the general purpose programming language, and they rely on language syntax and semantics to provide the necessary abstractions. So internal DSLs are particularly using a host language to give the host language the feel of particular language. This approach has a long been part of the tradition in Lisp, and in the last decade, get re- got re-energized by the Ruby community. Although it is usually easier in low ceremony language like that, you can do efficient internal DSLs in more mainstream languages like Java, C Sharp, and on. So internal DSLs are also referred to as embedded DSLs or fluent interfaces. For example, the internal DSLs include Ruby on Rails, RSpec, or also jQuery. They depend on these internal DSLs depend on the general purpose programming language, but they give their functions or they give their feeling of the new language to the given general purpose language. So we can say that these are internal language or embedded DSLs. So when you see the most common DSLs in the well, they are textual, but they have the graphical DSLs too. Graphical DSLs require too long or a long length of language workbench. So language workbenches are less common, but something that they have potential to profoundly improve the way we do programming. So DSLs can be implemented either by interpretation or code generation. Interpretation or reading in DSL script and executing at runtime is usually easiest, but code generation is sometimes essential. Usually the generated code is itself a high-level language such as Java or C. Let's see now creating the domain-specific language. So creating a DSL can be a complex process, but it can also be incredibly rewarding. Here are the steps to follow while creating the DSL. The first one is define a problem. The first step in creating DSL is to define the problem domain. This involves identifying the specific problem you want to solve and requirements of your domain. So, as I say, we have to specify the scope, otherwise we are going to face an issue after we finalize the DSL, because we may find some scopes that are out of our DSL. So we have to define the problem clearly, and we have to make the scope that is more inclusive. The next one is choose a language. The next step is to choose a language of your DSL. This can be existing language such as Ruby or Python, or it can be a new language that you create specifically for your DSL. So as I said about the external and internal language, you can create the external language like by creating the parser, the Lexer code generator and all, or you can also depend on the general purpose programming language like C++, C Sharp, and the other ones. Next, define the syntax and the semantics. So once you have chosen the language, you need to define the syntax and semantics of your DSL. This involves defining the keywords, operators, and other constructs that will be used in your language. And the last part is to implement the DSL. So this is the final step to implement your DSL. This involves writing a parser, compiler, or interpreter that will be used to process your DSL. If it is external, and if it's internal, writing the syntax or the functions to use the general purpose code or the general purpose programming language, and by giving it the functions to have the DSL filling on the general purpose programming language. So in conclusion, domain-specific languages are a powerful tool for developers who want to write code that is specific to their domain. They allow you to create a language that is tailored to your needs, making it easier to write code that is both concise and expressive. Now, let's do some exercise on the given DSL. Create a simple DSL for creating and evaluating mathematical expressions. It must include basic binary operations: addition, subtraction, multiplication, and division. So this is the task that is given for us to work on. So the first thing that we have to do is to look into the scope. So it gives us that it must include basic binary operations: addition, subtraction, multiplication, and division. So our scope must include all these three or four operations. And also we can, let's assume that's what we use, and for this purpose we are going to use the C++. We are going to write internal DSLs that is dependent on the C++. So by using this tool, let's dive into the code. So let's open our Visual Studio Code and let's create a new file here. So let's select the text file. So let's select then the C++. After that, we are going to write our C++ file. So in this example, we are going to demonstrate the power and simplicity of our domain-specific language for mathematical expressions in C++. So in this example, we will use our DSL to create and evaluate mathematical expressions involving constants, variables, and basic operations. So let's dive into the code and see how the DSL simplifies the expression, and let's see it. So while creating our C++, the first thing is we have to do is to define our library. So let's include a stream, and this is an input output stream library, and it provides the functionality for standard input and output operations. So in this code, we are going to use it for printing results to the console using the std or cout. And the next library that we are going to use is the functional. So include functional. And this function object, this is the function objects and higher order operation library, and it is used for working with function objects, particularly for defining operations in the binary operation class that we are going to create. And we are going to use it for storing lambda functions and std function for the binary operations. The next library we have to include is memory. So as the name indicates, this is the memory management library, and it provides or facilities for memory allocation and deallocation. And we are going to use it for managing object ownership through std unique pointer to manage the ownership or the dynamically allocated objects. Let's start by writing the base class for our expression. So let's name it class expression. and let's give it a public of virtual double evaluate and virtual expression, which are the default value. So we wrote now the base class for our expression. So to define it, it is an abstract base class representing a mathematical expression, and it defines the interface for all expression types. So it declares a pure virtual function, which is evaluate, which any derived class must implement. And the virtual expression, this one, specifies the virtual destructor, indicating that the class is meant to be used as the base class. So the key points is that the pure virtual function or virtual double here is for the expression evaluation, and the next one is for emphasizing that the base class is meant for the inheritance. Now, next to this, let's write the another function or constant expression. So let's write class constant, and we choose the expression that we wrote at the top, and let's write the private of double value, and let's write the public explicit constant double val, which is value while with an empty bracket, and double evaluates const override, and it returns the value. So this is our constant expression for our given value. And to clarify that more, so this is the constant is a class derived from the expression, and it represents the constant value and implements the evaluate function by returning the stored constant value. So it is the concrete class representing a constant value, and it stores and evaluates the constant value, and the constructor explicit here, this one, the initialize the constant, and the double evaluate returns the stored constant value. Now let's write our class variable. So below here, class variable public expression. We are going to use the expression class in most of our classes. Private double and varif, and for the public explicit variable double and ref, which gives us varef with the ref value and empty bracket. double evaluate, which const override and returns varif. You can clearly see that these classes use the expression class method as you see here. So this class variable represents the variable and it also derives from the expression and it implements the evaluate by returning the referenced variable value. So it is the concrete class representative variable and it stores and evaluates the value. So when you see the constructor here, the variable takes a reference to the variable and the double evaluate returns the reference variable value. Now let's write the class binary operation for the binary expressions that we are going to use. So let's write class binary operation, which is the public, and use expression and let's say private std function double double and double operation. And unique pointer here, expression and left. We are going to use the expression, so we are going to use the pointer to detect the left and right values. Std unique pointer expression right. Now let's write the public value. So binary operation std function double double double. Let's close the tag, then opt, and it uses the unique pointer expression. And std, and we are going to write again a unique pointer expression r. So this gives us operation of left of std move 1 and right of same like the left one move r an empty bracket and next double evaluate const override and it returns the operation left evaluate and right to evaluate. Okay, so this binary operation class represents a binary operation like addition, subtraction, multiplication, or the division. It takes a function operation representing the mathematical operation and two expression objects left and right. The evaluate function calculates the result of applying the operation to the evaluated values of the left and the right one. So the constructor binary operation, this one, initializes the operation to and left and right expressions, and this double evaluate calculates the result of applying the operation to the left and to the right operation. Next one, which is the DSL functions of our code. So std, unique pointer, constant first, double val, which returns std make unique constant val. So this is the DSL function to create a variable expression. Let's create the DSL for the variable also. Unique pointer variable, which has val, double, and ref, and it returns make unique variable. Now let's write the operations. Now we wrote the variables in our DSL functions, the variables and the constants that we get. And now let's write the operations. So unique pointer of binary operation operator plus which is the unique pointer and expression left is the unique pointer expression to the right. Then it returns make unique binary operation with the double and double R, and it returns L plus R, and it moves the left and also it moves the right. So this is the expression for the addition or the our operation on the addition, when we find the plus sign on our expression, this function is going to be operated. So this function, uh, this is the operator overload to create instance of the binary operation using the plus operator, and it returns the unique pointer to manage the ownership of the created object. While these two, as I said earlier, are the functions to create instance of the constant and variable, and they return the unique pointer to manage the ownership of the created object. So let's write down the other operations also. We only write the operation for the plus sign, so let's continue that one. Unique pointer, binary operation when the operator is minus std unique pointer of expression to the left, and it has the expression to the right, which these are the two values or the two variables that we have that we are going to divide subtract into. So std make unique binary operation double L and double R. Then let's return L minus R. Let's have a space between them to clarify more. And std move left and move right. Now the operation for the subtraction is done. Let's jump into the other operator, binary operation. Then the operator is multiplication. This is kind of similar to what we have been working on. So mm, unique pointer, expression, left and std, unique pointer, expression, right, and it has the return value of make unique binary operation, which has double L and double R, and it returns L times R. And std move left forward. Now let's write for the last one for the division operator. So unique pointer binary operation, operator of division, which is the std unique pointer expression left, unique pointer expression right. So it returns std make unique binary operation. It has double L and double R, and it returns L divided by R, and it moves the values from the pointer. Move right. So okay, here I misspelled operator, so operator. Now we are done with our function, and as I said, these are operator overloads to create an instance of binary operation using addition, subtraction, multiplication, and division operators, and they return the std unique pointer to manage the ownership of the created objects. So their purpose is to overload the addition and the other operations. Now let's write the main function. Now we are done with the DSLs to express. So int main. Here let's have a double, for example, x equal to 5.0 and double y equal to 3.0. Because as you see it here, we are using double values, so that's why we are writing here double. So let's write the DSL usage. So this is how we write one. For example, let's name it expression one and says 2.0 multiplied by for x plus 1.0. And let's have expression 2. Let's use multiple examples to see the value or the result of our DSL. So let's say 1.0 divided by 2.0. So these are the DSL expressions that we have. And let's evaluate the values. So cout results one. Let's say result one to see the value of the results, and expression one evaluate. In the line here and cout. This is to display our results on our console. Result 2. So expression 2 to evaluate. Then in the line, and let's have a return 0. So this is the code that we wrote, and the main function here, okay, the int main function and variable x inside it, we have variable and x defined, and the DSL expressions, expression 1 and expression 2, are created using the DSL function. And finally, the results of evaluating these expressions are going to be evaluated in the console, and this demonstrates the basic implementation of the DSL for simple mathematical expression involving constants, variable, and binary operations. Now that we finished, let's save our C++ file. So let's name it maths DSL, and let's save it. When you save it, we find some errors in our code. For example, here, okay, we forgot. And let's go to our code. Okay, instead of L, we wrote 1. And here, for override, we use different quotation. Let's change that one. I hope it works now. Okay. Let's save our code, and let's go to our top right side, and let's run the C++ file. So our C++ file is now running. Now let's run the code. So we get the results here, and it gave us an output of result 1, which is 12. If we look at the expression 1, we have 2 times x plus 1. So x is 5, so x plus 1 is 6 times 2, 12, which is correct. And for the second one, we have y minus 1. Y is 3.0, so we have 3 minus 1, which is 2, and divided by 2, we have to get the value of 1. Instead, we have 2.5 here. So let's look at the value, or the expression for the given value. So okay. The mathematical operation, okay. First works the division, I think, here. So 1 divided by 2 is 0.5. So y minus 3, okay. 3 minus 0.5, it's going to give us 2.5. So actually it's correct. So this is the simple way to implement the DSL. As you see, we wrote the expressions, and we get the value of the expressions like this, and we are using the internal DSL method, meaning that we are using the C++ as our base code, and we created our DSL using C++, and we have our functions that make the C++ work as we want it. So this is the simple way to write a DSL. Hello everyone. Now let's see how to build a simple DSL or domain specific language. This time we are going to create based on a problem that's stated. Here we have Bob, and Bob is a manager of X company, and he wants us to build him a system that to manage his products. He comes to write to us and he says, "Hi, I'm Bob. I'm manager of X company. While at work, I face issue on managing my products. I need you to create me a system so that I don't have to worry about products and how much remaining on the store." So based on this sentence, we have to write or we have to give him a system to manage his products. As you see this sentence, it's a little bit vague. So while starting to create the DSL, the first thing that we have to do is pick up the grammars from the sentence that we have. And if you look at in the sentence, we have nouns and verbs. And for example, we have here we have the create, and he wants to create, okay, this one is not for the products, but he wants to know how much remaining the product is. He wants to control everything about the product from the system. So from the sentence we have to pick the grammars. So the grammars that we get is the first one is the products, because he says that he wants to manage the products. So this is the noun that we get from the sentence. The next one is the number of products that we have, and he wants to see the remaining, and these are the words picked from the sentence, and he wants to manage the products also. So these given grammars are a little bit vague, so let's change them a little bit. So we have the products, the quantity for the number, and for the management we have this update. On the update we have the adding and removing of the products, and we have an inventory. Currently we are using the product for the single one product, while the inventory is for the other products that he may have on the store, and he wants to see the listing of the products that he have. So the first thing while building the DSL from the given problem is to create the grammar or to define the grammar in order to see the scope of the domain specific language. Next to this, we can create the expression based on the given grammars. Like the products can be added, the products can be removed, and the products have quantity, like the and inventories are a collection of products, and we can see the listings. So this is how we write the grammars, and we are going to write the C++ code. We are going to use the internal DSL for this issue. So next we are going to write the C++ code. Let's start by opening our VS Code, and here let's close this one and let's create a new file, which is a text file, and let's select a language, and we are going to write using the C++. So as I said, this we are going to write the system for Bob and using the simple DSL, and DSL is a programming language that is designed to solve a specific problem within the particular domain, or we are going to write the internal, so we are going to use C++. Now we start by importing the libraries. Like the first one is include a string, The second one is vector, and the last one is algorithm. So these are the libraries that we are going to use. Like we imported the necessary libraries for the input output here, the array stream, and for dynamic arrays we are going to use the vector, and for the algorithm like find, if, and others we are going to use this algorithm. So we imported them. Next, let's write our first class, which is the product. So class product, and it has public std string name and int quantity. Our product is going to have a name and a quantity. That's why we are making this class. And product const string and the product name and product quantity. We are going to use this class in order to add and to manage our product. So this is how we write the code. And product quantity. So this defines the product class with two public attributes, the name and the quantity. And the constructor initializes these attributes here. Now let's write the inventory. Class inventory, private. It has private attributes and vector product products. It's the collection of the products, our inventory. So we are using the vector to store all these products. Public, and let's see, have a void add product const string, and it takes the product name and initial quantity, which is an integer. So the products, new product, let's create a new product with the product name and the initial quantity. Then let's push our given our created new product to our inventory. And let's show the bob that the product is added. And also let's display the product name with the quantity, how much he added, initial quantity. And let's close it with new line. Okay, for the quantity, let's close this one. Let's make it inside the bracket. And we wrote our first add product instance. Now let's add the update quantity with const string product name and int quantity change. And let's auto it find if the product is inside our the products dot begin and products dot end. To find the given right, okay, to find the right product, let's find it and let's pass the product name const product and p, and let's return p dot name, or if you find the right product, and let's close our tag. Then if you find, okay, if you don't find the product, then we are going to quantity change. Then let's display updated for the product name and the quantity with the new line. Else we are going to display product not found if the user inserts the product that's not found. And product name like this. And lastly, let's write the void function list products And this is going to list us the products that are available inside our inventory. So let's display product inventory with a new line. And for const auto product products, let's display see out the name, and let's map the name with it. And next to that, let's display the quantity. So let's give it a little bit space. Quantity. Then product dot quantity. And let's close it with a new line. So here we are going to display the or list the given products. So this is the product class, or I mean the inventory class that we have, and it has a private vector of products, and it has a method of add product, as you see, to add the new product to the inventory. And we have the update quantity here, and it updates the quantity of the products in the inventory. And the list product, as the name indicates, it's going to list the given products that are available inside our inventory. Now, let's write the main function so that the Go can interact with the our main function or our return function. So let's write the int main, and here we are going to invoke the inventory class that we wrote. So inventory, let's create my inventory. So okay, we have inventory here, so we invoked it here. Next, let's have in choice, and here we are going to display different choices for the user or both. So let's use the do cout, and the first choice that he has is to add products. And let's close this with new line. And by using the Shift and Alt, you can populate this one. And for the second one, let's give this update product. And for the third one, let's make it list products. And for the fourth, let's make it an exit. This is the fourth. And here, let's change this one to enter your choice. The user is going to select from these four, and from the given input we are going to take using the scene choice. we are going to get the value of choice from the user here. And with that, let's have a switch. A switch with the choice that we have. And inside the switch, we have the case. And if the first one is if the case is 1 or if the choice is value is 1, what we are going to do is string the product name, then int initial quantity, and let's give the inter a choice to add the product name, and let's use the cin dot ignore empty, and get line cin product name. We are assigning the value of the cin value to our product name that we created here, the string that we created here. And next, let's write cout enter initial quantity, and let's make cin with initial quantity value, and now we are going to add this product to our my inventory that we invoked here with the product name that we got and with the initial quantity. Okay, initial quantity. Next, after this, we are going to write break to get out of the loop or to get out of the case. Next, let's write the case 2, which is the update product here. Then for the update product, we have string of the product name and int is the quantity change. This is int, not init, sorry. Next, let's have cout with enter the product name. Then let's take the cin value and we are going to ignore if it's empty. And using the get line, we are going to assign the cin value to the product name. Let's not forget here to add a break always. So cout enter the quantity change. So it could be positive or negative. So let's add this option also. The user can add the positive number or negative number. So cin, let's make our context change to be an input of the from the user. Then using my inventory dot update quantity, let's pass the product name and the quantity change. And next to this, we are going to write break to get out of the loop that we have. And the third case is case 3, which is to list the products. So what we are going to do is my list dot list products and write break here. The last one is case 4, and the case 4 is to exit. So std cout exiting dot 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 new line, and let's add a break here. And always don't forget to write a default value right when writing the switch. So coutts invalid choice. This is going to appear if the user is going to add a wrong data to the cin value valid option with new line and a break. Then we are writing the do function, so always there is a while next to the do. So because this is the do while function, unless this is for, the choice is for, and we have the return of value of 0. So this is how it looks our main function, and the program starts by creating an instance of the inventory here at the top, which is called an my inventory, and the main function presents the menu to the user, and a do while loop. The user can add a product, update quantity, list product, or exit the program, and the program ends with the return statement indicating the successful execution. Always, even though it's an error, it's going to return with the successful execution. So let's save our given file. So let's name this Bob's system and make sure it's saved as a C++ file and in the right directory. Now that we saved the file as a C++ file, we can see some of the errors are appearing, which is the nice thing. Before, it's always good to see the errors before running the code. Here we have an issue and it is misspelled. It should be quantity. Okay, and here, okay, the expected expression should be like this. It shouldn't be double equal sign. And here we have at the end The break is showing us an error. I don't know what the issue is. Okay, here I forgot to add the break. So I think everything looks cool. Let's save our file, and next let's go to our at the top right corner and let's run our C++ file. So let's build and debug the active file using the G++. So now let's run it again. Let's run the C++ file. Now it's appearing that you can see clearly here it says the add product. It's listing us the options to update the product, list product, and the exit. For example, let's click on one here to enter the choice. So let's enter the product name. Let's say this paper, and the quantity, let's give it 5. So we have added the paper quantity to our inventory. So let's look at the list that we have here. So here we have the paper and the quantity, and this is how it appears. Okay, now let's add another product, and let's name it this pen, and let's have the initial quantity of, let's say, 10. And let's look at the list that we have. So let's input 3. So here we have seen that we have pen and paper added to the quantity. And okay, let's look at the code once. The product, okay. List the product, and this should be a double quotation. Let's stop this one by Control C, and let's change this one to double quotation. Let's save it. Let's run our C++ file. So now let's add the product first. Let's call this one paper. Currently, we don't have any database to store our files, so it won't save to the system, but this is how it looks. But in real world, we are going to save the files once it's added. So if we see the product, we have the paper and the products. Okay, let's look at the code on add. Okay, so okay, so let's add another product again. So let's write type 1, and let's have a pen with the value of 10. And if we list it, now we have the pen and the paper here in our data. And if you want to update, let's click on update and the product name. So let's write for example, pen. So enter the quantity change that you want. For example, let's make this one 7. So the quantity of pen is now updated to 17, because as I said, here we are going to write positive or negative. So then it's going to add or subtract the value from the given product. So if you see now the list, the quantity is 17. Let's try with the update with the paper. So let's click on 2 and the name is paper, and let's subtract 3. And when we list the value, we can see that the remaining quantity is 2. So this is the simple DSL form that we wrote for the Bob's inventory management system. And this code creates a simple inventory management system where Bob can add product, update his product quantities, and list the current inventory. And it demonstrates the use of class, vector, the user input, and basic control flow structure. So this is the simple DSL. Write a DSL program for the given problem. We have here Angela. She's saying, "Hello, I'm Angela. I'm facing an issue managing my tasks every day. I keep writing my tasks on paper, but I kept forgetting it. So I need you to create me a system where I can log my tasks and manage them. Use C++ or internal DSL to write the program for the given problem." Solve the issue that Amanda have stated. What we have to do is we first create our C++ file, and then before writing the code we have to know the scope that we are going to write. And before doing all the function and all the tasks, we have to write the scope that we are going to write on. She is facing an issue on managing her tasks. So what we are going to do is we are going to make it a very simple one for this purpose, but you can modify it as much as you want. So what we are going to do is we are going to create a task, and that task can be completed or not. And she can list all of the tasks. And I'm going to write the simple DSL form. You can enlarge it as much as you want. So let's dive into it. So let's select a language, C++, and we start always by including some of the functions that we are going to use. We use this include as string for input and output purpose. And the next one is vector, and we use this function to store our objects of our task. And the next one is algorithm, and this is for the algorithm purposes. The first class that we are going to write is the task, and so this is class task, and it contains a public of standard string description plus a boolean value of completed. It contains two public functions. The first one is the description of the task, and the next one is the boolean if it's completed or not. And the task string description disk, let's say it's disk, so it's going to be description is going to get the value of disk, and the completed is by default is going to be a false. So we have this method that we can initialize, where when we add a new task, we are going to call this task method, and what it does is it gives the name or the description, and by default it gives for the boolean completed a false value. So this is our task, and it creates the string description and the completed one, as I said, and the constructor that we have here is a task, and it initializes the task given description and sets the completed false by default. Next, what we are going to write is the task list, which is composed of the task class, task list, and it has private value of standard vector. It's going to store the value of the tasks in our given vector, which we are invoking here at the top. And next, it has public values. The first one is void add task, and standard string description when you add the task, and this description is going to be passed to the method that we have here. Then what we are going to do is tasks dot pushback using the function pushback the new task. After we added the task, we have to tell our client or Angela that the task is added. And standard inline. Okay, the next method that we have is void mark complete. When one task is completed, we have to pass the Boolean function of the completed. So here we have index greater than or equal to 0, and task dot size then tasks, and we are going to find it by the index completed to true, and we are going to let Angela know that the task marked as complete, and from the tasks let's pick the index and the description, and let's finish it by inline. Else, if the task is not found in our tasks list, we are going to let our user know invalid task index. And let's finish this one also by new line, end line. Here I think I made a mistake. And the next method that we have here is for list tasks. which is going to list all of the tasks that are remaining. So what it does is, this is a simple function. It's going to show task list in standard inline, and we are going to loop over the given tasks. So size of the task, let's say 0 first, and I is less than tasks dot size, and this is the simple loop, so plus plus I. So standard cout. Let's wrap our function by bracket, or the task name by the bracket. So I plus 1. We are giving it the number. And if task is completed, then what we have to do is we are going to show that the task is completed, right? So standard cout is completed. Otherwise, we are going to give the output of tasks with its description or its name. Either way, we are going to display this one, but if it is completed, we are going to have another tab which is completed here that's going to be shown. So this is the task list function that we have. So in order to clarify it more, we have the tasks class at the top, which has attribute of description and completed. Which one is the first one is the string, and the next one is completed, is a boolean. And we have the constructor here, which is task, and by initialization it has the completed value of false. And here we have the task list, and it has an attribute of tasks, and it is a vector of task object to store the list of tasks. And here we have methods of the task list. So the first one is add task, and this adds a new task to the task list with the specified description. And the next one is mark complete, and this one marks the task at specified index as a complete. And the next one is list task, which displays the list of tasks along with their completion status. So now let's write the main function so that we can display the output of the given classes. So let's write here int main, and let's create a task list called my task list, and let's have an int of named choice. The user is going to choose using the do while loop. So standard cout, the first option is going to be add task, then new line. So to save time, let's click on Shift and Alt and click the arrow down button. Okay, the next one is going to be mark task. Okay, mark task as complete. The next one is going to be list tasks. The third one, list tasks. The fourth one is an exit. And at the end, let's have a description saying enter your choice. And let's remove this new line from the enter your choice. So next to that, let's take an input from the user. So let's add standard cin with choice value. And here we are going to have a switch based on the value the user is going to insert. We are going to have a case. The first one is if the user chooses 1, let's have a standard string description, and then we are going to see out enter the task description. Next, we are going to take the input from the user cin dots ignore. If it's empty, we are going to ignore it. Otherwise, using the get line, we are going to give the value to the description, and by invoking my task list dot add task, we are going to pass the description, and at the end we are going to break from the function to get out of the switch. So okay, next what we are going to have is the case 2. And here the user is going to have an index, so let's create an index int first, then standard cout enter task index to mark as complete, and the user is going to pass the scene value, and we are going to pass this to the my task list and mark complete with an index -1, because the user is going to see the index from 1 to the rest, but the array is going to start from 0, so we are going to subtract one value from there, then break. The third case is if the user clicks on third case, which is to list my tasks. So my task list dot list tasks, we are going to invoke that function, and we are going to break. The next one is case 4, where the user is going to click exit, so we are going to show him exiting. dot dot dot, and let's end it by a new line, then break. And the last one is the default value. The default value is always necessary because the user may insert some unnecessary values, and we are going to show an error showing invalid choice. Please enter a valid option. And then we are going to break from the loop. And okay, here we have the switch and we have the do while loop. So let's have the while the choice is not 4. When the choice is 4, we are going to get out of the switch function and also this do while. Otherwise, this is going to pop up again and again. Return 0. So this is how the function looks. Next, let's save our C++ file. Let's name it Angela's tasks and make sure it is saved as a C++ file. Now we have some errors in our function. We can see that from here. So the first one is here. Okay, I forget when I am writing the cout. And here, this should be tasks, not task. Okay. And the last one is where in the break here. Okay, I forgot. So C++ is very case sensitive, so make sure always to check the errors. Let's save the code. Now on the right top corner we have this run C++ file. So let's run the G++. And let's run the code. Now it says it displays this add task, mark task as complete, list task, and an exit. So let's add a task first. So let's give it, the task is going to be cleaning. Okay, now let's list the tasks. Let's click on 3. So we have here cleaning. This is showing us. Now let's add another task. And let's name, or let's give the task of like reading. Now, if you list the tasks, we have cleaning and reading, and we can see the index here 1 and 2, but in the vector, they are going to be stored as 0 and 1. So the next one is let's mark task as a complete. So let's click on 2. So enter the index, the mark to mark as a complete. So the index we want is let's finish the cleaning. So let's click on 1. So task marks as complete and which is cleaning. Now if we list the tasks, we have this completed in the beginning of the cleaning, and the reading is going to be just displayed. Now at the end, let's click on the 4 to exit from the loop. So it says exiting. Now we are out of the function or our DSL. So this is how we implement the simple task management. Hello guys. In this video, we are going to build a simple compiler using the base language of C++. Previously, we have seen how to build a compiler by theory. We have done some calculations, So now let's build a simple C++ compiler by following all the steps. So the first thing in the compiler design was to build the Lexer or the lexical analyzer. This part, what it does is it generates a lexemes or tokens that are going to be identified by the parser. So the first thing that we have to do is we have to know the token types that we have, like symbols, integer, number, identifiers, and so on. So here we are going to build a simple Lexer for a mathematical calculation. So let's start by creating a new C++ file. We are going to click on text file and let's select the language of C++. And first, let's import some of the libraries. And first, let's import the include IOStream for the main purpose or to get input from the users. Next, include, sorry, include cstring. Now, let's define our using namespace standard. We can use the standard in our codes, but to simplify our code, we can specify the standard here so that we can only use we can use directly cin and cout and some of the other functions instead of using standard then the double colon and cin cout. Rather than we can specify it here. And after that, let's define our the max value our Lexer is going to work on. The first one is the max is 1000, and next one is max of identifier, max of identifier. Let's give it 25 so that users don't just add multiple multiplies more than 25. This helps us for our computational purpose since we are building a simple compiler. Now let's add the enum of token type. The first one is identifier. Let's give it value of 1. Next one is integer. The next one is add sub. And for the last one, let's add assign. So this enum token type, this enumeration defines different token types that the Lexer will recognize. The token types include the identifier, integer, add, addition for addition, for subtraction, and assign. We are building a simple calculator for mathematical purposes, so I think it would be enough to add only this one. Okay, next, let's have the structure table node and sorry, let's give it the int of type and character token with the max of identifier. So this table node, this structure represents the table entry for a token. It includes the type of token based on the token type enum and the actual token up to the max of identifier characters. So this is how it looks. And after that, using the table node, let's have an array of token table with the value of max So this is an array of table node structure representing the table of tokens, and the array had the maximum size of max or 1000 in this case, which limits the number of tokens that the Lexer can handle. After that, let's have int table name of the row. Let's define this. We are going to use it, and this variable keeps the track of number of entries in the token table, and it is initially set to 0. We are going to use it. Next, let's have a bool value of error flag, and as the name indicates, this is helpful for to detect an error. And let's give it the false value for by default. And this flag is used to indicate whether any error occurred during the Lexer operation, and it is initialized to false. Next, we have let's create some other thing. And after the error flag, let's have enum error type with unknown identifier. And this is the enum type, or this enumeration defines different error types that the Lexer might encounter. And in this code, there is only one error type, which is unknown identifier. If we are using something different than our token types, given token types, we are going to get the unknown identifier error. So that's why we are using that. And okay, after that, let's write the function to get the error from our code. Void, sorry, this is small letter, void error. It has an error type, const and string. It's going to detect the error. So error flag is going to be true, and the cout is going to say error and end line. Let's have a switch value here with the error type, and if the case is unknown identifier, you're going to have unknown identifier, and you're going to display the string, which is the unknown one, and let's close it with a new line, and let's break the loop. So this is the error function, and it is responsible for reporting errors. It sets the error flag to true and prints the error message based on the type of error encountered. Now that we finished the error, let's write the Lexer. But generally, when you are building the bigger parser and Lexer and the bigger compiler, we are going to handle this error using the error handler function, which is outside of our Lexer function. And we have the symbol table manager and error handler, which handles the symbol tables that we have in our compiler and error handler. But since we are building a small compiler, let's first create the error function here so that we can detect the errors. Now let's write our Lexer. Let's name it void scanner, and it's going to get the character pointer and the source code. And let's define the code length like this. This string length is the function to detect the length of the string that you have. And let's define the character index to 0 by default now. And next one is the table index, which is by default 0. Now let's write a while loop while the character index is less than the code length. We are going to have a loop if it's more than the character index is greater than the code length, then we are going to return the function out because the character index should be inside the code length. So let's first start by skipping the white spaces. While is space, then the source code, the character index. If the index is if the source code's value in that index is empty space, then we are going to skip it by just adding the character index or character index plus plus. So if the character index is greater than or equal to the code length, we are going to break the loop also. Now let's look at the identifiers that we have. So is alpha if the source code with the character index value or the given value or the source code with an index of value now let's have a character of string with the value of max of identifier and int of the string length with the value of 0. Now we are going to write a loop function here while is unknown. The source code index character index value or the value in this index string with the string length plus plus is equal to the source code with the character index plus plus. Inside of our while loop, Let's add the string with array with the string length of 0 and token table with the table index value dot type is going to be an identifier. And the token table with the table index dot token and the table index plus plus. So here we have the identifier recognition. If the current character is an alphabet or an underscore, it starts recognizing as an identifier. It uses another loop to capture the entire identifier using isAllNo, this one. And to check the alphanumeric characters, we use this isAllNo. Now let's look at the integer constants. So let's write our loop here. So if we have the if function here, then next to that, let's have else if for our digits. So is digit, we are going to use the function is digit and the source code with the character index that we are looping over. So let's have a character with the max of identifier value and integer with the string length of the 0. Now let's have a while loop while is digit of the source code with the character index value. What we are going to do is we are going to add the value to our string array, string length plus plus, and the source code with the character index of plus plus. And then in the token table, we're going to add it with the table index of the type. We are going to give the integer value. With the token table and table index of dot token and table index plus plus. So this is the integer recognition part. If the current character is an alphabet or if the current character is a digit, it's recognized as an integer, constant, or in a similar manner. So next to this, let's have for the operators. The last one is else. If it is an operator, and the source code is ch index. Let's use the switch function here. The given character from our source code. Let's use the case here. If you have addition here, the now let's go to the token table and with the table index and dot type, and let's change this one to add, and let's break the loop. And to save some time, let's click on the Shift plus Alt and click on the down arrow key to populate this one. Let's change this to minus, and we are going to change this one to the sub and break. Next, let's change this to the equal sign, and let's change the value to assign. And for the last one, let's change this to, okay, let's remove this one and let's add default value. So by default, we are going to have an error if the given value is different from these identifiers. We are going to throw an error of unknown identifier. Unknown identifier. And we are going to return. Then now we have done this switch loop. Let's add the values on the token table with table index dot token and the table index plus plus. Now outside of our while loop that we have here, let's add a table num with the table index value. Now we have done the parsing here. So this is how it looks. We have the operator recognition written here, and if the current character is not alphanumeric, it recognizes the operators such as plus, minus, or equal. And we have the switch statement, and it uses the switch statement to determine the type of the operator and assigns the appropriate type to the current entry on the token table. And then we have the copying token to the table, and it copies the recognized token identifier, integer, or operator. Then we have the incrementing indices, as you see here, and it increments the table index to move to the next entry on the token table, and the character index to move to the next character of the source code. And at the end, we have the end of the Lexer loop. The Lexer continues until the end of the source code and it's reached. And the other thing is the setting on the table name. After the Lexer finishes, it sets the table name to the final value of the table index. Here we have that one. Now we finish the Lexer. So let's write the main function to see the output of the Lexer that we have. Let's start by writing the int main with the character of the source code of, and let's give it the array size of max, and let's use the cout since we used or declared the namespace standard here. We don't have to use the std here. We can just write cout, and let's write enter the source code, and at the last input the hash, input the hash here to int, and let's finish it by new line. Then the user is going to insert the values, so let's use the get line here. Then let's use the source code with the max until the hash value is inserted. When the hash value is added, and it's going to stop. So let's add the value of the source code to our scanner. So let's see out the tokens, and we are going to generate the tokens from our scanner. So let's use the for loop. Int I is equal to 0 and I is less than the table name, and we are going to add the value of I as you go down. Then let's use the switch, and let's look at the token table with the index value of I, and let's look at the type, and let's look at if the case is an identifier. Then we are going to cout identifier with the token table of I.token, or the value of the identifier. And let's finish with the new line and break. Next, if it is an integer, let's have a cout of integer with the token table value of index of I and token, and in the line. And also again, let's break the loop. What we can do is we can populate this by using Shift Alt and down arrow to save some time. Next to the integer, let's add the add, and let's change this integer to operator. And for the next one, okay, here we don't have to show the token value. So what we can do is operator, and we can just show the plus sign here, and let's remove this one, it's unnecessary. And let's finish this one also by new line. We can do that. And if it is sub, we can change this to operator, and like this. Let's finish it with new line, and let's remove this end line. And also for this, let's have operator. We can actually specify the values like operator, addition operator, things like that. But to save some time, we can do it like this. And here this is going to be operator assign, and the last one is the default value. Default is going to break the loop. So next to that, let's have the error function. If there is an error flag, return 0. And let's have the return all by default. So let's save our function. Let's give it the value of, let's say, scanner, and make sure that it is the C++ file. Okay, we forget a here's some tag, and also here there is, I forgot to change this one to, I used the curly brace while I should have used the normal bracket. Let's save it now. Everything is looking good. Now let's run our code, C++, using the G++ that we have. So our function is now run correctly, so let's run it again. So enter the source code and input hash to in the value. So what we can do is let's assign the value, like for example, let's say x is equal to 4 and y is equal to 5. Then let's say z is equal to x plus y. And at the end, let's write hash to end the function. So when we do that, then our tokens are generated. Here we have an identifier x, operator, equal sign, integer of value 4, identifier y, and blah 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 to the next. So this way we can specify the Lexer, or we can know that the output of the Lexer currently we are displaying it using the int main, but by default what you have to do is this value is going to be passed to the parser, so that the parser is going to look at this Lexemes or token and generate a parse tree, and we are going to do that next. But as you see it here, this is the output of the scanner, and the scanner or the Lexer that you have is going to identify them like this is an operator, this is an integer, this is a identifier, and things like that. So this is how we write the scanner or the simple Lexer. Now that we have seen how to create a lexical analyzer, now let's jump into the parser. So we have seen how to create the lexical analyzer and a token that can be useful for the parser. So now let's jump into the parsing, how to create a parser. So as you know that the parser is the step of in the compiler design that is going to generate us a context-free grammar or CFG. And to create a parse, we use the parsing table and some mechanisms. But since we are working on a very simple compiler, we are not going to add the dictionary here. And since you are not using the symbol table and the error handler, and that's we are not going to jump deeply into the parser, but let's now create the parser that generates the string address code. So let's first create the class parser, and before writing the parser code, let's have another class which is we are going to call it, let's say, emit, and const char of result, and const char asterisk of left parameter, and const char of pointer operator, and const char of the right parameter, and it's going to give us the result with the equal sign, then the left parameter, then with the operator that we are using. Okay, sorry here. Then the operator that we are using, space, and again the right parameter. And then let's add the end line here. And so, sorry here, it should be car like this. Okay, now what's this emit class? So the purpose is this function is responsible for emitting or printing the generator code of an operation. And as you see, the parameters are result, the result variable where the operation result will be stored here. And the next one is left parameter, the left operand of the operation. Op is for the operator that we are using, the plus or the minus, and the right parameter for the right operand of the operation. And the functionality, when you see it, it prints the line of code in the form of result is equal to left parameter operator right parameter, meaning that it's going to give us cout or the value of the string address code here. Okay, good. Now let's write the parse function here. So int table index, let's initialize this with 0. Now let's have a while loop. So while the table index is less than the table num, then let's have the function if the token table value of the table index dot type is identifier. If we are facing with an identifier, then the left value is going to be token table of the table index token. And let's add the table index by 1 here. Okay, the purpose of the parser is to function represents the parser part in the compiler, and it processes the token generated by the Lexer, and it generates the code accordingly. So the first one is initialization, and it initializes the loop that will iterate through the token stored in the token table. And when you see the parsing assignment statements, the first one is the one that we wrote here. So if the current token is an identifier, it assumes that it is the left operand of an assignment. And let's write the next one, which is if the coming token from the token table dot type is an assign, then let's add the table index, and okay, car the right value is going to be the token table value of the table index token. And let's add the table index. So if the next token is an assign operator, it assumes it is an assignment statement, and it proceeds to parse the right hand side of the expression. Okay, now let's have another while loop. So while the table index is less than the table num, and the token table value of the table index dot type is add or the token table that we have, the token table, okay, with an index of the table index of type subtract so what we are going to have is let's have a car of operator with the token table in the token index dot token value, and let's add the table index by 1. Let's fix this one. Sorry, this is the table index, I mean, not token. And let's remove one of the brackets. It's unnecessary or redundant. Okay, now let's have the right hand side expression. While the table index is less than the table num, and the token table is the table index, and type, when the type is an integer, right? So I think we don't have to use while. We can use the if else. So let's change this one to the token table with the table index value of type when the type is identifier, or when the token table with the table index of the type where integer. So integer, let's have our function. So char of the next value with the token table of the table index dot token. And let's add the table index by 1. And now let's create a new temporary variable, and let's call it temp var, and new char of the max of identifier, the size of max of identifier, and with the temp var, and let's give it the value of, let's name it temp. And after that, let's emit the value that we get. The emit is only necessary here because we want to display it in to our users. So otherwise, we may not need the emit class that we have at the top. Okay, after this, let's add the right value to the temp var. Now we wrote the if function. Now let's write the else function. Else we are going to throw an error if it's not an identifier or an integer. If it is an assign or an identifier, we have the loop above. But if it's not all of them, then we are going to throw an error, which is the unknown identifier, and the token table and table index, and let's spit out the token. We have the if else now. Okay. Next, what remains is to emit the value again. So we have the if function here. So for this if function, let's write an else inside here, and I don't know why this one brace is here. For the if else, for this if else, we have finished. And now let's also again let's emit the value if it's an identifier. Currently we use it for the integer only, and so let's add our emit emit the left value and the right value, and comma like this. Now for the this if, let's write an else function Okay, so this emits. Okay, we have function here, right hand value is undefined. Okay, I placed this if function in the wrong place, so let's put it here. Nice. So this is the parsing right hand side expression. It assumes the next token is the right operand of the assignment. And while the next token is our add or subtract operator, it continues parsing and emitting code for expression. And for each operation, it generates a temporary variable, emits the code using the emit function, and after parsing the right hand side expression, it emits the assignment code to using the emit function that we have here. And now, right, since we finished with the emitting part, let's write the else function for this if. Let's write here an else, and let's throw an error or unknown identifier, and let's have the token table of the table index dot token. Okay, and again we are going to repeat this one for this if function, and else just copy this one and paste it here. And one thing that I forgot is that we have the return here and also here. We should have a return value also here. Now that we have finished the parsing and the error handling, if there is an unknown error, as I said, it's going to speed up. And after this, we have the loop termination. The loop continues until all tokens in the table token are processed. And now let's customize the main function again. Previously, we used it to look at the list, but now we don't need this all token. So let's remove all of them and let's put the error flag there, only that one. Okay. After that, let's have the scanner with the source code, and let's have the parser. Now everything is looking good. And this function or the main function reads the inputs, runs the scanner, and then runs the parser. And if there is any error during the lexing parsing or the parsing, the program returns with the status of the error. Now let's save our program and run the code or C++ file. Let's click on G++ and make sure that we are not on the previous scanner file, because it's going to generate us the previous one if you are on the previous one. So make sure to delete that one. So let's write a is equal to 2 and b is equal to 4 and c is equal to a plus b plus 3. And at the end, let's have the hash and let's see the parsing, what it generates. So it generates a is equal to 2, b is equal to 4, and it's going to have a temp file where a plus b temp is equal to a plus b, and the other temp is going to add the 3 to our previous temp, and at the end it's going to store it in the C, the temp file. So this is the string address code that's generated by the parser, and this is how it looks. This is very simplified, and this is the very tip of how the parser looks. In most cases, while building the parser and the compiler, there are some parts like memory allocation that we haven't touched, and also we are going to have a symbol table manager and error handler by themselves. Currently, we don't have that one, but this is the simple way to create the parser for our given compiler. Now that we have seen how to create the lexical analyzer and the parser, now let's jump into intermediate code generator. As you know that the intermediate code generator generates a low-level language that's closer to our target language. Most of the time, it's going to be an assembly language. By default, the intermediate code generator works with the symbol table manager and other functions, but since we are working on simple compiler design, let's mimic or let's try to see how the intermediate code generator works. So let's start by creating a new file, and let's select language of C++, and let's start by including the libraries that we use. The next one is include string and include vector for the arrays. Vector, sorry. Let's define using namespace standard or std. Let's define our class, and let's name it x86 assembly generator. And since we are trying to mimic the intermediate code generator, it's better to name it like this. And what we are going to do is the purpose of this class that we are working with, it represents the simple code generator for 86 assembly instructions. It provides methods to generate various 86 assembly instructions such as move, add, subtract, multiply, and it also has methods to create temporary variables. Well, by default, the general one, it works with like memory allocation and things like that, but we are not going to write that one. We are mimicking. So public, let's start from the public values, add 6 assembly generator. Let's invoke it again, and let's have a value of temp count of 0. And this is an integer that keeps track of the count of the temporary variables created. And next, let's have an instructions. So string generates assembly and const string assembly code. And let's have a for loop const auto and instruction. Then the assembly code is going to add the value of the instruction. New line, and let's close this with new line. And let's return the assembly code. So this generate assembly generates the complete assembly code by concatenating all the stored instructions, and it returns the string containing the entire assembly code. Next, let's write the create temp variable method, and this is create temp variable method, and as the name indicates, it's going to give us a temp value that we can store our values there with temp count plus plus, and it creates a new temporary value by incrementing the temp count and returning its name, and the string it returns the string representing the name of the newly created temporary variable. Now let's have a void constraint and constraint source, then instructions dot push back the value of the move. Let's give it space there, plus this, then comma space plus the source. So this generates a move instruction that moves the value from the source to the destination, and the dest is for the destination operand, and the src is the source operand that we have. So this is for the move, and for the add, what we can do is we can populate this one by using the shift and alt. And for the second one, let's change this move to add, and the values are going to be the same, and instruction and pushback, and we are going to change this move to add. The next one is for subtract, so let's change to this to sub, and let's change the pushback value to sub. Next to that, let's change it for the multiplication, and we are going to give it mul value, mul only. And so to the purpose of the first one is for generate add. It generates an add instruction that adds the source operand to the destination operand. The next one is the join sub, and it generates a sub instruction or subtraction instruction that subtracts the source operand from the destination operand. Then the last one is genmul, and it generates a mul or a multiply instruction that multiplies the destination operand by the source operand. So these are the functions that we have. Next, let's give it a private value of int temp count, and let's give it a string instructions. These are the private values. Okay, now we have done with the function for the code generation. Let's write the main class that we have. So int main, and here let's invoke the code generator that we have, and let's name it assembly generator. Now what we are going to do is we are going to create a string address code for generation. What we by default it's going to get is this is going to get the value from the parser, but we are mimicking the code generator, so let's create the string address code here instead, and let's see the output that it generates for us. So string a with the value of a, and string b with the value of b, and let's create a temporary values also, temp 0, and assembly code, no, assembly generator, sorry, dot create temp values, and string temp1 is assembly generator dot create temp value. Next, let's have a string of x is equal to with the value of x. Now let's assemble our code. So assemble generator dot gen move. Let's move the value of the a to our temp 0. On general, this has its own function that reads from the parser and moves it. That's currently. Let's see how it works by let's write the code by ourselves, and let's see the output of the given code generator. So temp 0 and temp 1 and assembly generator. No. Temp 0 and x. So string assembly code, assembly generator dot generates assembly, and let's see the outputs. So the generators assembly code, let's give it a new line, assembly code, and let's end the line, and let's give it a return value of 0. So what we are doing is this should be a by default a function that reads from the parser and that gives the for the assembly code if it's going to be like if it's going to be a multiplication. What it does it assigns the value for the assembly generator by looking to the parser. There should be a function that reads from the symbol table manager by default. The symbol table handles all the values, so it's going to look from the symbol table and pass the values these values to the assembly generator, but currently we don't have that much, so we are mimicking all of the things. Let's save our value and let's name it this one CodeGen and make sure it's C++ 5. And let's have a colon here. Now everything is working fine. Let's save it. Let's go to the right top section and run our C++ file using the G++. So this is going to be our generated assembly code, and first it moves the value of a to the temp and moves the value of b to the temp1, and it adds the value of temp0 and temp1 and stores the value in the temp0. Then it multiplies with the temp0 with the x. So this is how the generator code looks like, and this is an intermediate code that is generated, and the main thing that we have to understand is that the code generator is going to take the values from the parser, the thread code, and it's going to assign the values to the memories that we have, and it's going to create us an assembly code most of the time. And this is how it looks, but we are mimicking, as I said. There are a couple of things that are missing, like the memory allocation part, which is the essential part, because we need the memory to store the values, because these things are going to be done on the registers, so we need a memory allocation for that. Currently we are not doing that, but when building a real-time compiler, we need to assign the memory locations for specific targets, and we have to assign the size for each values. But as a simple example, we can see that we can generate a assembly code from the given instruction. Explain the use of symbol table management in a compiler. To answer this question, the symbol table is an essential function of a compiler that is to record the variable names used in the source program and collect information about various attributes of each names. These attributes may provide information about the storage allocated for names, its type, and its scope. When I mean scope, where in the program the value may be used. And in case of procedure names, such things as numbers and types of its arguments, the method of passing each argument, for example, by value or by reference, and its type returned. So, symbol table is a data structure containing a record of each variable names with fields for attributes of the name. The data structure should be designed to allow a compiler to find the record of each name quickly and to restore or retrieve data from the record quickly. Hello guys, this is the last part of our compiler design course, which is the recap of the key concepts in compiler design. We have seen what compiler design means, what compiler means. First, compiler is a program that can read a program written in one language or the source language and translate it into an equivalent program in another language or the target language. We have seen the steps in compiler design. These are the steps. The first one is lexical analyzer. The next one is syntax analyzer. The third one is semantic analyzer. After that, we have intermediate code generation. Next to that, we have code optimization, and at last, we have code generation. To see them, The first one, Lexical Analyzer, eliminates the comments and white spaces. Input strings and output tokens or lexemes are the features of the lexical analyzer. It gives the lexeme or tokens. The next one is syntax analyzer. This syntax analyzer generates a parse tree. We call it the parsing phase. After that, we have the semantic analyzer. Once a sentence structure is understood, we can try to understand the meaning. And the semantic analyzer checks the meaning by looking at the simple table manager. And if it has an error, it throws an error. And after that, we have intermediate code generation. And it generates an intermediate code, usually generates a string address code or assembly code. After that, we have code optimization. And as the name indicates, it optimizes our code. Automatically, it modifies programs so that they run faster, use less memory, and conserve some resources. At the end, we have target code generation. This will generate an assembly code that is specific to the platform that is running on. So in the left and in the right, we have symbol table manager and error handler. And the symbol table manager helps for each phase to have their resources on. For example, from the lexical analyzer, it accepts the data. And when on the syntax analyzer checks the symbol table manager as a reference while parsing the given tree. And so is the next ones. And the error handler checks the error that's going to happen in all of the phases. These are the steps, or these are the main steps in the compiler design. Next, let's see the further learning resources that you have. The first one is compilers with principal techniques and tools, which is the Dragon Book by Alfred, Aho, Monica, and others. And this is the class textbook, often referred to as the Dragon Book, is a comprehensive guide to compiler construction. It covers the theory and practice of compiler design, including lexical analysis, syntax analysis, semantic, and all aspects. Next, we have Engineering a Compiler by Keith Cooper and Linda Torkozon. And this book provides a hands-on approach to compiler construction and focus on the practical aspects of building a compiler. It covers intermediate representations, data flow analysis, and code generation, making it suitable for both beginners and looking for practical insights. Next, we have modern compiler implementation in ML or machine learning. The author is Andrew Apple, and this book takes a unique approach by using the meta language as the implementation language. For example, it covers lexical and syntax analysis, semantic, and code generation. There are also editions to this book for other languages like C and Java. Next, we have compiler design, theory, tools, and examples by Thijs Bergman. And this book provides also comprehensive introduction to compiler designs and so on. And we have at the last we have Introduction to Compiler Construction with Unix by Axel Schreiner.